Hello and good morning, good afternoon, good evening, whatever it is, wherever you are, and welcome to Wilderness Lab's second annual DevCamp, DevCamp 2021. I am Brian Kosnich. I'm co-founder and CEO Wilderness Labs, and I am joined by a host of team members from Wilderness Labs, and we're super excited to bring this to you today. We've got a big show in store and a lot of announcements, a lot of fun stuff to talk about. And I'm really excited to have you on and listening. And let's take it away. All right. Thank you very much, Adrian. So DevCamp 2021. And this year's theme will be production IoT. And we will be looking at production IoT through the lens of our IoT accelerator, Klima. This is our first IoT reference kit, and we'll dive into what this means a little bit later. But it is available for pre-order today in our store, and is an awesome climate monitor and does a lot of things that Pro IoT does. Really excited to have this to look at various aspects of the Meadow platform via Klima. But first, I want to talk a little bit about the story of Wilderness Labs, because we were formed almost exactly 5 years ago, and we set out to, hardware is this place where things can be really challenging to build. And there was some fun stuff in the market. There was NetDuino. There was the micro framework, which has been renamed to Nano framework, and .NET was doing some interesting things, but it wasn't quite ready for prime time. It didn't quite do what we wanted it to do. We wanted a real modern experience of .NET on hardware. And so we set out to change that. In fact, our mission is to make building hardware as easy as mobile or web development. And for those of you who had been building hardware, you know that that wasn't really the case. And we launched a Kickstarter. I think it was 3 years ago now today, but time flies. And thanks to you folks, we blew it out of the water. We 5x'd our goal, and you helped bring Meadow to life. Month after the Kickstarter, we released our first early beta, and it was very early. For those of you that were on it, you remember that. Deployment time took a long. Deployment was onerous, and hardly anything worked. But we had a start. We had mono on a microcontroller, and that was where it all began. And since then, we've really expanded and made a lot of progress on Meadow, which is now really a fantastic offering. And at the heart of it, for those that are unaware, Meadow runs full .NET on real embedded devices, on microcontrollers. And today it runs full .NET Standard 2.1, and we're in the process of moving that over to .NET 6, which will come out, which will port to this next year. It's got a really fantastic security story. A heavy security posture is a big part of our platform. And of course, it's designed to be managed out in the field. So as you build IoT and you deploy them by the thousands or hundreds of thousands, Meadow's this platform for you, because it enables you to manage those devices and update them and get information from them while they're out in the field. And so you can rest assured that your devices are not, that they're connected and alive. And really what this is production grade IoT. This is enterprise IoT for every developer, and ultimately it is just a better way to build hardware. Now, if we look at the Meadow stack as a whole, we see here at the base of it is Meadow OS, and Meadow OS is built around NutX's kernel. It's a micro real-time operating system that is a battle-tested kernel. It's POSIX compatible, so it looks like Linux, but it runs on embedded devices. And I think NutX is 19, 20 years old right now, and it is battle tested. It is a beautiful piece of engineering. And then on top of that, we have just absolutely gorgeous hardware APIs so that you have full access to the hardware, where .NET runtime, and some stuff on top, which we're going to talk about in a moment. The OS itself really feels like a modern, almost like a web OS, or like almost like a mobile OS on hardware. So full networking stack with Wi-Fi and Ethernet, full SSL, which is, for those of you who are doing hardware elsewhere, that's a big deal. It's a big deal to have full SSL on a microcontroller. And of course, we've got a full Bluetooth low energy stack. We've recently added SQLite, so you can do local database access and data persistence, and even through SQLite.net, the ORM that we all use and love. Of course, there's a watchdog timer, so if the device crashes and it doesn't pet the dog, it will automatically reset. And then there's a fantastic persistent file system with strongly named directories and protocols to make sure that your data stays on the device through app updates, through OS updates. And so it really is its own OS. It's an OS in its own right. And there is really no tool chain set up to get started with Meadow today. We support VS Code or Visual Studio in both Windows or Mac, and it's easy. And getting started is as easy as doing .NET New Meadow. And of course, Meadow Foundation, and this is really a pride and joy of us. Meadow Foundation is this massive open source library of peripheral drivers and industrial control algorithms and libraries to make hardware plug and play. So we have all these really beautiful hardware APIs, and then we have Meadow Foundation so you don't have to use them. So you can use hardware off the shelf. They have an API ready to go, and you can really build hardware in a plug and play way. And of course, our hardware, beautiful Meadow hardware modules. We have both a developer module for developing and for low run prototyping. We're going out to productizing up to 1,000 units. We've got a really fantastic piece of hardware there. It's got battery charging. It's got all the RAM and storage you want, BLE, Wi-Fi, and of course, now we have our F7 core compute module, which is this tiny little thing. And that's so you can go from low run production to high volume on the same hardware and the same code. So it really makes it easy. And while we've been doing this, in the meantime, IoT itself, embedded hardware, has gone really mainstream. And in fact, a revolution is in progress today. We went from this idea back in I think Bill Gates said this back in the 80s. He had this vision to put a computer on every desk and in every home. And we've gone from that to being able to put compute in nearly everything, everywhere, through the magic of modern microcontrollers. And the microcontroller, fun fact, the microcontroller on the Wilderness Labs board today has got the power about of a Pentium, plus a whole bunch of hardware and peripherals that the Pentium never even could have imagined having. So this is really, we've had a real revolution in hardware itself. And that was a gift from the mobile revolution, which brought us really amazing hardware. And now we really can put computing at the edge in just about everything. And in fact, this has spurred on this revolution in which now today, embedded computing is the new thing. That is the new epoch. We went from mainframe computing and then desktop computing and the web hit, and everything was about web, and web turned into cloud, and mobile hit at the same time. And for the last 10 years, all we talked about really was mobile, mobile, mobile. Well, the next 10 years is really all about hardware, about embedded computing. And in fact, today, IoT is so big, it's already 3 times the size of mobile. And in just a few years, there will be 10 times as many non-mobile connected devices on the planet as human beings. So for every human on the planet, there will be 10 connected IoT devices, which is just almost too much to imagine. And in fact, nearly everyone today now is building IoT. If you look at companies of any of nearly any size now, folks are building and are going after IoT solutions and doing interesting things in the IoT market. And what that means to us as developers is that our skills as hardware engineers and embedded developers have really just shot through the roof in terms of demand. And while there's really a high demand overall for technology workers, that will at some point, that demand will sort of normalize and shrink back. But for the next 10, 15 years, that will not happen for embedded developers. Embedded developers will be in massive demand for the near future, the time being. And that is important because that directly affects our pocketbooks, which means that there's no better time than right now to skill up, to learn embedded development, to get your hardware on, and to embrace that market change. And what's interesting here is that if we look at the IoT market as a whole, we see that this is kind of a quiet revolution, because the hero experience that we see, the IoT that we generally interact with, smart thermostats and smart ovens and things like that, that is just absolutely the tip of the iceberg. That's consumer IoT. And in fact, the market itself, 90% of that is below water. That is commercial and industrial solutions where IoT is really making a huge difference every day in transportation and logistics and ag tech and retail. IoT is really changing the game there. And like I said, this is a revolution in quiet, because unlike the mobile revolution, where the hero experience was something that every one of us had in our hand, a mobile phone. And I remember when Steve Jobs got up and showed his iPhone off for the first time, and it was this beautiful piece of cinematic glass. That's not happening in IoT, because we don't actually get to see this revolution on a daily basis, but it is still absolutely happening, and it's very massive. And in fact, if we look at some of the solutions today that are being built with Meadow, our customers reflect exactly that. Just over across on the other side of Portland in Washington County, they're using Meadow they're building a solution to use Meadow to optimize water treatment, to reduce time and increase capacity. Over in the UK, we've got a customer building an energy meter that is designed at reducing energy usage and preventing failures in industrial equipment. And we've got a customer building CO2 monitoring systems so that we can all go back into public spaces in a safe way again. And even myself in my own backyard, I've been building a smart beehive in partnership with Portland urban beekeepers and Oregon State University to help to learn about and prevent colony collapse disorder, because we're losing our bees. IoT is really changing the world today. So that's all well and awesome. What's going on with Wilderness Labs next? Well, I've got some interesting and fun announcements today. First up, announcing Meadow Beta 6.0, and this just came out. And Meadow Beta 6.0 was a big release for us. And first of all, probably the biggest feature from this, the most long-awaited feature, full debugging on Meadow hardware. And this is debugging in both Visual Studio for Windows, Visual Studio for Mac, and VS Code. And here to show this off is Adrian Stevens, everyone's favorite Canadian. And take it away, Adrian.
Thank you very much, Brian. So yes, do a quick demo of debugging on Meadow. So here I've got Visual Studio Pro running on Windows, and I've got a Meadow application. This is a familiar one. This is Blinky. This is the file new experience, and we can see that our light is running. But really exciting, we are debugging. So we get all those amazing features you get from the modern debugging experience. I'm going to add a breakpoint in my cycle colors method. And we're going to see it come on through. And look at that. We've hit the breakpoint. We can do all the wonderful things we expect to be able to do, like inspect values. We can, of course, step through. We can also step into methods. Let's do that here. I'm going to step into the show color method. I'll step into the show color method here. There we go. Keyboard commands. in. It's worth it. Okay, so notice here. So I'm going to step over the start pulse method. Light goes on. We're going to sleep for a second. It pulses. Light goes off. Again, full modern debugging experience. And of course, this is really great just for learning how to use Meadow. I love this example here. Here's the device object. This is the object that represents the Meadow board, Meadow hardware. It can zoom in. You can interrogate the properties. You can check the version numbers. And again, it's a really, really amazing way to deeply interrogate. Well, you guys know how to debug. You know the power of debugging. We have it on Meadow, a fantastic experience. And back to you, Brian.
Thank you very much, Adrian. Thanks for that demo. I'm really excited for this. You know, we've been using console.writeline for a while, and console.writeline is fine if that's all you have. That's better than nothing. But man, it is really an experience to look at the hardware under a microscope while it's actually running. And I'm really excited about this. This was a feature long time in coming. And also hats off to the community. This was a mix of internal and community contributions on this. So thank you everyone involved. It was very cool. Next up in the beta 6.0 release feature pipeline is full device configuration at build time via YAML files. This is very exciting. Now, at build time, you can specify things like your device name, which is how it appears on the network, and then also your network configuration, including automatic network hot start. So at build time now, you can deploy your Wi-Fi credentials. Those get sucked up as soon as the app boots up. They get put in secure storage on the ESP32 coprocessor. The file gets removed, so the secrets are gone, and we can automatically go out to the network, get time from network servers, and automatically set the device time. And of course, there's other network settings as well in that configuration. And so I'm really excited about this. This really increases the overall boot time of Meadow because the coprocessor will start getting spun up and connecting to the network while the main processor is also booting up, and your application is starting to run. We also have huge upgrades to Test Suite. And for those of you who are unfamiliar with Test Suite is pretty awesome. It allows you to run XUnit-like tests on Meadow hardware. And with the latest version of Test Suite, it's now fully CI-able. You can fully bake it into your CI/CD pipeline, which means that as you're building production hardware, you can make sure that all of your tests, as you build new code, as you check in new code, you can automatically deploy tests to your device, have them run every time you build, and make sure that everything is working great. So you can make sure that your production IoT application is stable and have good test coverage. Now, the way this works is that you've got the tests run on the device, and we've got a host coordinator which will push the new tests down to the device. The device has a RESTful API for those tests, and you can talk to those directly, or you can use either the Test Suite CLI. We now have a full CLI for this, or the SDK to talk to that device and execute tests, get test run, get the validation back from those tests, whether or not they passed. And like I said, you can either run that from CLI if you're integrating into your CI/CD pipeline, or you can use the SDK as a library and call them directly programmatically. So you could write your own interfaces. You could write like a Maui app, for example, that coordinates and runs these tests. So that's really exciting. Test Suite is really awesome. We're integrating that into our own CI/CD pipeline, so that when we do new Meadow OS builds and we add new features, and we run regression tests and we make sure that Meadow is stable. And along with that, we actually did some big upgrades to Maple Server. And Maple Server is our ultra lightweight RESTful web API server. and we upgraded routing. So now Maple has full routing privileges. It looks a lot like routing in ASP.NET Core. You can see the code there. We did that actually as part of our Maple server upgrades, and now part of our test suite upgrades. And now Maple server is really a first-class web API endpoint server, but still very light, very awesome. So also excited about that. Now on the hardware front, we have some exciting announcements. I'm super stoked to be able to announce this. First, our Meadow F7 V2s will be back in stock this next week and shipping. So I know a lot of you are waiting for, you pre-ordered, you're waiting for the new F7 V2 board, and that will be going out next week. I can't wait to get those into your hands. And all of the Meadow hardware designs have been open sourced. So you can now go and see exactly how those are built and get schematics for those designs and use them in ways even that aren't, you can now use our hardware without Meadow OS. If you want to do MicroPython or whatever, you can do that because all those designs are open source. Or if you want to run embedded C on those devices, and all the JTAG information is there and whatnot. So I'm really excited about that. And on the open source front, we all come from open source backgrounds, and our goal is to open source as much of Meadow as we can, and still have a business, still be able to develop on Meadow and have a sustainable business. And I'm really excited. There's some more announcements here coming up around that later on in the deck, and then also on our core compute core compute news front. This is our production module. It adds Ethernet, adds SD card. And as I mentioned before, it's really for high volume production. It's very, very small. It's about the size of a US quarter or a Canadian loonie. It's very, very tiny. And it will be available first quarter next year. So coming up very, very soon. And we've locked down pricing. You'll be able to get the core compute module as low as $30 at scale. So very excited about that. And the star of the show, our IoT accelerator, our first reference IoT kit, Klima, is now available for pre-order. Klima is just really a fantastic piece of IoT. We ran a developer survey, as we do every year, and this year we had an interesting learning. Almost 15% of you that wrote in and said you were building some sort of IoT, you were building a climate monitoring station, which was pretty funny because we were also building a climate monitoring station internally as a reference kit. Now, Klima is really awesome because it is the quintessential piece of IoT. It is battery and solar powered, meant to be living in the environment. It monitors your weather, temp, pressure, humidity, as well as air quality and Vox in the air, and also solar intensity via the solar panel. And then it takes that data, it wakes up, it takes those readings, and then it takes that data, pushes it up to the cloud, synchronizes with your favorite service, in our case, Open Weather Maps. And then it also has a BLE server on there, which enables you to connect to a companion Xamarin app, which we have built. So you can pull up your Xamarin app and connect and talk to the Meadow to the Klima device via this app, and everything is open source, and including the hardware schematics, the enclosure source, as well as STLs to print your own enclosure. The Meadow app and the Xamarin app, all of that are up in our Klima repo and ready for you to take a look at. And of course, you can pre-order yours today, and we'll be shipping those first units out in December. Make sure, if you want one of these, you better get in line. You better get in line now, because I guarantee we will sell out of the first batch very soon. In fact, we've been moving a lot of these, and I really do expect these to sell out. So if you want to get your hands on a Klima, go over to store.wildernesslabs.co and get in line. Now, that's all awesome. Really, really great, really fun announcements around what we've got out there today. I want to take a few minutes and just talk about what we've got going on that are going to, new things that are coming out soon. So first up, we've been making progress on Meadow Cloud. Meadow Cloud is our offering to be able to manage those devices out in the field. This is where OTA, over-the-air updates, are happening through. That's where security updates get pushed through. If you're deploying out to hundreds of thousands of devices, fleet management being able to send out updates to some of those devices and do rollbacks, etc. That's all handled through Meadow Cloud, and of course, we'll also be shipping a feature for push messaging and MQTT, so you can reliably send a message to your device, or you can send an MQTT message directly. And then, of course, features for identity management. Make sure that your device has a private public key, that it has identity, and even being able to provision your app on modules directly from the factory. So if you're going out to production of thousands of devices and you want to get modules from the factory, already have your apps loaded in your configuration, that's also handled through Meadow Cloud. And of course, we're also working on automated crash reporting and logging, and we're really excited about this. And today, and also, I want to talk a little bit about the security stack of Meadow, which we're getting ready to release. So with Meadow, your devices can be in either in developer mode or production mode. And when you switch your device over into production mode, it's really a provisioning in which your private public key pair is created. Your private key on the device is stored securely so that it can't be accessed, but you can run things through it. You can encrypt and decrypt. And then also secure boot. So the ability to make sure that when you're deploying an application to the device, it's signed with your key. And everything on the device, all storage is encrypted. This is very similar, in fact, almost the exact same feature that you may be familiar with Azure RTOS's security updates. The idea there that you can't sideload an application. This really looks like the iOS App Store, in which as a developer, you sign your application, you upload it to the cloud, and then it sends a push message to the device. The device says, oh, I have an update. Let's go download it. Let's reflash, reboot, and now we're running the new stuff. And that's part of OTA updates. We also have a number of trusted platform features on the device, including hardware crypto, true random number generation, and as I mentioned before, full SSL built in. And in this vein, I am really excited to welcome Alexi Christoforides, our head of Meadow OS, to come on and give us a early preview demo of OTA in action. Now, Alexi's going to show us how this is working today and give us a little demo of it happening. So welcome, Alexi. Really excited for this demo.
Thanks, Brian. Alexis here. I am part of the Meadow OS team, and the team has been working very hard to bring you full stack software updates for the Meadow device. Both the OS and the app will be updatable in 1.0. And we've been working on several components to make that work from OS to app. And I'm here to show you a little bit of that functionality. So we have a Meadow hooked in, and I'm just a Meadow developer who has our Blinky V1 project. If you have developed on Meadow, you're familiar with this. It's like the default new project template for the Meadow. So we have a few nice colors that we are blinking on the device, and we're gonna deploy this. However, we have recently developed a much fancier version 2 of Blinky that is using these Wilderness Labs colors instead of the default colors. And we would love to get that update on the device. So we're going to observe the app having been pushed on the device, the version 1. Restarting with version 1. I like to work on terminal, but most of you know that we can you can use extensions for checking the output and deploying. As you can see, we have the old colors going on right now. And as soon as the device connects to the Wi-Fi network that we have here, it's going to pull a sample update that I have set up in a little local web server.
And while we're doing that, one thing you folks might notice, Alexi's working and deploying on Linux. So full Linux support for Meadow development, which is pretty fun.
Yeah, I would like to mention that anyone who is comfortable working in Linux or working on CLI, you do not have to use the you do not have to use extensions. If you want to just use VI, you want to use your own editor. Meadow has a very good interfaces on the terminal. As you can see, the update was downloaded. We had it pulled from device. The Meadow is resetting. And now it's blinking the much fancier colors of Blinky V2. And that's a short demo of our app updates coming to you soon. Thanks, Brian. Back to you.
Thank you very much, Alexi. That's really exciting. Seeing Meadow update over the air is a big step forward for us in Meadow Cloud, and also a big step forward for you folks being able to put devices out into production, because it's not really IoT if you can't maintain them in the field. And so I'm really excited to get a OTA shipped shipped out soon to you, and we'll ship it in stages so you can play with it and give it a test and help us stabilize it. It's very, very cool feature. Awesome. Well, some pretty cool announcements so far. A lot of really cool stuff that we've been working on. We got really great dev velocity. And I've got one more thing to show you today, something that I'm really excited about, something that's very, very huge. I want to introduce Meadow for Linux. Now, what this is a way to run and get all of the awesome Meadow Core APIs on Raspberry Pi, on Jetson Nano, other single board computers. We're bringing those Meadow APIs to that space. And what that means is that with those Meadow Core APIs, you also get access to the full catalog of Meadow Foundation. So you can run the same code on a microcontroller via our Meadow microcontroller modules as a Raspberry Pi, as a Jetson Nano, which is really, really fantastic. And Chris Tackey has done a ton of work to make this really easy with one-touch OS deployment so that you get everything that you need on a Raspberry Pi to run Meadow out of the box. And like some of our other stuff, this is fully open source. And in fact, we'd love community contributions here. We'd love for you to join us and hack on this and, help us improve this. And we've got Chris Tackey joining us to give us a demo, and he will also be giving us a session this afternoon, and a little deeper dive into Meadow Linux. So, Mr. Tackey, thank you, and take it away.
Thanks, Brian. As Alexi had shown, we support Linux for doing your development, but we also support Linux as a target now. So this started as a skunkworks project that I was working on probably about a year ago. And we've got a much more in-depth session on this later today. But just as a highlight, you can see here we've got standard old Meadow app class. If you've been working with Meadow, you're already familiar with this. You've got an app base class, and it takes in a type. Typically, it would be the F7 micro here, but now we take in Meadow for Linux, and then it takes in a type parameter that is a pinout for your hardware, because our different target hardwares may have different pinouts. Once you've done this, everything else is very familiar. You get your device property. We create our I2C bus from that device. We can use a BME 280, which is a device driver that comes out of Meadow Foundation, pass in the bus. Then we're going to call start monitoring on that. Start monitoring simply reads from the BME. The BME is the same thing that is being used on Klima, provides us temperature, humidity, atmospheric pressure. So we're going to write that to the console once a second and loop. Now, if we take a look at this under Linux, I'm SSH'd into a Raspberry Pi sitting on my desk that has this BME 280 wired to it. For those who want proof, here we go. It is running Linux. And because we're running on Linux, even more fun than just running in the OS, we can actually run this inside of a container on Linux. So let me pull up and look at all of the containers that are running. Nothing is currently running on this device. I can now run from our Wilderness Labs Docker Hub repo a BME 280 sample. This is publicly available. Launch it. And you can see inside the container, it is now pulling from hardware that is connected to the device all of these conditions. You can see the Docker container launched, and it ran .NET app.dll, which is our Meadow application inside the OS. As I said, we've got a more full session later on today, but this is really exciting, really fun stuff, and it's going to unlock a whole ton of things. All of these Meadow Foundation drivers you can now use on a Raspberry Pi, Raspberry Pi 02, Jetson Nano, and even other devices. I'm looking forward to seeing what people do with this. Back to you, Brian.
Very awesome. Thanks, Chris. That's so cool to see. You know, this really, what this does is this unlocks Meadow to run anywhere on anything, right? So when we set out to do this, every single hardware API we looked at, we sat down and we said, okay, this is how it works today in the world, but is this really the way that it should work? What is a better way? And we have, 20 plus years of .NET, of fundamental changes to the way that we develop and program in the world via .NET. And we took those learnings and we took all the modern pieces of .NET, all of the new fancy stuff that we can do in C# and F#, and we looked at that stuff and we said, how do we approach hardware APIs in a way that is 100% modern, right? Serial port, for example, works a certain way because some engineer back in 1972 who was working on hardware said, "Oh, I'm going to write this little API because I just need to expose this hardware," right? That's not necessarily the way that serial port should work. It's not necessarily the way that serial port is easy, to use. So we sat down and we really took a fine-tooth comb to all of those, and we questioned, why is this working this way today? Is this the best API? And we really, when I say that we built beautiful hardware APIs, we really do. They are groundbreaking. And now you can take those APIs and you can use them anywhere. And that's really a fantastic step forward for hardware technology, for hardware development. And Meadow Linux is fully open source today, and we'll be open sourcing our contracts and units and all the things that are the underpinnings of that, all of the interfaces and things very soon as well, so that you can see the entire stack is completely open source for you, and you can use that anywhere. And this is really an upgrade to some of the other APIs out there around .NET and hardware. You compare these two frameworks, and you'll see this is really a much more streamlined, much better way to build hardware. So I'm really excited about that. Really excited to have that out. Now, I also have one more thing, and this is also a very exciting thing. This is something that's near and dear to my heart, and it is called Chloroplast. And this comes out of years of working on documentation and publishing documentation and really wanting a better way to take markdown files, to take XML API documentation, and to be able to publish them in an easy way and have a workflow that's really friendly to folks who are writing documentation, who are creating content, and also pushing that out to the web. And so I'd like to introduce Chloroplast. Now, Chloroplast, for those that are unfamiliar, are organelles within plants that take the light from the sun and use that to combine CO2 and water, split off the oxygen, and make sugar. And this is really a metaphor for what chloroplast does, because chloroplast is used to take raw content and transform that into output that can be used elsewhere. It is very much like Jekyll, but built in .NET. It's got a full .NET backend, and it'll take Markdown and XML API files and output them as HTML. So this is really a fantastic solution to creating websites from content, from documentation. And it's pretty awesome. You hit the button and it'll output some static HTML, or you can run that as a self-hosted ASP.NET site. So you have full ASP.NET engine if you need to. So you can put in authentication, you can put in all the things that you want. You can make this dynamic site and still have all the loveliness of our templating engine and stuff. And it is fully Blazor, and the templates are they're so great, because you can stack your templates all the way down. They can be Markdown, they can be Blazor, they can be integrated. And this really is something that we're using this for our upcoming doc site. We've been doc fooding this and building this so that we can have a first class, modern documentation site, and also fully open source. And so I'd like to introduce and bring to the stage my co-founder and best friend, Brian Kim, to show us off some chloroplast.
Hey, everyone. Thanks. Glad to be here. Like I said, Brian said I'm Brian. Nice to meet you all. First thing you got to do to get chloroplast running is you got to install it. So if you come to the NuGet site, you can get the command there. You get that running. All right, and next thing you need to do to get the demo or the sample running is to clone the chloroplast repo, and inside there we have a sample site. So we go in there, and then it says simple as running chloroplast build. Awesome ASCII art there. So we're building the content, and now if we run host, we got it running. So you can see we got a basic sample site running here. This is the command line interface page. On the left, I have the source up, so you can see that it's similar to Jekyll, as Brian mentioned. We got a YAML header, we got some Markdown that's been rendered to HTML there. If we check out the site config, it's pretty basic. I've got title, email, description, and some pointers to different areas in the file system that need to be there to get the site running. And to look at the templating, it is fully Razor enabled, so you can use your favorite templating there. And that's it. So that's all you need to get it running. It's super lightweight and easy to use. So we're really excited about this. And back to you, Brian. Thanks.
Thank you very much, BK. Yeah, I'm really stoked about that. We went kind of fast through there, but like I said, this is fully Blazor templates. This is a really, really great way to build websites, and it's very similar to, like I said, Jekyll, which runs in GitHub Pages, and we'd love to actually get that into GitHub at some point as well, because this is just a really fantastic way to build content. And this came out of 15 years of experience in building documentation and being frustrated by the lack of good documentation tools in .NET and the lack of a good static site generator. And so I'm really excited about this. This isn't a Meadow specific feature at all. This is really a gift from Wilderness Labs to the .NET community, which we are a part of, which we've been a part of for many, many years. And I'm just really, I'm really excited to give this to the community. So I hope that you will all check it out and give it a shot and give it a try, and help us develop it. It's still early in its development. It's incredibly powerful today. The API doc stuff are still in kind of an alpha phase, but the main markdown to HTML stuff is pretty stable and very rad. It's cool to see. It's cool to use like Blazor templates to process markdown files. It's so incredibly powerful. And as you get to start to play with the templating and whatnot, you'll see what I'm talking about there. So thank you, BK, for that demo. This is really a big dev camp for us. Just running through the announcements today. A lot of stuff we talked about, full debugging support in all our IDEs, YAML configurations with network, hot start, very cool, test suite, and Maple server upgrades. It's a real big lift in Meadow Foundation. And of course, we open sourced all of our hardware and announced our core compute pricing, and Klima IoT pre-orders are open. So definitely get in line there if you want one of those. And we saw an awesome OTA update demo from Alexi. Thank you for that. And then also we talked about our security stack, which, putting Meadow into production mode, which will be shipping very soon. And one of the coolest things that I think that we've ever announced since the beginning, Meadow for Linux. So you can really bring those Meadow APIs and Meadow platform everywhere. So you don't have to use some of the other stuff that's out there. You really get best in class, the absolutely best in industry APIs for hardware, and get that in a completely open source way. And then, of course, our gift to all of our friends in the .NET community, Chloroplast, and everyone doing documentation out there. I think that you're going to love that. So thank you very much. Enjoy DevCamp 2021. We've got a lot of really awesome sessions today. And I will be back on this afternoon at 3:30 Pacific time to do a live Q&A. This is also live, by the way. We're live television, as we like to say. And up next, we have Jorge Ramirez doing Meadow from start to awesome. So thank you very much, and take it away, Jorge. I think you're muted, Jorge.
All right. It always happens, in the remote work live. Thank you, Brian. Hi, everybody. My name is Jorge. I'm a content developer and developer advocate for Wilderness Labs. And I want to show you, I want to kick off the session on Meadow from start to awesome. So this session is ideal for people who are wanting to, they don't know much about Meadow. What does it look like when you're developing, when you're going to start working on Meadow, getting on IoT, getting your hands on a board. So I have structured the session in these 5 big points that most people would want to work on Meadow. So the first big thing happening here is coding on C#, F#, Visual Basic. We all have support of all these languages using .NET. So basically, when you get your board right out of the box, you're able to already start using these applications. So let me share my screen here. Let me share my board. I'm gonna bring up my camera. I want to show you my board. I have a little setup here. Cam. Here you go. Okay, here's my Droid Cam. And this is what you will be getting when you have your first hands-on on using Meadow. This is the dev kit. It comes with a breadboard and a prototyping board and this fancy wooden board here, so you can have all your setup ready to go. And the only thing basically that you'll need to use when to use Meadow and deploy is basically go to the extensions and just go into the gallery and look for for VS Tools for Meadow. And that's basically what you would need to get started on deploying .NET applications. So basically, why do we need this extension? Basically, it'll give you access to all the different project templates for making .NET Meadow applications. So if I create a new project, I search for Meadow, and I can show you here that we have support for Meadow applications in C#, F#, and Visual Basic. And you can also create Meadow libraries, which is basically like a little repository of files that you can use as a library for creating drivers, which is something that we use all the time, especially for Meadow Foundation, which we'll talk a little bit later on. And so, yeah, the moment that you create an application, you'll be greeted with this sandbox app that has already access to using the RGB LED on board, which is this little LED that is right here. And it can already tell you how the paradigm of how using Meadow is basically using this initialize method. Is basically what we're telling is when you're connecting your peripherals to Meadow, you have to specify on which pins these peripherals are connected in order to create some object of these peripherals, and then we can use them later on in the code. So I'm going to go and I'm going to show you something a little more exciting this time. So I have this application. It's a accelerometer sensor with some directional LEDs. And I want to show you real fast. Yes, so the application for this is basically we have 4 sets of LEDs. And again, the initialize method right here, we specify on which pins are connected, which are these blue lines here. And we have the MPU 6050, which is our accelerometer sensor right here. And basically, it just needs a simple prototyping communication bus. It's called I2C. So just what we need to do is just pass in the I2C protocol. And we have an event handler whenever the sensor detects movement. And we have our event handler right here. And basically, it'll just keep track of where the sensor is moving, and it'll turn on and off those LEDs. So if I can show you here, if I'm moving them on these directions, you can see how the LEDs are moving. So yeah, that's basically one of the things that I wanted to show you. The other thing we covered already was developing a Visual Studio. And with B6, using debugging, no more console write line. It's something that we've been waiting for a while, and we got it working finally. Modern development practices, everything, all paradigms, design patterns, everything that you've learned and love about working with .NET and mobile and either Xamarin or .NET, WinForms. You can also do all these design patterns into Meadow. You don't have to learn any new things. It's everything just going to be really familiar. And another big thing is the feature packed hardware that the board already comes with. And the what I'm referring to specifically is having Bluetooth and Wi-Fi capabilities right from the get-go. So this will allow us to actually have the eye on OT, so you can connect to your internet, you can send login information to the cloud, to Azure or whatever service you have, the Amazon cloud. And also, if you are in remote places, you don't have access to the internet, you at least have Bluetooth, so you can go over with your phone, and you can just pair your device. You can start gathering data that way without being reliant to have Wi-Fi around. Another example I wanted to show you is, and this one's really cool. This one's I've been working for a while, and I wanted to show it on Hackster, but I want to show it here as well. And this is my little rover, and this is a 3D print board that I made with and that I printed for PLA. And this has already it's an H-bridge sensor, an H-bridge motor controller. These already comes in the hack kit. So basically, all this with a hack kit, you can build it yourself. And I want to show you this working with my little app here. Let me show. I'll show you my screen of my board. But here's a controller, and you can see right from the start, it's already paired up. So if I can start moving, there you go. Let me make the camera a little bit bigger. And this was really simple to make. I'll have a session later on to show you in more detail how to work with Bluetooth, specifically for Klima. But basically, you can also tweak, or you can apply the same pattern of using Bluetooth to any other of your IoT solutions that you're working on. In this case, I have the rover working, and so yeah, that's something that I think it's really relevant to have Bluetooth and Wi-Fi on board. No longer need to have any shields to do that, and a massive driver library. So we I already showed you how to create these peripherals very easily using here Meadow applications, but there's something called Meadow Foundations that we'll talk a little bit later. But it's basically a platform or a massive library of drivers that are available to you from the start. So if we go to the peripheral drivers, you can see all the different peripherals that you can just download, add it into your app, instantiate them, tell them to which pins are connected to your Meadow board, and you already has an APIs right out of the gate, so you can start working with these sensors without fiddling with data sheets and all that. So that's basically what I wanted to show you for the getting started from start to awesome. Adrian, back to you. If you have any questions, feel free to drop them in the chat.
Jorge, that was fantastic. And I love that you did all of that live too. That's either arrogance or pure bravery. That was beautiful. Really excited.
Thank you.
That. Thank you so much. So Jorge is going to come back in a few minutes to talk more about all kinds of things on Meadow Foundation. But Jorge, I'll give you a little break here for a minute.
Sounds good.
But we're really going to kick things off here. We had the awesome keynote. We're set up. We're ready to use Meadow. And now we're going to get into the star of the show. Clearly, that's me. Of course not. It's Klima. And let's make some space here. And we're going to talk a little bit about Klima here. I'm going to tell you all about the hardware and the software. And then this is really going to be the focus of the next couple of hours. And we're going to dive into a lot of really great capabilities at Meadow. We're going to learn how we can do really amazing things in terms of adding hardware and connectivity and mobile devices, all kinds of coolness, but all centered around the climate station. We heard from you that you want to build climate stations. You want to know how to use this type of hardware. You want to know how to connect hardware IoT to mobile devices or other .NET platforms. Well, we're going to give it to you. So Klima. The Klima is, of course, a climate station. And the obvious part is the physical part here, where we've got a number of sensors, and we've got some great standard things like wind direction and wind speed. We can detect rain as well. And then, of course, the fun part here, this is the brains of the system. We've got our Meadow board mounted to a custom PCB. And this PCB is pretty important. There's a couple of really, really interesting things. So you can see the bottom here has a couple connections, and these are, of course, the connections so we can connect to our physical sensors. And on the other side of the board, there's another sensor. There's a BME 280, and we'll talk a lot about that for the day, but that has some sensors to do things like temperature, of course you want to know that, pressure, and humidity. So we've got a lot of capabilities here, and I'm going to point out something for you that are building your kits at home too. This is backwards. And that's very intentional. So you'll have this flipped around when you build your kit, so the metal will be on the inside. But I wanted you to be able to see this here. So yeah, it's a physical kit. It's powered by Meadow, but it's really more than that because it's an open source hardware and software platform. And I'm going to switch over to my desktop and pull up. I'm going to go to GitHub because this is really the best place to learn all about this. So Wilderness Labs, GitHub repo, and it's just called Clima. Clima is Spanish for climate. And if you go into the repo and scroll down, the README is pretty fantastic. You can see our beautiful hardware setup. And there's actually 2 versions of the hardware for Clima. There is this beautiful Pro kit. And if you order the kit off the Wilderness Labs website, you'll get all this amazing hardware and you'll get everything you need to put this together. There's also a variant that you can build from the hack kit. And this one's kind of fun. So absolutely, it's a simplified version. We talked about that BME 280 in our kit. Well, the hack kit version is going to use an analog temperature sensor. So the sensor capability is a little bit different, but the hack kit version has the bonus. It incorporates a display. And again, these are things we can do we can hack these 2 things together. We can add display to our hack kit Pro version, but it's actually both these versions have different capabilities, and they're both really great opportunities to learn how to build hardware. Which I think leads to a next really important point, that these kits are, of course, extensible. It's open hardware, open source. And so these are meant to be starting points. So they are going to be fully featured, fully working out of the box. We can deploy the source code. We can do amazing things with them. But they're really meant as a kickoff point for you to build the systems you want. So you're going to see examples throughout the day using Clima. Does things like Bluetooth connectivity. Of course, our Meadow boards have Bluetooth capability thanks to our ESP32. Has REST capabilities as well, thanks to the Maple server. We're going to learn more about that. And I want to show just a couple of other really quick things. And then we're going to get to dive right into it and really look at some of the source code with Meadow Foundation. So beautiful here, if you have the hack kit, we've got the full wiring diagram. And you'll notice we don't have a fritzing for the Pro version. And the reason is we don't really need it. All we have to do is plug the Meadow board onto the physical board, onto the PCB, and then your wiring is basically done. But for the hack kit version, this is pretty fantastic. Again, see how to wire up the analog temperature sensor, bring in our display, and again, lots of room to add other sensors or extend. Now, before I move on, let's take a quick look at the source code. So you come to GitHub, actually, I'm going to show you one more thing first before I jump over to Visual Studio. If you go into the repo, I'm going to switch over to the main branch. So you notice we have the source code, of course, but we also have the hardware design and the industrial design. So if we go into industrial design, this is all the STLs and the source for the enclosure. So this one here, this is 3D printed. There's a lid for it as well, which I think is hanging out on the table behind me. There's also a 3D printed bracket in behind it. You probably can't see on camera. And we also have the bill of materials and everything you need. So you can buy this kit through the Wilderness Lab website, but it's all open source. We document every part. We include all the necessary requirements for 3D printing all the materials. You can build this kit from scratch, and I'll just open up the CSV file. Not the prettiest thing to see, but just again, full build materials, all open source, open hardware, open software. Again, meant to be a really fun place to learn IoT and do some hacking. If we go over to the project, here I've got this open in Visual Studio Pro on Windows. This will, of course, work beautifully on VS for Mac, or you can even open it in your favorite new lightweight editor, Visual Studio Code. And you'll see several projects. So I'm going to spend some time today in the Clima. I'm going to zoom in here. In the Clima Meadow Pro project. So this is the source code that's designed to run on this hardware here. Right above it is the Meadow Hack Kit project. And that is meant to work on that hack kit version. I've got the hardware here. You'll see that more later today as well. There's a few other fun ones. There's a mini server, and that can be used to do basic communication from Meadow to a local running server. Again, a really great starting point. And then up above, this is a ton of fun. There's a full Xamarin client application, and that's going to be used to talk to your Meadow, your Clima build over BLE or via the Maple. So again, you will spend lots of time here, but again, you've got a lot of source code, everything you need to get going. And I'll just show you right here in the bottom left-hand corner. This is in fact running and actively reading data right now. And if we give it a spin, we might even be able to see some new sensor data coming in from the wind direction and the wind speed. So Jorge, if you are ready, I'm going to bring you back in. And Jorge, anything you want to add to our introduction to Klima before we switch over to talking about Meadow Foundation?
Awesome. Yeah, no, it's a great, as you mentioned, it's a great reference or foundational project for everybody to use and get to learn how to do industrialized IoT grade projects using Meadow. It's really good. Wait until we get over-the-air updates, so you can have your Klima already sitting on your backyard, and they're like, oh, there's something new that I want to change, a data structure model, change a table on your database. You'll just write the code and you just go to Meadow Cloud and just start sending that update, and without having to go all the way with your computer and connecting it, so yeah, pretty exciting stuff.
That is beautiful. And we're seeing some comments and questions coming in the chat. And yes, I am wearing a Meadow t-shirt. This is a limited run collectible, perhaps. Yeah, this is a lot of fun. So the team was kind enough to send us out some t-shirts, but maybe those will appear in the store. I'm not making promises, but it's a lot of fun. So we'll talk about that. So awesome. Jorge, are you interested in talking a little bit more about Meadow Foundation?
Yes, let's talk about Meadow Foundation now. I'm sure there's people that they want. Am I sharing my screen? Yeah,
I can bring that in for you right now.
Perfect. Yeah. Sir. Okay, thank you. Let me share my screen properly. There we go. Okay, I'm a little bit more prepared this time. All right, so let's talk about Meadow Foundation. For the people who doesn't know what Meadow Foundation is, it's all about building a plug-and-play developing or building experience. It's all about just we want to just try to keep you away from data sheets and of components that you will have to spend time to write your drivers and see which pins they have to go high and low. We want to move you away from that and try to get you more time focused building your solution rather than building the parts that involves to make your solution. So right now I also split this into 5 sections: building plug and play, building experience. Super cool. It's actually what I showed you on my little rotation detector sensor. It'll be just about telling it on which pins you are connected, and you already have a set of APIs ready to go. We have over 100 available peripherals already in the NuGet gallery. Obviously, we don't want to cram all those 100 peripherals in a single library and then try to just use a small percentage of them. So if we go, say, to the NuGet gallery here, and let's see, I can search for Meadow Foundation. There we go. We have 100 exactly packages readily available. You can see you already have almost 27,000 downloads on Meadow Foundation, because Meadow Foundation core comes already with a set of very simple drivers such as LEDs, rotors, rotary encoders, things like that. And then what we want to do is, when we want to add more specialized peripherals, you can just download them separately and add them to your project. So in this case, for the Klima Hackett project, which I have right here, let me switch to Klima solution right here. Let me bring up my little camera. So for the Klima project, we already have a set of NuGet packages installed. So let's go and we see things like we have our Meadow Foundation project, which is the core library for things, again, as like doing basic things like the analog temperature sensor, the push buttons. We have a text display menu. It's something that it's a little library that helps us to interact with the buttons to switch in this case the units of the climate for Celsius and Fahrenheit. We have the TFT-SPI. This is for our displays. So we have the display right here. This is the one that comes in the Hackett, and a simple JPEG decoder. It's again, this is full.net, so you are able to just download almost any NuGet package that is out there, even system.txt.json to serialize just like you would do on any mobile or desktop app, and you can just use it right there on using Meadow. So let me show you here in the Meadow app. We have an initialize method of how to initialize. We have an LED indicator. We pass in the device, in this case, Meadow V1. How Chris Taggy said earlier, paradigm for Meadow app is passing what device are you working with, especially now that we are adding Raspberry Pi into the mix. Is very important, this field here where you're telling, okay, what device am I running this application? In this case, it's an F7 Micro. And then we pass in things like the device to create an LED indicator, which is the onboard LED. And then we have an analog temperature sensor. And here we pass in which pin is connected. Again, we're passing the pin analog 0, which is right here, the blue line here. And Meadow Foundation say, okay, there's many different analog temperature sensors. Which ones are we talking about? In this case, we go back to the Hackett version. The Hackett temperature sensor we have is the LM35. And we have a display controller. So we want to abstract these peripherals into making them like more bite-sized, more and abstract all the logic of them. So display controller has even its own initialize method, and is basically just doing the same thing. It's an ST7789. The display that we have is a 240 by 240 resolution display, and we pass in all the necessary parameters so we can get started talking to it with using Meadow. And another cool thing that we have on Meadow Foundation is graphics library. So graphics library is something that we built in-house, and it's a driver that is display agnostic, meaning that whenever you create an object of a display, regardless of the nature that the display is, when you pass in that object to graphics display, now you can start doing things like drawing shapes, like circles, rectangles, drawing text, drawing images, and you can do all that using graphics. And if you swap your display with another one, you just simply have to specify resolution and what type of display it is, and graphics library will just keep running and just redraw everything based on the new hardware of the display that you're running there. So super exciting stuff. Let's go back here. Unitization, that's a big one. That's something that we also meant to cover in our platform, is using units. We have a lot of sensors out there. We have load cell sensors for weight. We have distance sensors, but we don't want to say things like, oh, values are going to be from 0 to 1 or 0 to 1024. We wanted to actually give meaningful values for the user. And so we make sure that we're all on the same page. Like, are we going to work with Celsius? Are we going to work with Fahrenheit? We're working with Kelvin if it's a temperature sensor in this case. So let me show you a quick glance about how we're working with the units. So after we have our analog temperature sensor here, if we go here and we read the conditions, notice that we're doing a display controller, and we're passing in update the display to update the ambient or the room temperature. So let's go here. Let's go dive to and then here on the render method, this is where I wanted to get and to show you. So we have a Boolean here that says if it's Celsius. We have our conditions, that is the value that is brought up by reading the analog temperature sensor. And we already have Celsius, and already in-house, it's giving you units. So you have Celsius, we have Fahrenheit, we have Kelvin for all the scientists out there. And we'll plan to keep adding more if necessary, or you guys can, all this is all open source. So if you guys want to add a new unit on temperature or any other metric that we want to send, we'd like to hear about it. And so, yeah, that's something that is really big, really important. We also have microservers when we are rotating back and forth. Are we talking about radians? Are we talking about regular degrees? Super, super important. Amazing API docs. This is also really important. We need to, our drivers are always not ready for production if they don't come hand in hand with docs, because it doesn't matter if I release the driver for ST7789, people are not going to know how to use it until they see an example. So if I look for a display, we have the TFT SPI driver here. We have great API docs with already links to the GitHub repo to show you the source code of how the driver was written. We also showed you a link of where the NuGet packages are stored and which ones do you need to use in order to add them to your project. And there's a basic, blurb about what peripherals are we including in this package. Since they're all about the same nature, the TFT SPI drivers, we have a set of other displays here available and ready to use. So if we go to the ST7789, we already have super important usage example. So it shows you right out the gate how are you supposed to use it. And this is now, all these code snippets are on B6. They are going to be fully updated automatically. We automate the way of our code snippet samples to update in every release. So no more about like getting old samples and not being able to run them because they were updated docs. These are copy paste, and you'll get your peripheral or your example running right out the gate. And this has to come, of course, with a fritzing diagram to give you a look of how we're wiring, in this case, the display into your board. So first step, you grab your display, you connect everything, you make sure, double check your connections, and finally run your example here, and you should be good to go and really start tweaking and start getting going on building your .NET up there, .NET Meadow application. And the last point I wanted to give is that all this is open source. So if you go back here, we have, okay, that's not good. GitHub.com labs, and we have our Meadow Foundation repo, where we have all the documentations. We have public contributions for sensors. We have sensors requests, or just peripherals requests of people asking, hey, I got this display. Right now I can't find it. Can somebody work on it? So you'll just create an issue, and we can, or anybody in the public can also take a look, or people can also just bring their inventions of peripherals and add them into our Meadow Foundation repo. So all that is pretty awesome. The last part I want to show you is, as Adrian mentioned, we have the CleanMat kit here. And so in this case, I have the 3D printed enclosure. So when we open it, just as Adrian mentioned, let me zoom up the camera a bit here. There we go. And this is how it'll be all packaged. And notice that the sensor, the BME 280 sensor, is right on board here. And if we take it out, then we have our Meadow board here. In this case is a V2 version, and along with a battery. something that we haven't mentioned actually, it has a battery connector here. So it has a charging circuit, so you can also connect your battery, and we can plug in a solar panel to it. So when you leave it in your backyard, if you have good weather all the time, you'll be able to keep that meadow alive using solar power over the day and using the battery charged overnight. So pretty awesome stuff.
That was fantastic, Jorge. Thank you so much. And I really appreciate you pulling up the hardware as well. It's I like that we've got ours front and center, but it's good for people to see how to properly install it in the enclosure.
For sure. Yeah, I'm working on the manual, so I don't have the fancy one that's assembled to yours. I'm taking pictures and getting the manual ready for when people start getting the hands on their Klima kits. They can just follow the guides and make sure how everything is wired up properly. So.
Yeah, that's beautiful. And I love that you called out the documentation, both for Klima, so everything is fully documented, so no one should feel stuck.
Super important. It's vital. I mean, a lot of people in public Slack, we have a public Slack, by the way, also. People are always there, super awesome, bringing up questions and things like that, and examples. We need examples for these peripherals or not, then we just grab whatever we can find on these API docs and just get them going.
Absolutely beautiful. Now we actually have a couple of questions, so I'm going to pull these up here. And one great question was, do we have more cameras and more camera drivers than the DevCamp? And I'll happy jump in on that, but Jorge, please feel free as well. So yeah, we've got a few camera peripheral drivers in progress. And as Brian mentioned in the chat, there were some capabilities on the platform that need to come before we could fully support cameras. I mean, being able to store those images, those pictures locally is really powerful, really important. So the camera drivers got slightly deprioritized until we had that functioning file system. So that's something that will come next. There's also some questions around requesting a driver and a driver priority. And we don't have an official roadmap for drivers. There are some capabilities that we're still waiting on as well. So there's a few drivers that are very timing sensitive. And so as the platform evolves, as we get AOT on Meadow, you will see more drivers get unblocked and unlocked. And then a lot of it really is community driven. So it's what's commonly out in the market, what contributors are using. And so we highly encourage open source contributions. Again, Meadow Foundation is all open source. So feel free to take a crack at running a driver and submitting a pull request. And Jorge, that reminds me, we should really make sure that we set up a system to give some guidance on offering drivers. But yeah. Oh, please go, jump in.
Yeah, of course. Yeah, so as I was mentioning, we are also keeping track right now that will be the one-way communication of, one of the mediums of communication of people requesting drivers is following up on creating issues on Meadow Foundation, or you can also just ping on some Slack and then we can create it and put it on our to-do list as well. And as also Adrian mentioned, we have some peripherals that are reliant to have ahead of time compilation that we need that our Meadow to be a little bit faster. So things like distance sensors, like the ultrasonic one, it's right now it's not fast enough to be able to handle those peripherals, but it's definitely once we have AOT, we'll be able to use it. However, for distance sensors, we have the time of flight, which is also pretty good. And you just use 2 ports out of your Meadow board. Just use an I2C protocol bus, and you're good to go. You do that.
Yeah, it's been pretty fun to see the progress. Meadow's been getting faster every release. It's still in beta, 0.6, but it's really moving along. And we're going to see some of those performance benefits later on today. Got another question. We've got time here. We've got a couple minutes. So do we have plans to add a sensor to measure solar radiation to Klima?
That is an excellent question. I think, what do you think, Adrian?
The answer is a big yes. And so Brian was kind of jumping on Twitch and answer that. The hardware does support it. And so yes, that will definitely be coming. Absolutely.
Yeah, I think there's also APIs to get the battery levels as well. So if you have a display and you have your Meadow running on a battery, you can even do like a little battery indicator on a corner of your display, and then over time you can just query that battery level, and it'll just show the indicator of when you're running low, it needs to charge or things like that. So pretty cool.
Absolutely. And a few comments. The automizing, the automating of the code snippets. Yeah, that's really nice. And I'll show this here. Nice touch. Keep code snippets the same. And this is actually lead into our next topic. We're going to talk about working with sensors and go into a little more depth. So Jorge, thank you so much. A really fantastic kickoff into Meadow Foundation. And now I'm going to show a lot of what Jorge did, but put it into practice and dive into some of the patterns we use in these peripheral drivers. And it is a nice connection to contributing and adding new drivers. Because some of one of the really beautiful things about Meadow Foundation is the really well thought out API surface. And that one means that it's a consistent API. So we'll see some of the tricks in the source code. I'm gonna actually dig into the source code a little bit to show you how the drivers are put together. And what that lets us do is have consistent patterns. So when you're using a BME 280 or a 680 or another atmospheric sensor, the way you interact with those APIs is consistent. And that means that you're not relearning. You're not learning new APIs every time you switch hardware. And of course, yeah.
What I wanted to say is, what we want you guys to do is, once you learn how to do or use these sensors, you want to get a feel of how the paradigm of how to get these sensors working. So when you switch to one temperature sensor to another, you'll have the same paradigm. Like you can either do using observables, you can do it like in a React mode, React pattern, or you can also simply just do a simple read on a certain time. And well, Adrian, yeah, go ahead and dive into the code. I don't want to keep spoiling your session.
Nope, that is fantastic. Very appreciated. Tiny bit of background noise here too, so I should end quickly. Hopefully it's not coming through. And so yeah, let's dive in. And I'm gonna pull back pretty far actually, because I want to show you some fun things. So I'll get my screen shared. And I want to start on the Wilderness Labs developer website. And you saw this briefly when Jorge talked about it. And Jorge, stick around and please jump in if you like. But I want to talk about how we would go about adding hardware to our builds, and then how we use that in our source code. So the best place to start is the peripherals page on the Wilderness Labs website, developer.wilderness-labs.co. And I'm going to scroll down to our atmospheric sensors. Here we are. And so we're going to talk about the BME 280. That's one of our primary sensors. And of course, that's the sensor that we have on this custom PCB. And Jorge was able to show that to you just a moment ago. Now, typically when you work with sensors, you're doing IoT, you're going to pull up the data sheet. You're going to look at how all the communication protocols. Now, a lot of these are standard, and the BME 280 is a fun one because it uses both SPI or I2C communication protocols. And those are well standardized to a point, and they're well known, but that's the data communication protocol. But the data that the devices expect and the format and the packages that they return, well, that rides on those protocols, on those communication buses. And so those are not always standardized. And so we typically have to learn that, sometimes pulling apart bits and bytes to get the information out we need. And so Meadow Foundation takes care of a ton of that. And so we don't have to worry about the underlying things, but we still have to use this API surface. So there's the API surface that Meadow Foundation presents. And again, we're going to talk a little about that standardization, but I want to show you first here on the documentation page, as Jorge pointed out. So every driver has a code example, and I'm going to start with the BME 280 because I'm going to show you two ways to use this driver. And the first one here is this observable pattern. And actually, I love this code snippet here because you can see there's examples of instantiate as an I2C sensor if you have the I2C version, or instantiate it as an SPI version. And it's actually the I2C version, I believe, on this hardware. So let's talk about the observable pattern. And this is a really powerful pattern. And it's one that as .NET developers, depending on your background, you may not be used to, and you go, oh, this is a little bit complex, but actually it's really cool. And by using this pattern across the entire driver surface, you learn it once and you use it with all the drivers. So we create an observer for this driver. And what that's going to let us do is control how often we get data back and we can do some gatekeeping on what data we get back. For example, we may not want notifications if the data hasn't changed. And this observer patterns can give us full control over that. So first thing first is the handler, and this is the result. And now in the code sample, it's just a console write line. It's just spitting out some data. But this is where you would attach it to the rest of your code. You might store it in a model object. You might pass off to your business logic, your business layer. You know, this is your opportunity to take the data out. But the part that's really interesting, I think, is the filtering. And this gives us the ability to control exactly when we get those notifications of what data we get. So you can see here, in this case, we're actually gatekeeping to make sure that the change is more than 0.5. But, you know, Jorge, since you're here, so 0.5 what? What's that 0.5?
Yeah, exactly. There you go. There's your unitization right there. It's using Celsius. So by the 0.5 Celsius, if it's over, it's gonna start hitting that, you know, hitting that event, and then we'll have a handler about what we're going to do with it. So.
Absolutely, and I love that. And this is a great example. And we'll show you a little more in the code. We'll do a little bit of live coding. But we can, of course, this could be Fahrenheit if that's your preferred measurement. I love that you said Kelvin as well. I have a physics background, so Kelvin is near and dear to me. So yes, we get it in the units that we want. We have a meaningful value here if it's more than half a Celsius change. And in this case, this is a more complex check. So we also add in the humidity. And so this, again, meet your build needs. You do some filtering here, and then only get the notifications. And what we do here is we build the observer, and then we pass it into subscribe method. So we pass in the consumer object or consumer reference into the sensor, and then we subscribe the updated method. And now this is going to give us data back based on what we've set up in the results here in the filter. So pretty fantastic.
Yeah, and I think something
I misspoke. Please jump in, Jorge.
Sorry. Yeah, I think the iObservable pattern is such an amazing feature, especially that we don't need to constantly every second monitor, or in certain situations like in a measure the room temperature. The temperature is not going to change drastically in a minute or two. So putting the application in a low sleeping state and then start measuring every hour, you can do that, and without the need of actually writing the code to do those implementations, you can just use the iObservable and just also say, I want you to trigger an event whenever a certain condition has passed. And so what I see there in your sensor start updating, you can specify how often you want to show, you want to start the application to activate. In this case, we're doing a time span from seconds, 1. In this case, it'll be 1 second. So each second, your board is going to constantly be monitoring the temperature of whatever you're measuring. So yeah, pretty cool.
Fantastic. Thank you very much. So now let's look at another way of using the sensor, and let's jump into the source code. And we can, of course, use regular .NET events, so we don't have to use this whole filterable observable pattern. And we can also just read values directly from the hardware. And you notice a consistent API surface. So here's our BME 280 instance, and there's a read method. And what's fantastic here, if you look at it, of course, this is an async method. So we can await this. I'm going to come back to this in a moment. I want to show you how we're using it in this project. But I think to fully appreciate how this is all wired up, we almost want to go back and look at the life cycle of the application just a little bit. So I'm going to switch over to our program.cs. I'll be really quick here, but this is the entry point to our Meadow applications. And this is the most important thing we do here is we instantiate Meadow app. Now, if we go into the Meadow app class, this class is really interesting. So if you notice the signature, it derives from this app class, and this app class knows the type of hardware. Saw some conversations earlier about V1 and V2 boards and life cycles. And to the best of my knowledge, both boards, there's no plans on deprecating either one. The V2 is brand new, of course, and the V1 we supported for a long time. And the great thing is here, we can actually change our code very easily to go between the V1 and the V2 hardware. And this is really important because this inheritance here gives us one really important thing, and that's the device class. So let's jump over to where we instantiate our hardware. And we're going to do that here. So if you notice in our class, we have an initialize method. In this case, it goes through and it's doing some hardware initialization, so initializing our onboard LED on our Bluetooth server. But what I want to show you actually is the climate monitor agent. Now, the climate monitor agent is a class we're going to use to get our climate data. And you're going to see this used all throughout the day today. And it controls today 3 peripherals. We have that BME 280, our wind vane, and our animator. That's our wind speed. So if we look at our BME 280, let's see how we instantiate this. And before I talk a little about the I2C bus, so notice this line here, line 71. I'm going to flip my zoom here a little bit. So we instantiate our BME 280, and this is really beautiful seeing the patterns of the APIs. So we're going to use the I2C version, and so we need to pass in an instance of our I2C bus. Now that's a physical thing. That's part of a board. And so these boards, so you hold up on the camera, be a little bit small, but you can see the pinouts here. And of course, it's all documented nicely on the website. But there's very specific pins we have to attach our hardware to in order to communicate over the I2C bus. And now the pins between the V1 and V2 are pretty similar, pretty close, but they're a little bit different. And we might see a V3 or other variants. And we're going to see other hardware form factors in the future. And so we're going to need to know the specific hardware configuration for the hardware we're using. And that's where this device class comes in. So this device class knows the hardware. And so we can create an I2C bus. In this case, we're not passing in any parameters, but there actually is a bus number. And so if we have hardware that supports multiple hardware I2C buses, well, we can configure that. We're using the default 0 for this one. That's the standard pins. And look how beautiful this is, though. There's a lot going on. I just told you a whole bunch of things. If I go device create I2C bus, this is the bus we need now to use I2C on our hardware. All we do is plug in the right pins. We can now communicate with our BME 280 over that I2C bus, except we need one more thing. So I2C is designed to allow us to have multiple things on the same bus. And so the way the devices know when they're being talked to is by an address. And those addresses are built into the hardware, and they're specified by the manufacturer. And some hardware has configurations, so you have more than one address. There's like often a primary and a secondary. So these are things we need to know. This is a known number, and it's just a byte. So of course, what's great here though is the driver knows that it's defined. It's almost self-documenting. So we've actually got a static property here. You can just actually zip over to it. And so those addresses are actually defined as an enum in the class. So you don't have to go chasing through the documentation. You don't have to go chasing through the data sheets. It's part of this class, and this is consistent. Again, going back to that consistent API surface, we learned to do this on one I2C driver. We now know, hey, there's addresses. You'll notice there's a default value in the enum, which ports back to address 0 and 1. In this case, this one is configurable. So we're using that default one today. So again, covering a lot here, but what's beautiful about this is now one line of code. I told you a bunch of complexity, but you can just basically copy paste this. You're good to go. You've now done your hardware configuration for that BME 280, and now you're back to just regular old .NET. So let's go back now where I was showing you where that read method. This is a lot of fun. So again, there's a lot of ways to interact with the hardware, and it's going to depend on your needs for your hardware build. I love that filterable observer pattern. We can use regular old .NET events for hardware that supports it. But in this case here, we're actually going to read the value. We're going to basically ask the device, hey, what's your current state? Now, sometimes those read values are, they take a non-trivial amount of time, and so the read method is async. Now, what we're doing here, this is a lot of fun. So we're actually caching off the task. So the BME task with the var, this is actually a task of type. Actually, we should almost type this out. Let me just see if I can zoom in on this a little bit here. So it's a little bit of a complex object. So notice it's a task of type meadow units. I moved it. Temperature, meadow units, humidity, and meadow units pressure. And so we have a tuple here that's going to come back and give us access to those 3 values. This is why I love the var. This is why I love the C# language. We hide a whole bunch of complexity in that those three little letters. So we now going to have a task that's going to represent this tuple with temperature, humidity, and pressure. And then we can do something similar for our wind vane for our direction. And again, another really great example here where we also want to have it unitized. We want to know what we're getting back. So the wind vane really, well, this is going to be a direction and could be an angle, but we know there's lots of different ways to represent direction and angles, whether it's degrees or radians, or even compass positions. So in this case here now, we take the two tasks, and then I love the C# language. So we want to build a model object that brings all that data together. So in this case here, we're going to call task when all. When both tasks complete, then we're going to instantiate an instance of our climate model object, populate all our properties, and then a fun one here for our wind speed. This is just representing current state of that sensor. So it actually is it's a trivial amount of processing time to get that value out. So we don't have to wait it, we can just grab that. Jorge, pretty cool, right? It's a lot of fun.
Oh yeah, and what I wanted to show, if you go up into the initialize method,
yes,
we have all these three peripherals, and the same thing we're doing. We're just passing the device that we're using, and also the pins. So for the anemometer, we're passing in analog port 1, and there we're specifying the update interval, which in this case is going to be 10 seconds. So every 10 seconds, the anemometer automatically internally in the driver is going to activate. It's going to see what angle the anemometer or the wind speed is, or what speed what speed the wind is flowing into the sensor, and it just updates internally its current last reading. So you can use that on the climate without actually doing just a regular good old async read in this case. So that we have a little bit of a mix there of different flavors, just to spice things up about how to do all these different things. We also have our wind vane there that is basically about the same approach that we're doing for the BME 280. Another thing that I wanted to also mention is our paradigm or our structure for returning these tasks on these sensors. As I mentioned, as we mentioned, there is some sensors that are only returning temperature values, like the analog temperature comes on Meadow, the Hackett or the BMA 280 that is, very ambitious. It has not only temperature, it has humidity and pressure as well. And all that comes condensed into a single object that you can just start accessing to these metrics, and you can start doing the unitized feature, and you'll bring up the values just exactly how you want them.
Well said. Absolutely.
Yeah.
Thank you for that.
Thank you.
I think we're getting close to time here, but I want to just give you a little peek under the hood, just to really enforce the beautiful API surface that Talos has built. Now, a lot of this will look complicated, but we can start to see some of the things we saw under the hood. So here we have our temperature, our humidity, and our pressure values. So we're defining this, but notice we're deriving from a sampling sensor base. And so these sampling sensors, these sensors that are reading data regularly over time, are actually using a common base class, again, nodding to that common API surface. And then, of course, we've got the abstractions here too. So our BME 280, well, it's a temperature sensor. So it derives from temperature sensor. It's a humidity sensor, and it's a pressure sensor. So we derive from these interfaces, and again, we can abstract this out. So we could have a hardware configuration that's using the BME 280. We could swap it into some other hardware that implements these three interfaces and just store the abstract references, or we could even have three different sensors. And we could architect our code in a way that we don't have a hard dependency on our BME 280. We can use all those amazing modern C# patterns that we know and love. And then with these interfaces, you get some great things too. So you're going to get standard events here. So those temperature updated, pressure updated, humidity updated. Again, these come from the interfaces. So we know that we can use the abstraction successfully and bump things back and forth. Any questions before we move on to our next talk?
I don't see anything in the chat, but I think, yeah.
I do see one. This is a good one. Is CAN bus on the roadmap? And yes, it absolutely is. Thank you, Brian, for jumping on that. Yeah, it's on the roadmap. It's not a priority for V1.0, so I'll make sure we get everything fast, stable, and efficient. And of Unfortunately, actually, it's looking pretty good. Notice we've actually been running our sensor data. If you've looked at my screen in the lower left-hand corner, we've actually been running this the entire time. We've been sampling data live.
Super awesome.
It's pretty dry in my office today. Last time I ran this was at 45%.
So as also we were mentioning, this is full .NET that we're talking about. So we are able to just use just about any NuGet package that is out there. So also we're thinking, we are sensing data using Klima, and we can either send this data all over through the cloud directly, but we can also just maybe have some kind of storage solution to just store those, to store that information locally, right? So that blends in perfectly into our next session. Go ahead, Adrian.
Thank you very much. That is fantastic. Yes. So next up, we're gonna show you a little bit about data storage on Meadow, another exciting feature that launched very recently. And again, this type of structured data is gonna be really powerful, both for storing data locally and then making sure we have meaningful data that we can expose via other mechanisms, maybe Bluetooth perhaps. And so with that, let's get that queued up. And I pass you over to Chris to learn about SQLite on Meadow.
Hello, and welcome everyone to DevCamp 2021. My name is Chris Tackey. Today we're going to be talking about using SQLite on the Meadow platform. It's a good bet that most of you are familiar with SQLite. It's a well-known, well-used relational database engine. What we've done is we've taken the SQLite native bits and baked them right into the operating system on a Meadow. By putting it right into the operating system, we've enabled the ability to p-invoke into those libraries. That, in turn, allows you to use something like SQLite Net from your managed application. That gives you a nice object model to call into the SQL libraries without having to write actual SQL code. The other obvious benefit, aside from not having to write SQL, is that you have code that is portable across different platforms. So if you write some code for a desktop or a Xamarin mobile app or something along those lines that uses the same SQL database, that code is actually directly portable down to the Meadow. Saves you time, saves you work, saves you debugging. Another major advantage of using a relational database is that your data persists across reboots or brownouts or resets of your device. Resets are quite common in IoT scenarios, so the ability to have data that isn't just in RAM is really important. Of course, you could use just a file, write it with a text writer, something along those lines, but retrieving data from something like that is difficult. It's also really difficult to delete records in the middle of a text file. So a relational database works really well. It's especially good for something like a store and forward service model, where your application is taking data as it's received and stuffing it into a database. Then you have a separate service or thread in the background that is reading back out of that database and forwarding it on to a service or a cloud, something along those lines. If communication is cut, network is down, the service is down for some reason, that store and forward service then only pushes when it's able to, so you don't have any loss of data. No data gets thrown on the floor, and you don't have any problems with data loss if you have a power outage while you have data that's been cached for forwarding during a network outage. Now let's just talk real quickly about the basics of doing data storage, especially to a database. The first thing we have to do is we have to define our storage entities, so the objects that we're going to put into the database. Once we've defined those, we then need to create the store or the database and create tables within that store to hold those entities. Once we've created the store and defined all the entities and tables, we then need to connect to that store. Once we have a connection, we can then do our creation, read, update, and delete operations. Let's take a look at what it means to define an entity for use with SQLite Net. You can see here that I've got a class that is basically just a pokeout, plain old C# object. Inside of it, the important things are that every property that we want to go into the database needs to be public, needs to have a setter and a getter. We also need to define the class with an attribute that is a table. In this case, we actually are giving it a table name that is different than the class name. If you omit that parameter, it'll just use the class name. Another often important thing is to have a primary key. In this case, using an integer primary key, which is set to auto increment. So it'll start at 1 and increment every time we insert. This is important here, so instead of having to look by date time, in order to remove them once we've forwarded them to the cloud, we can just look by ID. So we forward a specific ID to a cloud service. Once it has been recorded in the cloud, we can then delete by that same ID in our local database. This is actually a simplified example of what happens in the Klima application. Let's go take a look at Klima for a moment and see just a little bit more complexity. Here's the actual definition of the entity in the Klima project. We have the class definition with the table attribute. You can see we aliased it, and we have the primary key. But then we have all of these properties. They are not just simple setters and getters. Instead, they use these Meadow units conversions and then convert, for example, this wind speed is aliased down to some of these. So we have a Meadow unit speed here. The database has no idea how to store a Meadow units object, so instead we just store double values. You can see these properties are marked as ignore. That prevents SQLiteNet from even trying to put them into the database. And then lastly, we have this indexed date time field. By indexing it, it simply means that these will be put in order in the database so that when we go to retrieve them, it will be faster. Now let's take a look at the next step we talked about, creating and connecting to the store. You can see here that we create a database path and then pass that into a SQLite connection object that returns a database instance, and that instance is what we use to interact with the database from this point on. You can see here we use it to create a table based on our climate reading type. Once again, this is a somewhat simplified version. Let's go take a look at the Klima source and see how we're doing it there. Inside Klima, you can see we have this class that's the local database manager. And this database manager has an instance static property. That instance is what the entire application will use anytime it wants to get access to the database or any data in it. When the instance is created, you can see we make the connection here. What's interesting is this path is generated using the Meadow OS data directory. This directory is not erased during deployment like the root directory. So when you're developing, it's important to use this directory so you don't lose your data every time you redeploy your application. Down here in the configure database method, you see we create the table based on the climate object type. There's also this line here that drops the table. That's purely a convenience thing. You're probably going to want to remove that line if you're playing with this or deploying this. Otherwise, you'll lose all of your data every time the application runs. Alright, now let's go take a look at data insertion. Inserting data is really simple with this object model. You can see what we've done is we have this agent. The implementation is over in Klima, but basically it is receiving events from the sensors and getting data in as a conditions object. This is why we used a conditions object for the database entity definition as well, because we can then call save reading on that database manager. We'll take a look at that here in a minute, but we can pass that condition directly to it and it will insert it into the database. We've also gone here on the agent. We've told it to start updating, which then will trigger that event. An optional item here is you could have a store and forward service that takes data out of that database, forwards it onto the cloud or to some remote service, and then once it has successfully been inserted remotely, go ahead and delete it from the local database. Again, let's take a look at this in the Klima code itself. You can see here in the Meadow app, which is the entry point of our application, right in the constructor, we hook the event on the climate monitor agent. Here we use the local database instance and then call save reading. Save reading over here in that manager does some sanity checks at the beginning to make sure things are configured, and then it calls insert on the database instance itself, passing in this climate instance. And you can see that that instance is just a SQLite connection. And that's a pretty good summary of how you can use a database inside of a Meadow application. Obviously, you can do more, and we haven't shown things like reading, updating, and deleting, but they're very similar operations. You'll be seeing a lot more examples using Klima throughout today's presentations. Remember, it is open source. It's an Apache 2.0 license. The full source is available on GitHub. I've put the link here on the screen. You can also pre-order all of the hardware for Klima, including an anemometer and a wind vane, though those are not required in order to start playing around with the source code. By all means, go download the code, play with it, learn from it, give us suggestions, and tell us what you've done with it. Thanks for your time today.
That was excellent. Chris really understands and knows this very, very deeply, and he was the excellent engineer that was able to bring all this to life. And it's really quite interesting because it is a complex stack, and we'll learn more about this later on. But there is the underlying OS that actually exposes the SQLite database, and it gets the APIs to be bubbled up through Mono, and then you have it's set up nicely to work with SQLite.net. So it's a really big feature, and it's really fantastic. And for those of us that come from the Xamarin background, it's a really nice, friendly API to work with. There was a really great question.
Sorry, I was just going to interject and say that in the early days when I was in Xamarin University and I was learning, data storage on mobile devices, there was actually a SQLite session. And it was all about, just storing data into your device. And now, 5 or 6 years later, now here we are just running SQLite on a microcontroller. So all that knowledge that you already know and used on your mobile apps, you're already able to throw them into your Meadow board.
Fantastic. And Chris, I see you here. Are you available for a couple of questions?
I am.
Wonderful. So there was a great question early on about...
Is it about store and forward?
That's the one. Thank you.
Yeah, I just posted an answer, but basically store and forward, it's not built in. I thought about doing a reference service for it. The challenge is that the back-end implementation tends to vary slightly. So it depends on whether or not you're using integers or GUIDs for identifiers and how you want to push and how you want to delete. We could probably put together a fairly easy reference service for that, but it would not be likely identical for every implementation. Then I think I saw one other one about EF Core.
Yes.
And I actually tried to get EF Core running with this, but the Meadow just doesn't have enough space. EF Core, as with a large number of Microsoft libraries, tries to solve all problems rather than 90% of problems. And so it's too big. It's very large. When we have linking working, I know it will bring down a lot of the footprint of what we push to the device. And when linking is enabled, it's possible that EF Core might work. So it would be worth a try if you're trying to keep code compatibility with other, stuff that you're working on. But otherwise, I don't know. Currently, it will not work. You can push it all down. And as soon as it attempts to create the connection to the database, it runs out of memory and crashes.
So in summary, SQLite.net is probably your friend.
In summary, yes, currently that is the way to go.
Fantastic. I'm going to show one thing really quickly here as well. I'm just going to share my screen and just show you all that there is a really great example of using SQLite, of course, in the Clean Meadow Pro source code as well. And you can see all the, for those of you that are familiar with it from other platforms, you'll see the familiar things like creating your SQLite connection. And you can see where we're actually creating the database on the file system. Again, that file system unlocking a lot of capabilities. And then you can see some fantastic examples of actually creating tables based on model objects. And
important to mention, and I had mentioned it in the talk, that path, use the path that is in there, that data directory, because it does not get erased on deployment. If you put it right in the root application directory, when you deploy your application again, your database will get wiped out. So just as a word of warning, because otherwise you'd be like, what happened to all my data? Yeah.
So if you want a persistent database.
Chris, and what happens if I want to update my data model? I want to add a column. How would that work? Is there a way I can just delete my existing table to recreate the database?
Yeah, you can do a drop table. In fact, right there on line 37, drop table will delete the table and you can add it. But the reality is you can, if it's only adding a column and if it's a nullable column, you could actually add it live and it will backfill nulls for all of the existing rows. If it's a non-nullable column, you cannot do that. You would have to delete all data and then alter table, but you can do it that way as well. So it really depends on the schema change you're trying to push.
Perfect. That's beautiful. I didn't know that. That's great to know. I'm more of a brute force SQLite.net developer. So thank you very much, Chris.
Absolutely.
And we'll talk to you later.
All right.
Really appreciate hopping on for Q&A. And Jorge, I think we're back to you. And next up, we're going to talk about connectivity, a little bit of Bluetooth.
Yes. So let's talk now about Bluetooth. That's something that it was also something that I was like really looking forward to it. And it was actually in beta 5 when we actually made it available. Thanks, hats off to Chris for putting this together. And it was just such an amazing feature. And I had my little Rover car there just gathering dust in the closet waiting, when is it going to get Bluetooth, until I finally got it and you guys saw it in action working. But I'm just going to move on back to go to Klima Pro version, because if we're going to have this little climate system into our backyards or in remote places, we might not be reliant on Wi-Fi all the time. So it might be better if we just have Bluetooth, so we can, once in a while, we drop by and see, and we just pair it to our device and get the information. And then maybe when we hit Bluetooth, when we head home or in our office, wherever we get connectivity, we'll be able to just throw that into the cloud and just keep our logs updated somewhere on the internet. Let's jump into our Visual Studio here. And I wanted to show you this little particular class. I'm going to move this over here. And we have, if we go to the Klima Meadow Pro project, we have this class called Bluetooth Server. And this is the one that is in charge of all things Bluetooth. So it's a singleton class that will initialize or instantiate all over and on Meadow and the Meadow app main class. And the things that we need to gather here or understand is the initialize method. So this is where everything is going to start to set up and start putting everything together. So the first thing that we need to understand is something called the tree definition. So the tree definition is our specs or our different registers or our different properties that we're able to access using Bluetooth. So in this case, for the Klima Pro, we have temperature, we have pressure, we have humidity, wind speed, wind direction. And for each of these are called characteristics. And with the characteristics, we have to pass in a unified, unique value, which is the UUID. And that is the address or the register identifier. Whenever we're going to get information from the device, we're going to need that information to reference that particular value so we can bring it over. And we have characteristics. In this case, it says string, but we also have integers, we have booleans. I'm using booleans on my rover because I just need them to go on and off to turn on the motors to make it rotate. And so yeah, we have, in this case, we have strings for everything. And there's also multiple ways that you can build this. We can also rely on one string, and then we can just grab all the climate reading, we serialize it in JSON, and we can pass it over to our app and deserialize it over there. In this case, we're just using 5 characteristic strings that we're just gonna access. And notice also other things here. Important is permissions and properties, which it allows us to also have that security or ensuring about the properties that we're exposing if we are able to just only read data. In this case is what we want, because I don't need to do anything to the Klima project. We just want to get the data that is available for us. And in the case of our rover, it also has read and write. So I can also read the state of where the motors are and what's there, if they're on or off, or we can also do write. As I'm pressing a button, I'm writing into that register or that characteristic, turn a motor on or turn a motor off, things like that. And
now, this looks pretty complex. Do you have any suggestions on how first-time developers using BLE might make this journey a little bit easier?
Sure. Yeah. First off, we have great documentation here. This will be an intro, very lightweight, understandable way to learn some Bluetooth. It took me a little bit to understand the graphs, because Bluetooth is a slightly more complex feature or communication protocol here. There's also information about BLE clients. So if you're using Xamarin, you can also get your NuGet packages and start building your own application to connect, which is what I've done to use our the Meadow rover controller, or also for this particular example, I'm also using a NuGet package here. And another bare bones application, and something I haven't mentioned throughout the entire session, we have a Hackster hub that has over 50 projects that are readily available for you to understand some things. Like I sometimes I don't want to be overwhelmed by a lot of things happening on the boards. So if you want to learn a little bit more and easier way to understand Bluetooth, I recommend this little project that I put in about how to control an RGB LED there. It's a great example, and it'll just give you the minimum code that you need to understand this.
I love this project. It's absolutely beautiful. It's a gorgeous Xamarin app. And one thing I'd love to throw in here too is, for BLE, it is complex. The APIs that the Willowside team put together are really streamlined. So this is a really nice way to implement BLE. And Jorge, I've really liked using some of those off-the-shelf BLE Explorer apps too. So as I'm working on Meadow, I can use those to interrogate Meadow and then make sure I've got everything working, and then build up my mobile client.
For sure, yeah. And so resuming about this example is after we have our definition of the for the Bluetooth connectivity on our device, we have this start Bluetooth server, and we finally pass this object that I've been talking about, characteristics and service and all that. And something really key is the climate conditions updated. So we keep track of an event handler of whenever the device is receiving requests from other devices via Bluetooth. So in this case, when I want to gather data, this event handler is the one that's going to be kicked off. And it's going to say, oh, look, we got new climate data, setting it, and then it'll just set the information, and it'll start returning that information into our phones. So let me jump in, and I'm going to show you my phone here. Let's see, I can put it on focus. Put this aside.
And we've had a request to bump the font size a notch too, if.
Oh, on the code here?
Yeah.
Sure. There we go.
Fantastic.
Perfect. And so let me show you first a little example. Let's turn the visor here because I don't want to. It's best to show you. There we go. We got our application. There's my phone. And now if I check and I set Klima here, this is a companion app that we're adding into in our repo. And we structured it to have the Hackett version and the ProKit version. So on the Hackett version, we're using something called Maple, which is used to gather information over Wi-Fi and doing just basic REST client server requests. And the ProKit version is the one that's going to kick off and have all the Bluetooth connectivity stuff. So I'm going to reset the board, the Meadow board here, and notice that the LED is going to blink. And once it goes back to green, it's going to indicate me that everything is set up, initialized, and Bluetooth server is already running. And now I'm able to discover it over the mobile app. So this is pretty quick. So it's already there in green. And if I click the Hackett Pro version, this is going to start doing a scan for devices. So it's going to spend a couple seconds there, and notice that it already discovered the Meadow Klima Bluetooth server, which is how I named it here on my BLE tree definition. Is called Meadow Klima. It's this guy right here. And all that's left is just hit this connection or pairing button there. And we're connected right now. We are connected to our Meadow board. And now we proceed and call the update button. And this will start getting the data straight from Bluetooth from your Klima project. In this case, it's gonna not give me wind speed or wind direction, or my Klima project's not properly set up with all the sensors and stuff, but it's also just to get you an idea. And this is fully scalable. We can also make it Klima to start storing data in a database, and I can also give me back, return me all the records, and I'll show them on a list view. In this case, very bare bones, very easy to understand. Just give me whatever you have in your current status. So if I click this update button again, it'll just keep updating and just get the latest information on the Klima project. So yeah, pretty exciting. I wonder if maybe I can show you a bit on the Klima app what I'm doing.
Yeah, I think seeing the client side is really powerful. And I love seeing, once you get the Bluetooth set up on Meadow, it's fairly straightforward. Then just update those characteristics and update those data endpoints. Exactly.
And so notice that it's, again, we are setting those UUID characteristics on the Meadow device. It's vital to have them also that they're the same on the client side, because this is the one thing, the one identifier on these characteristics to start gathering information from your device. So those same UIDs that are on Meadow, I put them here on the characteristic constants, and here they are. And so in the ProKit view model, if I do search for devices command, this will call scan for devices. And this is thanks for that that Bluetooth is called plugin.ble 2.2. And this has already an API that already tells you start scanning for devices. And it comes with an event handler whenever a device is discovered. Right, this one, correct? And it'll just give you a list of all different Bluetooth devices that it's on your vicinity. So notice that if I click here, it's finding other different Bluetooth devices. This case also, I think my printer is right there, so it's able to pick it up. But I don't want to connect to my printer. I want to connect to my Klima project. So I'm checking like, oh, Meadow device is discovered. It's called Meadow Klima, which is how we named it on the Meadow application. If it is, I don't need to scan anymore because it drains a lot of battery on your device. And we no longer device list is empty. And we do a device selected. And that will already populate your picker with that Meadow Klima. And yeah, so the other thing would be the Klima status. How to get the Klima status? It's pretty simple. You just do this async method. It's called a temp characteristic read async, and that will just handle going through all the process of connecting to your Meadow board, getting the characteristic, passing the UUID, and return it, and just display it on these values that they're the ones that are data bound to your labels here on the UI. So yeah, pretty cool.
I love seeing the .NET ecosystem coming together. There's just something beautiful about seeing a Xamarin app working with Meadow.
For
Fantastic.
sure, yeah.
We've had just a couple of questions, and I want to just focus on one. Thank you. I think Chris already answered that, but this is a great one. Just asking where they can find the Bluetooth sample code.
Right. Okay. So one option, the one that I would recommend, like I'm also a Xamarin developer, so having a companion app is really handy. You can also use Bluetooth scanner applications, so you can just go and look for discovering, and you look for the application. You can start writing applications for that. But going out of scope, it's really easy. If you use this application, we also have, if you go to the GitHub, we also have a Meadow Core. We also have a Meadow Core sample. What's it called? It's Meadow Core samples. Yeah, here we go. So on this one, it has a bunch of nice examples to show you how to do either connectivity. Here we go. We got network here. So we have things like Wi-Fi basics, how to connect to Wi-Fi and handle different scenarios of connectivity. We have Bluetooth basics. Also, this is the one that will show you bare bones of how to use Bluetooth here too, in just one simple file. And notice that we have, as I mentioned, we have characteristics for Booleans, we have integers, we have strings. We can keep adding more and more over time. And yeah, and there are also some other great features here. We have as well the config files. It's something that we also shipped in beta 6. We no longer need to do specifically if we're going and join a network. We don't actually need specifically to tell it to connect. We also have these config files. They'll be included on the projects. And you can also say automatically start network. You set it to true. So what does this mean? You run the application, it'll go through these config files, and they're like, oh, start network. All right, I got it. And it'll just join your network without without having to reconnect or without having to explicitly tell the device to join your network. And another also interesting, cool thing is NTP servers. So this means that when you're running the application, not only you'll join the network, you'll be able to query an NTP server, which is a network time protocol communication, and you'll also get your time, your local time, and set it on your board. So right out the gate, you do datetime.now, and you'll get the current time and date without having to query a web service, which is what I was doing before. So
That is beautiful. And it's almost as if we planned that to move into our next talk, which is could be all about networking and Maple. Thank you. That's perfect.
Awesome.
That's a beautiful segue. I think we're good for questions for Bluetooth, but keep them coming. We'll have some time over the break as well to dive into more questions. But yeah, let's continue on that conversation around networking. And we're going to show you a couple of things. We're going to talk a little bit about how we just use the networking APIs, and then talk about how we can host a lightweight HTTP server right on your Meadow board, and that is Maple. So let's, I'm all about the code, so let's jump into the code. Get my screen shared here again. And I've got back into Visual Studio, and I'm going to use the other project. We're going to use the HackKit project. And just as a reminder, I'm going to find my window here. So here I've got, this is the HackKit version of Klima. We saw this earlier. We've got the display, a couple buttons, and our analog temperature sensor. I'm going to use this as the foundation for some of our tests here. And we can actually, well, let's just jump into the APIs. So this is a .NET platform. We're using Mono. We've got the .NET runtime. It is full .NET. And so as you expect, you get to use .NET networking APIs. And I'm going to, let's go to the climate service here. This is a great one to start with. So this is an example in the Pro project. It might be actually in both, and I'll have a look. I think it is in both projects. The service actually there, yes. And this is a lightweight example of using networking APIs that works with the companion app. We've got a mini server here. And so in this case, what we would do is we would put in the endpoint, the local endpoint for our server that we can run locally. But I wanted to show you some of the APIs actually using this. And no big surprises here. It's .NET, it's C#. What are we going to use? Oh, Jorge? I think we should use HTTP client. This is
Yes.
How else would you do it in .NET? And really beautiful here. There's a couple of things that are really fun to see. So we're going to instantiate our client. Good old modern .NET we'll use our using, so we clean up after ourselves for our iDisposables. And then this is really cool, system text JSON. So we can serialize our climate model object, encode it, and fire it over the wire. And then in this case, this example is set up to work with a local server. But of course, this is a great starting point if you want to hit another endpoint on a public API.
Yeah, and also notice that we're using system.text.json, something that is already readily available on desktop, on mobile. You already able to bring it over to Meadow. As Chris mentioned, there are some limitations on memory, so there are some things that you can't just go and get a Unity NuGet packages, just jam it there and run Halo or things like that. We have to be also very we need to keep things in the lightweight side of things. So using things as the Newton JSON stuff, which is a JSON serializer that's way more popular, it might bring a lot of things that the Meadow won't need, but it will be eating much of your memory in that case. So we keep things light. We use system.text.json for this reason, and also we don't have any linking yet, so we are also bringing all the output files of things that we might not be using at the moment. But then once we have the linked-in approach, we'll be able to just remove all those unused files, and then we can have better use of our memory. So,
yeah, very well said, and exactly as Jorge said. It's not always the libraries, but it's the dependencies in those libraries, and so things like Newton's JSON has a big dependency tree, and it will pull a lot of content in. Linker, for those who are not familiar, it's a technique of effectively removing parts of libraries and code that you're not using. And so it's a tool that will run through and actually crawl the dependencies and see the code usage in your code, and can actually remove big chunks of libraries, sometimes even libraries altogether if they're things that are just not being used in your code. And that's being worked on, and that should really help compatibility. So if you run into memory problems, storage problems, future versions of Meadow should address that. But really exciting, because system text JSON is something we had to do a little bit of work on in terms of how we handled the base class libraries to enable in Meadow v6. And so it's really exciting to see that working nicely here. So with the networking story, again, it's .NET, it's HTTP client. We can send data over the wire. We can fetch readings back from our server as well. And so again, not a whole lot of surprises here. A few things you need to do to get this working in your application. You need to set up your Wi-Fi. Jorge showed you another new feature in beta 6, where you can put it in the config file and have Meadow automatically fire up your Wi-Fi and connect with your credentials. You use that config file. I'll show you the other way here as well. And let me go with the right spot here. Perfect. So I'm back in the HackKit version of our Klima code. And there's an initialized Wi-Fi method here. We've separated out the Wi-Fi initialization. And there's a little bit of fun stuff here. I'll talk about this here in a second just because it's a little bit of fun C# code. But the important part for Wi-Fi is this right here. Remember we talked about the device class earlier? This is the class, the object that understands the exact hardware, right? This knows the F7 hardware, and then it's able to talk to that companion. There's actually a companion microcontroller on board, the ESP32, that controls networking and Bluetooth. You don't have to worry about that because it's all hidden, abstracted in those APIs, but we do want to tell it to connect to our Wi-Fi network. In this case here, we pass in the Wi-Fi name, Wi-Fi password. Again, probably going forward, the preferred method is going to be using that config file, but both paths are available. And then again, of course, it's a modern API. Notice that we are awaiting. This is a task returning method. It returns a connection result. We can test that status and just make sure it's successful and see if it passed or failed. Now, since I'm here, I feel obligated to show you just a little bit of code here. This is just some fun stuff, slightly off topic for networking. But we put in a little wait cursor. And is my camera still working? It's not on screen. No, actually, the battery on my camera. So I'll come back to that in a moment. But
I can show that in mine if you want.
Beautiful. I'll just walk through the code here. And if you feel like
sure.
Oh, great. But what's fun here, again, really showing you that we are using a modern API. Now, in this case here, we've got a task running, and then we're doing some async calls. Notice our modern pattern matching, really fancy switch statements in C#. And what we're doing here is we're updating, well, just a string. But we're using that string to update our on-screen text. And what we're able to do here is actually put a little animating ellipsis while we're waiting for that Wi-Fi to connect to give that feedback back to the user. Again, when you're using the HackKit version, we've got your display going. And so again, just that visual cue. Out in the wild, if we're looking in low power environments, well, we may not want to do that, but it's fun that we have those capabilities. And it shows a couple of other things that are interesting about Meadow, in that we're able to do things like update the UI in a task. We don't have to go back to the core of the main thread in order to update the UI, because we're just talking to the hardware over those hardware communication channels. And then just a little bit of fun modern C#. So we update this, and then what we do is when this comes back, once we've connected to our Wi-Fi network, in this case we use the cancellation token, we cancel out, and we end that animation. So again, good old C#, lots of familiar things. But I want to talk a little bit about Maple. And Jorge, let me know if you want to throw anything up on screen.
Yeah, sure. So yeah, for those who doesn't know about Maple, we already have a board that's able to connect to your Wi-Fi. So the next step would be, all right, if we want to get data from Meadow, what would be the next step? So go ahead, Adrian.
Yeah, fantastic. Yeah, so this has been around for a while, and this is a really lightweight, built for IoT, built for Meadow, lightweight web server. Now, for those of you that have been around the ecosystem for a while, there was a version of Maple running back on NetDuino. And this is really, we've modernized that web server. And you're gonna see it now, it's coming in, you can see it right here, support for system text JSON. And it's really meant to give a similar API surface, something like ASP.NET, but with a much, much, much smaller footprint and much, much, much lower memory requirements. Again, built for IoT. This is still a work in progress. It's working beautifully. We're going to see more features evolve as the platform evolves, but there's some interesting new features around routing. But again, it's a lightweight web service. So let's see what it looks like to bring that into a project. So over to our HackKit version. Jorge talked about this earlier. We talked about Meadow Foundation. Way you bring this in, well, we bring it in via NuGet packages, modern .NET environment. See if I can get this to scroll over nicely. Beautiful. And in this case here, we have Meadow Foundation web service. Maple Web Server. So let's have a look at how we would wire this all up. And in this case, I believe we have this all. Jorge wrote this for me, put this all together last night. So thank you very much, Jorge. Fantastic. And I beautiful make sure the right class. The temperature request handler class here. Now, what's important about this is this derives from request handler base. Again, we see some similar patterns here, and we can do a quick little poke here. And we've got our listener context and a few other common things like our send. And of course, it's deriving from iDisposable as we would expect. But then it's great. We just attribute our methods. In this case here, we're going to expose an HTTP GET. We define our get temperature method, and then that does a little bit of work. There's some convenience here. We're going to toggle the LED on the board just to give us a status indicator. It'll go magenta when the request comes in. And then we're going to build up our data and store it off, and then put our color back to green. And so I'm going to run this. I'm going to fire this up right now. I'm going to hit deploy. And what's fun about this is, so as this is deploying, I'm going to switch over to a modern web browser. And let me see here. Let me make sure I'm deploying to the right spot. And Control-Shift-M. I've been going back and forth on various boards. Should be COM14. I believe that's right. Let's hit deploy. There we go. And that's actually a nice little tip too. Sometimes when you're deploying, it's never a bad idea to reset your board in between deploys, especially for someone like me who's writing a lot of test and debug code. And so if my code crashes and puts my Meadow board in a bad state, hit that reset before you deploy. Not that we as developers ever make mistakes, but it could happen from time to time. So this is going to initialize. I'll show you in the bottom left-hand corner. You can see it's going through. It's going to instantiate our temperature sensor, display controller. It's going to connect the Wi-Fi. We saw that code earlier. But what this is going to do is it's going to fire up our web server. And we're going to watch for one thing really important. So right now, it's actually awaiting. I showed that code. And it's actually animating that little ellipsis on my display. I can hold it up on camera. You probably won't be able to see too much of it. But we're going to wait for that to complete, wait for that Wi-Fi connection to be finished. And then that's going to spin up our Maple server. And what's amazing about that now is now we can use REST to grab data from our board. Now I'm going to show you how to do that with the web browser, and then I'm going to pass over to Jorge, who's going to show you how to do that with a modern .NET application. And it's a mobile app.
Yeah, and notice again that we're doing the unitization here as well. That whenever we're getting the request, we are just doing temperature controller, we get the value, and then we return it in Celsius in this case. Eventually, we can put flags, and if you want to do a request, you can pass in a parameter in what unit you want to bring it. You can bring it in Fahrenheit or even in Kelvin. The possibilities are just endless. I try to have the tendency of showing minimal projects so people can understand. I think it's best than giving them a whole rocket ship of code there. Yeah.
So let me just zoom in here and just show you. So here's our address, 192.168.182 on port 5417. So that's exactly where we're going to go. And again, our HTTP attribute, get temperature. So that's our endpoint, get temperature. I'm going to run that. Did I make a typo? Let's see what I did.
Get temperature. I think it should be fine.
Don't say what to do. Well, I might pass over to you. I'm sure I've made a typo. Sure. But yeah, why don't you show it on the mobile app? I will fix it on my side, and I will have this working for y'all in just a moment. But again, I think it's a typo, but it is just hitting that API endpoint.
Cool. All right. If you can share my screen, I appreciate it.
Absolutely.
Perfect. Okay. So Adrian already gave you the rundown of how to use, how to connect to Wi-Fi, and how to start Maple is something also that's really important, and I think something worth mentioning. We have a Maple server field here that the way we instantiate it is passing in, newing up Maple to create the object, pass in the IP address of where your board is connected, which is right this little field that is already accessible, and we pass in a port to communicate. And this is a really cool feature that we're including on Maple. So sometimes if we are running our Meadow board and it doesn't have a display, then it will give me an address, but like, how am I able to pick up this address so I can connect to it? Well, we have this thing called discovery mode or advertise. And what it'll do is your device will start broadcasting the Maple server name along with its IP address. So other devices that are listening using our NuGet Maple client that'll be running on your app, it'll be able to pick up this UDP message and say, oh, I found a Maple server. And then it'll grab the IP address and you'll be ready to go, and you'll be using Maple, just start sending requests without no need of going into your code and writing down the IP address and the port. But you have that option if you want to put it on your application, but it's a convenience of being able to just discover your board across your Wi-Fi network. So let me plug this in. I'll connect here my little Klima Hackett project. All right, let's see if we can. Let me zoom in here. Maybe we might be lucky to see the ellipsis going. And there's a lot of stuff happening on this Klima Hackett. We have push buttons running here. We have the temperature sensor. We have the display running. We have SQLite running as well. We have monitoring climate change using the analog temperature sensor. So we're using the observable React approach. And so there you can see those little ellipses there. Adrian cleverly put them as giving us some feedback that is actually joining a network. I normally just, if I don't have display, I just make the LED pulse a different color every time through the initialization until it reaches green to give me a feedback that the app is ready to go. So we have to wait a few moments to join the network, and then it'll start the Maple server as well. And normally, I think it'll be bound to get faster. But yeah, there's a lot of stuff happening on the app.
Absolutely. And I can confirm, I diagnosed with in the background, I missed the colon on HTTP. So it's working beautifully on the endpoint.
Awesome. All right. Yeah. So there you go. It says Wi-Fi connected. It starts sensing right away the sensor, the analog temperature sensor. So my room temperature here is 20 to 23 degrees Celsius. And if I start the application now, I have it right here, but I'm just going to show Visor, so I need to, let's put it on Visor, next by, here is my phone. And then if I run the Klima app again, we can now go into the other app version of the app or approach is the Hackett version. So I click Hackett version, it has the Maple client running, and it'll start listening to UDP broadcasts. And there you go. It picked up the new Maple server running, which is, the guy right here is right next to the phone. And immediately after connecting, is just going to query, give me your temperature data right now. And it's also giving me the date and time. So if I do a pull and refresh here for the list view, it's just going to throw in another request, and it'll just giving you the same current data over and over again, populating the list view. I'm not sure what happened there. It was going well. Yeah. So basically, yeah, that was basically the gist of it. I can show you the code of how the discovery happens.
Client side, yeah, absolutely.
Yeah, exactly. So let's go to the Hackett view model. And here we have we have a server model. It's something that, we have, it has an IP address and the name of the server. And we also have the reload temperature log. That's when I do a pull and refresh. It's going to do the temperature, get the temperature logs. And that's going to make the it's going to do a client, which is the Maple client that I was talking about, that you'll be able to install on your client applications. So you can just do a regular GET request and just pass in that endpoint that Adrian was mentioning, get temperature. And once we get the temperature back, we do a JSON convert, we deserialize it, and we can add it finally into the list view. And here is how we normally we scan for some clients, some servers. We do start scanning for advertising devices. So if I can find any after a while, I just show a server list empty. And if I actually find some servers, then I can just pick, and I just put the first one by default. And I have a server collection change, which will be an event that is triggered for every server that I pick up via the broadcast on UDP. So yeah, that was basically what I wanted to show you here.
That's beautiful. So that means that we could actually have multiple Meadow devices running Maple, and we could connect to those devices through this client application. Really cool demo. So I think
one last thing. Sorry, I wanted to also give it's advertisement time, but I just wanted to show you that I've put together a list of Maple examples here as well, because I think it's also worth mentioning if you want to start working with Maple. I have control an RGB LED version on using Maple. So you have a companion app, you have your Meadow app, and just very bare minimal code that you can just start learning right away. And then after that, you can scale up and do other things. And in this series, I added also how to control a servo motor too. So this also comes in the hack kit as well. So I have a little slider there, so I can move and set my rotation on my microserver whenever I send a request. Maybe if I can make it faster, I can make it reactive as I'm pressing the slider. I can just send a request to make it rotate. But again, the possibilities are endless, and it's something that it's a go-to guide that is very well read and explained down to the line how to put these projects together.
Thank you very, very much. I'm going to do one quick question on the topic of network, and then we're going to jump on to our next topic. But someone asked about Ethernet ports. And yes, so the core compute module will have Ethernet support. So yeah, in the works. Great question. Yeah. And we'll go back and look for other questions as well. And thank you everyone who's jumping on chat and answer the questions. So let's now move on to our next topic. We're going to talk a little bit about the display we're using. And I'm going to hop back on my camera. And actually, let's do it this way. I'm going to zoom in here just for a moment. And so you've seen this a few times. I'm going back to our HackKit Pro version here. And it's a little bit washed out. We've got our display here. This is our TFT. There we go. Our TFT SPI. This is an ST7789 240 by 240 pixel 16-bit, actually up to 18-bit color display. And this is a really cool, really beautiful, crisp display. For those of you that have the hack kit, you do have this one in that kit, also available from a lot of retailers. And this is a really fun way to give some visual feedback to your projects. But display is only as useful as the API. So we're going to dive in and talk a bit about we call micrographics, and it was our graphics library. And it's a graphics API specifically designed, again, for IoT devices. And what's really fun about this is not only is it a nice, tidy API, but again, thinking about usability, but we've thought about how we can make a consistent API surface regardless of the type of displays you're using. So for example, imagine you're doing something like this. This is an e-paper display. And I love this. I actually pull back. Notice no wires, no batteries. this is not powered right now, but that display holds its state. Love these low power e-ink displays. Now this here, this is basically a 3-color display. It's got red, black, and then just the default white. So that's going to be a little bit different than controlling a full 16-bit or higher color display. And now if you also peer over my shoulder, I'm going to scooch over a little bit. This is another fun one. So this is a display, and this is the Max 7219 controller, and I can get a close-up of that in a moment. That's basically just an array of LEDs. There are 4 LED arrays that are 8x8, so that display there is actually using 8 by 32 pixels. Very, very different than something that's using 240 by 240 pixels. So we had to think long and hard about how we could expose an API that's going to let us control everything from complex, high-res, high-density displays to very, very basic arrays of pixels. So let's talk a little bit about micrographics. And Jorge, I might lean on you for some demos here as well. But
Of course.
Let's get my screen up and let's look at some code. So back to our Meadow HackKit code. And in our code, we have a display controller. And we've looked at other things we've instantiated for our hardware. And again, we're going to see similar patterns. We're going to use that device class again. But I love seeing this over and over again. So back to our nice driver pattern. So in this case here, we're going to have an ST7789 object that's going to represent the display. And we have that. Now, I've got the code here with local project references. So it's actually referencing the code in Meadow Foundation. But you would do that by pulling in the SCF, the TFT SPI NuGet package that will give you access to drivers for a number of these color displays. Right below, we also have something else very important. This is our graphics library. This is actually, we're calling it micrographics, and you might see some API changes in the future as we're towards version 1.0. But today, the class name is a graphics library. And these are the two things together that are going to allow us to control the display and do some really interesting things. I'm also going to point out one more thing here. We're going to pass our menu for a moment and come back to that. And that's this buffer class. So new in beta 6 are these buffer objects. And these are going to allow us to store really display data of various forms. And I talk a little more about that, but I'll point it out because we're going to make use of this as we update our display. So first things first, how the heck do we use our displays? So similar to what we saw before, and Jorge, I love seeing consistency. So we need to instantiate our display. We new up the object. Now this display is a little bit more complex than some of our other peripheral sensors. There's more connections to it. SPI, in this case, it's a 4-wire. Yes, it's 4 on mine, sometimes 5-wire to control these SPI displays. And so we also have a lot of flexibility on how we communicate with them. And SPI is actually, it's a higher speed bus than I2C. We can control that clock speed. We're doing that here. So we set up our configuration. We can, for our SPI, we instantiate the bus. And then again, we pass in that configuration. And this is interesting. So unlike I2C, we can chain a whole bunch of devices onto that bus. For SPI, we can do it, but there is some SPI specific configuration like that speed and that mode. And so we can put more than one thing on that bus, but these settings need to be compatible. And so we're gonna set that up here and then pass it in when we instantiate our device. And what's fun here is notice this display color mode and actually the width and height as well. So we're putting the parameters for our display. This particular controller, you can get various resolutions of those displays. 240 by 240 is the most common, but I have seen up to 240 by 320, and I think there's a lower one, and I want to remember it's something like 132, something along those lines by 240. So similar-ish, but they're configurable. And then we can actually set our color mode, and that's the number. That's basically the variation we have for each pixel, how much control we have. And in this case, this display, we're supporting up to 16-bit per pixel today. So this is going to give us control of our display. Lots of fun.
Yeah, I love how graphics library is so display agnostic. So just instantiating your display regardless of what it is, just setting that and throwing that into a graphics library, and then you're ready to start just drawing shapes and text. It's something that I haven't seen before, so it's pretty cool.
Absolutely. So thank you for that. That's perfect. And so I'll show you is on the display object. So our display class, there's a couple of methods. We've got draw pixels. We can specify a position on the display and do it. I mean, so actually draw a buffer. I showed you that buffer object above. We'll come back to that, but we actually can pass in a structured buffer of image data. But notice here, there's not a lot else. There's fill and there's clear and a couple of other little kind of handy, convenience methods like invert pixels. But there's not draw circle, draw text, draw primitives. And that's where the graphics library, that's where micrographics comes in. And exactly what Jorge said, we're going to instantiate our graphics library object, our instance. But notice what we do, we pass the display in. And that's because all of our display drivers today implement a base class of type display base. This will shift, so fair warning, we will shift this to an interface, and a future version will be mostly transparent to you using this, because again, we'll change the constructor for the graphics library, and this will implement it, but some possible breaking changes coming. But the beautiful thing here is all of our pixel-based displays, everything from high-res color to arrays of LEDs, all implement that contract, that base class today. So they can all be passed in the graphics library. And then where graphics library is really fun is, well, that's what gives us the control to do the fun things. So notice here I'm gonna say graphics. And then here is where the fun stuff comes in. So I'm going to go here, draw a buffer, draw a circle quadrant, draw lines, rectangles, paths, etc. And you'll notice this API, if you've been around with us for a while, this API is constantly evolving. Path support came in, I want to say V5.2 or 5.3, and you're gonna see these APIs evolve and mature. And what's beautiful about this and this abstraction here is when we move to something like hardware accelerated support as well, these APIs will be consistent. And so you only have to learn one API surface, you don't care which display you're using, and you've got this really nice surface. So with that in mind, let's see how we actually put it into action. So we've got lots of fun things here, and I wanted to switch over to, I'm going to start with draw background. This is a really nice example of using these displays. So very common thing to do is clear out what's on screen. Now every driver has basically an off-screen buffer. We're going to write to that buffer, and then we're going to send it over to the display to represent it. So for graphics, we're going to say clear and blow it out. Now in this case, we can actually pass in a color object, and this will then write that full color to that background buffer. This is really fun. So for B6, you probably saw there's some comments of performance improvements. This is an area where doing full screen clears has been drastically improved. In some previous versions, this would actually take seconds. We're now talking fractions of a second, as it should be. So clear the background color. And then I want to focus here. So again, seeing those primitives, in this case, we're going to draw a circle. We put it in again, standard thing, center X, center Y, a radius. We can give it a color. We can fill that circle. And this is then going to layer up that information on that buffer. Now, this was interesting. This is one thing that I'm really excited about with B6. We've got this draw buffer method. This is new. So again, we're going to pass in a location, an X, a Y, and a buffer. And this is what allows us to store structured data in memory that we can reuse and draw to the screen. And I want to show you where this one comes from. Oh, I will show you this here. For splash screens, we draw a background, and then the last thing to do to push that information to the screen is call show on the graphics library. That will then tell the display to update with the buffer, and then beautiful things appear on the screen.
I always forget that the instruction. Even in OpenGL, I would draw, I put my scene with drawing shapes, but then why won't it draw? Then it's, of course, you have to do the graphics.show. It'll actually pull the buffer into the display, actually show it. So yeah.
Yeah, and there's a lot of fun conversation to be had there. I won't go into a lot of depth, but with these communication protocols, especially if we've got displays using I2C, it's a relatively slow bus. So you can get good frame rates, but you're not going to get 120 frames per second. And so you want to be intentional, but when you're pushing data over that bus, so this gives you control over when you update the display. We can also do things where we can work on that off-screen buffer and then do partial screen updates. So if we know that parts of the screen haven't changed, when we call show, in this case here, we're calling show with no parameters, but there's also an overload where we can say, hey, We can update either by XY width and height, if I remember correctly, XY left and top and bottom. Sorry, left, right, top and bottom, or pass in a rect. And that's going to tell the display to only update part of the screen. And again, back to sending that data over the bus. In that case, we'll send behind the scenes, we'll send a command to the display saying, hey, we're going to update this part of the screen and then only send that data, which means faster update times for doing partial screen updates. Now let's talk a little bit about that logo, that draw buffer. This is a fun thing here. So I'm going to zip on down here. Now, some of you may have seen this previously. We've got a little lightweight NuGet package that we use to load JPEG data. Let me see if I can find it here. It should be in the packages. Beautiful. Simple JPEG decoder, really lightweight, really simple JPEG decoder. Now, previous versions of Meadow Foundation, you would be pulling that data out into a byte array. You'd be iterating over that byte array and manually updating pixels. Little bit of work. This has gotten a lot easier. Let's scroll down. So now we've got a load JPEG method. This is a convenience method in this code. And it calls another convenience method called load resource. This allows us to load embedded assemblies. And so load resource gets the execute assembly and then gets the resource name based on the project name, Wilderness Labs Klima Meadow Hack Kit up there. Then we pass in the file name. In this case, we're using a file called meadow.jpg that is an embedded resource in our project over here.
Awesome.
Yeah. So lots of fun. And so with that, let me just zip on over here. So a little bit of work, we grabbed the stream and we grabbed the bytes out of that. But now what we've got is the JPEG data. So then we need to decode it. So we grab that JPEG data, we run it through the decoder. But now what do we do with that? And that's the fun thing. So now we can create a buffer. In this case, it's a 24-bit buffer, 888. So that's 8 bits for red, 8 bits for green, 8 bits for blue per pixel. And we instantiate this buffer. We tell it the width and the height of the buffer. And then we pass in the data that comes back from that JPEG decoder, that simple JPEG decoder. Now we have an in-memory representation of that image. You know, you might be thinking on other platforms, yeah, we've got really robust graphics libraries, maybe doing 3D gaming. Yeah, this is simple stuff. But for an IoT lightweight platform, this is a really nice convenience. We're not bloating up our application, but we're making it really easy to manage these type of buffers. And then if we go back to our draw background method, notice here we call graphics draw buffer, give it a location, pass in the buffer data, and it draws. And I'm going to mention one more thing quickly here as well. One thing that's quite fun about this, if you remember when we instantiated our display, we instantiated our display as a 16-bit per pixel display. I won't scroll in the code too much. And so this buffer is actually a 24-bit. So this draw buffer actually hides a little bit of logic where it's actually going to downsample that 24-bit per pixel image to 16-bit on that drawing routine. And it's relatively fast as well. And you will get some performance benefits if you do those conversions manually, so you represent it in a format that's appropriate for the display. But you don't have to worry about that. It will do the conversion for you if there's a mismatch between the display and the logo. And so with that, let me just pull up a quick example. Actually, I can do this the lazy way. And again, we can look at our code here. And again, we can see, once that camera focuses, there we go. There's our we got the full screen clear. We can see the circle. We've got our Wilderness Labs logo here up the top. And this is how we compose visuals on our displays.
Cool.
Yeah, we go a lot deeper, but I think, we're kind of getting towards the end of time. Anything else you want to mention here, Jorge, before we move on?
Yeah, well, thank you. It's a great project, and all the work, like I've seen how graphics have matured. I built in Hackster a gallery viewer showing little images and showing the old way of like refreshing the whole screen, and then you press a button and goes to the next image. But that was taking 20-30 seconds to load per image. But now with these massive improvements on B6, all the changes between all these images are full screen refreshes. They're much faster. I haven't quantified them yet, but they are definitely a game changer compared to what we had before.
Yeah, no, it's a lot of fun, and there's more performance we had as well, but it's nice to see B6 had a big bump there. I'm skimming for questions. I see a question of support for other displays. Yeah, there's a request form you can fill in. Come into the Slack channel for Wireless Labs if there's drivers you're looking for. And again, you can go through the source code. I think I've got this here. There's a ton of example drivers you can look at in terms of implementation. So if you're looking at adding something support for a specific display that we don't have support for today, you can follow those patterns or put in a request, and you'll see the driver surface increase over time. And again, you can go through and see, here's our TFT base class and driving from our common display base. And someone asked, so this is an interesting question. So HDMI, so that's an interesting question. I don't believe there's HDMI is not implemented on any of the Meadow F7 boards today, but with the announcement of Meadow for Linux, I think that will likely be on the radar. I don't think it's on the roadmap today. Maybe community can support it, but with this pattern, that's the beautiful thing. We've got common implementation structure for this, so it is absolutely very possible to implement a graphics library compatible HDMI display. I know it's been talked about casually amongst some of the engineers, but most likely not prioritized for V1.
Perfect. Yeah, so I think that will resume everything about graphics, and I think the last session we have on hand, it will be the Meadow app architecture. So maybe it would be a good time to kick off this session now, and then we go for lunch. It'll be, let's just talk about it now to get it out of the way. We're going to be a little extra over time, maybe 10, 15 more minutes, and then we can take a break.
Yeah, that sounds perfect. And we are going to talk more about the Meadow architecture in general after the break. Alexia will come in and give us the beautiful vision of what's going on under the hood. But I want to talk just a little bit about how we put Klima together and some of the designs that we made from a coding perspective. And you've seen lots of pieces of the Hack Kit and the Pro projects, but let's step back and say, okay, well, how are we actually building this? And the first thing to think about when you're building IoT solutions is, generally speaking, unless you're doing a lot of clever coding, you're doing single purpose applications on the hardware. So yes, there is an operating system under the hood, and it does exist, but it's not an OS like we think of normally with like Windows. It's not a multi-user, multi-application environment. And really under the hood, the app we run is the runtime. That runtime then kicks off the application and push the board. And that's actually very freeing because you don't have to code defensively worry about things like multitasking. For those of you that come from a mobile background, the Android lifecycle can be very complex, and you're managing managing both parts of the application that are your visuals versus background services, and that lifecycle gets very complex. The lifecycle is drastically simplified on Meadow, and that's really beautiful. And that allows you to do some fun things. So you will just see some decisions like when we do things like initialize the network, we can do those things asynchronously. You've seen the APIs. Let me just jump in over here. But because we know this is a single purpose application, we can make the choice to say, you know what? Yes, I can initialize the Wi-Fi asynchronously, but I know my application in this case is dependent on it. So I'm going to wait on that. And that is an okay design decision for this type of application, because the user isn't trying to switch over and play solitaire on the board. The user is just running this application. And so we can say, hey, well, we're going to have that performance penalty for starting up, but we know things happen in chronological order, and we know the exact state as we run each method or each stage of our initialization. It also allows us to do other fun things in terms of how we reach other services or dependencies in the application. Again, modern developers might use techniques like service injection, for example, or more complex management. We don't have to worry about that. We can build those kind of things. We can find lightweight injection patterns we use in C#. It's the beautiful thing of the language. But we can also use some more basic patterns. And one thing we've chosen to do on a lot of these is actually use singletons. And let me find a good example. I think the data access layer in Klima Pro is a good example of this. And so in this case here, we've opted to use a singleton because we know we're only going to have one database. We know there's not going to be anyone competing for resources in terms of file allocations. And so this is actually a safe strategy, and allows us to use, where we might use like a service locator pattern in other platforms, we don't have to be that fancy. We can have a singleton, we can expose that public property, we can get to the instance of our local database from anywhere in our code. Now, some people might say, hey, I don't really like having that sort of effectively global, and that's, again, a decision that we can make as developers. But in terms of a performance, memory management, or competing resource strategy, this is absolutely a fair game to use. And again, for those
also, so it's also important, like, for the life cycle to not have multiple instances of the local DB manager. If we have one instance throughout the lifetime of the app, then we're good to go, right? Because in other places of the application, we might need to read, or we might need to update or create or add records. We can do that with this singleton class that is already there, available throughout the application.
Yeah, thank you. That's a really important point. Now, we can talk design patterns, and you find me 10 developers and I'll find you 10 opinions on how to structure these things. But for sure, absolutely, we know that we're not going to have multiple instances of DB manager. We want a single instance of it. And this is where the lazy singleton pattern is really powerful. It also allows us to do great things like, we talked about making that design decision that we're going to front load the initialization of our Wi-Fi network. We might take that time penalty because that's critical to our application. It's a decision that we make based on the needs of our application. But in this case, we might want to get some things up and running before we take the performance penalty of instantiating our data structure, our data manager. So in this case, this is where we can do the lazy loading. We load it once on demand as we need it, so we can let the rest of the application start up. Again, it's C#, it's .NET. We can do things in parallel. The platform is capable of it. We saw that earlier today when we had the wait cursor running. We're updating our display while waiting for the Wi-Fi to initialize. But really nice. Jump in, please.
Sorry, Adrian. I just wanted to say that another really cool feature that I always constantly bring up in every session is we have this thing called Watchdogs. And the Watchdog is the functionality in our boards that, if you have these boards in the wilderness, maybe even your klima, it's sitting on in the backyard, and it's up in a post or something. If that application tends to fail given of power outage, or there was an exception occurring during runtime, the Watchdog, it monitors your status of your application. So in case the application crashes, it'll just resume the application once again, just rebooting itself and restoring and grabbing all the latest state of your app and start getting the app running right away. So you don't need to, climb a tree or anything with your computer and start redeploying again. No need for that. You'll just leave the Watchdog, just keep track of your application's health to make sure that it's running at all times.
Yeah, and thank you. That's a really important part of the application lifecycle. So I thought it is simplified compared to other platforms, but unlike web and mobile, where you have very complex patterns, it is generally up and running or not. But we have that fail-safe. So where we might have inconsistent power or other reasons the app gets down and gets reset, we can bring things back up and rehydrate. Beautiful.
Perfect.
I'll talk about a few other things, but generally speaking, what we've decided on from an architecture and the coding perspective is to break things down into services. And in which case, you saw this earlier when we talked about the Meadow Pro. We've got the climate service where it's going to do the interactions with our, sending our data over HTTP, where we're uploading to an external server. And you'll see the climate service as encapsulation. You'll see something very similar with Bluetooth, where we set up the Bluetooth server. And again, similar to our database, where we've chosen to use the lazy pattern here. Again, it's a singleton. You've got a single instance. We know we're only going to load one instance of it. We load it on demand. Again, a really nice pattern. We don't have to front load the instantiation when the app starts up, but we'll take the load time as needed for Bluetooth. Now, one thing that gets really interesting on IoT is where you're interacting with the end user, and it is that interface. And for those of you that have been around web and mobile, we often think about the UI, and we say UI, what we really mean is display things to the user. And That can very well be the case here, but we're going to have interesting things where our UI might actually be comprised of, well, it could be displays. We might add physical buttons or joysticks. We might have a touch screen that we bring those capabilities, or we might have other ways for the user to send data into the device, and we have other ways of getting data back out. Sound is another interesting one where, typically on a mobile device, you've got a common audio API. And for those of you that kind of look at these lazy instantiations and go, oh, that feels wrong. Well, you know what? It's actually not that different than you think about how we do it on mobile, where we have a common context for our graphics displays. We have a common context for our audio. And so here, well, you're in control of it. But because you're configuring the hardware, you actually get control how and when you get to these services. And I'll pull up this display controller quickly here as well, just as an example. But notice in this case, we've done a few things where we've encapsulated, you saw this earlier, the display in the graphics library. One thing I didn't touch upon is actually an additional UI level, and that's something called text display menu. Won't go into that right now, but a really great way of adding a simplified menu user interface, works with graphics libraries, works on all pixel displays. Could talk for days on this kind of stuff. But we've encapsulated the menu, that UI, the graphics, and the display driver into the display controller. So it's an encapsulated unit that is really our primary point for our UI. And then with the menu, we've chosen to expose methods so we can inject the events from our buttons into the menu. So we've got a selection, and there's actually 3 buttons on the hardware. Again, take a look at the source code to dive deeper. But there's an argument made that we could actually encapsulate all the UI in this controller as well. In this case, we made a design decision to make it the display controller. So it's the display of the menu, it's the visuals, but you could actually make a UX or a UI controller as well and bring that other hardware in. I think with that might be a great place to leave it. We'll come back and talk a little bit more about the overall architecture of Meadow, understand the technology stack. But again, I think keep in mind, single source, encapsulate functionality, and you have full control of your object lifecycle. And so patterns that you might not use on other platforms because of the complexity of a multi-user, multi-application environment, you actually don't have to worry about on IoT, which gives you the gist of the encapsulation, the singleton, and lazy loading.
Yeah, I also want to say that remember, we are in beta and we are trying to get things more stable. And so even the state of the architecture for Klima is in this state right now, but we're bound to just making it better over time. So there might be some room of improvement on certain places. And so expect more changes on the Klima. So, or even it's open source, right? So people can also do their contributions and, trying to propose different ways to make the architecture more stable, more robust, and more maintainable, which I think everybody wins.
Absolutely. And I'm actually just reading some of the comments here. And there's a comment about renaming the watchdog. And that's an interesting thing here. And this is one of the things I really love about this platform is we're marrying the familiar. We're bringing together familiar .NET, the IDE, got Visual Studio. We're using our NuGet packages, and it's very much like other platforms we could develop for. But you're bringing in some standards from the IoT, from the hardware world. And I think as mentioned, Brian in the chat, yeah, Watchdog, that is a standard hardware convention. And so you're going to see that coming in. And it's actually a lot of fun. This is actually a really great way to learn that because we've got these tidy APIs where you're in that familiar space and you get to bring in and learn some hardware as well. So with that, thank you very much. It's time for a break. We're going to play something fun while we all take a break, rehydrate, refuel, and we'll come back at 1 p.m. PST. For those of you that aren't on the West Coast with us, that's going to be in about 46 minutes, according to my watch. We'll see you then.
Cool. See you guys.
All right. Good afternoon, and welcome to the second half of Wilderness Labs DevCamp 2021. Super exciting stuff this afternoon. We're going to start with our very own Alexi Christoforides, Meta OS lead, and he's going to do a deep dive into the Meta OS internals, and then we're going to have Chris Tackey do a deep dive into the brand new, just announced Meadow.Linux, which will be a lot of fun. And then I've got 3 back-to-back sessions on how to create your very own custom PCBs. And those will be fun. And those will be coming up after the Linux deep dive. And then finally, we're going to wrap up the day with a live fireside chat and Q&A. So without any further ado, I would love to introduce our very own Mr. Christoforides, coming live from Boston, Massachusetts, and is going to dive into just how we've created all of this Meadow magic. So take it away, Alexi.
Hi, everyone. Thanks for the introduction, Brian. Yeah, I'm going to go very quickly, basically, because there's a lot of platform, a lot of work that went to the Meta OS, basically what almost a blanket term for all the software, all the low-level software that was written to support the Meta platform. But in 10 to 15 minutes, let's cover the basic components of it and some of our strategies and goals for the future. The primary goals of the Meta OS is to be high availability. We are developing an operating system for devices that are going to be in the field that are going to need to be able to recover themselves or update themselves without any wired communication or a person going over there and pressing a few buttons and logging on a USB. We need a platform that can do modern internet communications. So we need software that can handle Wi-Fi, Bluetooth, Ethernet, pretty much the 3 most popular ways to connect your device to the internet universe. We need to have secure communications. These are devices that are, again, going to be targets, possibly. And again, anything on the internet today has to be secure. We need to support modern crypto, any kind of modern crypto communications method that is used by modern software and hardware. We need to support it. Obviously, we need to have TLS 1.2 for the modern web. We need to provide a safe and capable execution platform, a place where the app developer, the person writing software that's actually going to do something useful with Meadow, is not worried about vulnerabilities, which is again an issue with writing low-level software, and something that generally anything that's connected to the internet is struggling. Big tech is struggling with this. Modern OSs are struggling. So it's something that needs to be taken seriously about how to have a secure device, and that means secure software. Going with high availability, we want to support, and we will support full remote over-the-air updates, meaning that your device or Wi-Fi can receive a push notification of an update to the app or an update to the operating system itself, and apply that update and get back into running status as soon as possible. Same goes for instrumenting other changes to the devices, like shutting them down, bring them back to life, putting them on standby. Remote administration is a big component of what a full Internet of Things operating system can do. Efficient use of limited resources, that explains itself. Meadow is a small device. We can't have a full desktop operating system running. We don't have a running UI. These devices have very little RAM, and low CPU power. The Meadow is very powerful when it gets to be used efficiently, But for example, you can't really run JavaScript on it. That's not the most efficient way of using this. And so we have to be within our limits. We have to be efficient to make it a powerful device with what we have. And finally, easy and efficient development. We want our platform to be a place for someone who just wants to create what they have in mind. They don't need to fight hardware. They don't need to find. They don't need to fight the software. Writing in C is usually the only option a lot of embedded developers have, and that's a risky move that we're gonna talk about a little bit later. It's unavoidable when writing low-level software, since a lot of it is in C and has to be in something like C or Rust. But we're gonna get to some tactics about how we handle native code. The primary components of the Meadow OS, real quick, the things that are in bold that are things that we're mostly actively developing, actively modifying, contributing to, or are completely house-owned components. So we have a custom bootloader that handles, obviously, starting the OS, but its main features are its ability to perform OS updates and rollbacks, which we need for as we said, for our MetaOS goal is to allow full updates. And the bootloader moves straight to Nuttix, which is we're gonna delve into a little bit more depth about it, but it's a real-time OS kernel. It is the heart of MetaOS. It's the scheduler. It's memory management. It does a lot of the networking stack, and from there, from the network stack, in fact, connects to MetaComms, our software component that runs the second of the two main CPUs on the Meadow board, which is an ESP32 that provides Wi-Fi and Bluetooth capability. Then we have HCOM, which is our like in-house built sort of, yes, controlled data transfer nexus is a good way of putting it. It's a message based way for the main CPU to communicate with the networking CPU, and also to communicate with the desktop for the developer to provide bidirectional communications, such as for deploying files or for debugging and other support for host control. Then we have Mono, which is .NET Virtual Machine. It can run .NET apps, and if you have already developed on the Meadow, you know that it is a .NET environment. So people write in C# and F#, which are the .NET languages. Embed TLS and SQLite are two industry standard software providing us with crypto and TLS support from Embed TLS. SQLite is providing us with a database, on-device database, and persistent storage and query capabilities. So those are mostly not modified by us. They sort of like work in place, and it's something that we will maintain a relationship with as we move on. But we're not modifying SQLite heavily or Embed TLS. We're just using their graces. Meadow.core is a .NET direct hardware I/O library. That is how all .NET, all of the .NET environment interacts with the board capabilities, such as peripherals. And Meadow Foundation is drivers for such peripherals and a lot of utility functionality for app development on the Meadow embedded environment. Let's see. Okay, yeah, we have that later. Actually, let's go back. This should go around here so you can see a little bit about how everything connects. the bootloader starts everything. Nutix basically only runs 2 tasks, and we're going to talk about that a little bit more when we delve into it. That's HCOM and Mono. And Mono handles all the app and peripheral driver code through the Meadow Core and Meadow Foundation libraries that I mentioned. And HCOM handles talking to Wi-Fi and Bluetooth and giving the information back to Nutix, which I should have a bidirectional arrow here because Nutix also talks to Meadow Core and sends events and data back. HCOM also handles, as I mentioned before, the connection with your Visual Studio instance while you're debugging or developing, deploying, getting output from console.writeline. That is through Meadow CLI communicating with HCOM, which communicates to the Nutix kernel. Let's go back a couple slides to Nutix. The big first half of the whole stack. Everything is important here, but Nutix is the kernel. It provides us with so much functionality. It's an industry standard real-time operating system that compiles to a very small kernel and provides a POSIX-like environment, meaning from a user's perspective, there's a way to have Nutix on a device and get a shell that looks like SH or Bash, and then you type ls and get a directory. All those things are very similar. It is a very impressive piece of work. At the same time, it's a real-time operating system, meaning its scheduler is able to provide guarantees about how much time it's going to take for a process to return to execution. But from our perspective, the interesting thing about POSIX, a POSIX environment, is that it's easy to port other software to, because Linux is POSIX, for some meanings of POSIX, and everything is ported to Linux and oftentimes other Unisys. So having that being a kernel helps a lot with bringing a lot more functionality to our platform. So from Nutix, we use the scheduler. We set up the board through a lot of low-level APIs and code provided for example, the STM32 by the Nutix project. We have low-level I/O. We have TCP/IP stack. We have some drivers for some Ethernet. I think we use an Ethernet driver from Nutix. That's only partially implemented and we're working on. And memory allocation and file system code is also from Nutix for the Meadow platform. And then we don't, I hope you can't see my screen share keep coming in. And then what we do is remove all elements of the Nutix user space. So there's no shell for you to run. There's no little Unix-like utilities. There's no CP. What you have is an app running in Mono and HCOM also running in the background, servicing the CLI and the communications chip. You've seen that on the diagram also. So our strategy here is to minimize the amount of native code that we have on the platform. The reason for that is generally like almost common sense for a lot of low-level developers, but also accepted and studied that improper handling of memory is the source of the majority of software faults. All of us that have worked on low-level languages have done this. And a huge plus of the .NET environment is that it virtually eliminates memory leaks. It's very hard to introduce them. And it's very easy to create apps whose flow does not create lost resources. And .NET was not always as suitable for this kind of task because it was still, the code size was still large. It was designed for the desktop. It was designed for Windows. But recent changes since Xamarin acquisition really mean that and the merging of .NET Core and old school .NET and Xamarin.NET into .NET 5 and 6 means that the .NET platform is much more committed to multi-platform support, especially POSIX systems. It's much more crucial for a lot of workloads that performance is high, not just on servers but on small devices, because of Xamarin and putting Mono and .NET on Android and iOS phones, and WebAssembly being needs to be small in order to be downloaded off the internet and run in a browser. So all of that are now high priorities, and even another problem that embedded devices have, which is that they can't always afford to have large garbage collection process, which is a side effect of the .NET way of handling memory, is that sometimes it just pauses for a few milliseconds and just takes care of memory, which is fine for a desktop app. It's fine for a lot of server apps. It's not fine for all our users. So the focus recently into making memory management more efficient, so the garbage collector doesn't kick in all the time, is an important factor in making .NET and C# in more of a systems language and a systems programming language instead of just an app programming language. It still has deficiencies, but it's been working very well for Meadow, and all of its direction is always to be able to be an extremely minimal and fast workload that competes with native code execution, but with all the perks of running in a virtual machine, all the safety and all the introspection you can get on it. For this, on the other side of this, the Meadow stack is Mono, and everything from here on out runs on under Mono. So Mono is a .NET virtual machine. You give it a .NET exe file or DLLs, and it just runs the code. It was made mostly for Linux, so again, pretty POSIX compatible. Our porting experience has not been terrible. Obviously, operating systems are very different from each other. And it's a reasonably lightweight runtime that we made fit under 2 megabytes. And it's very well supported for the last few years, especially since it's now officially maintained by Microsoft, and Microsoft is taking its future pretty seriously because it's running the established Xamarin ecosystem and its future WebAssembly attempts at client-side, providing a platform for client-side web development. All of that is good news for us because they need to keep things optimized and they need to keep things light. And HCOM is, as I mentioned before, it's used for it's used for a lot of the data transfer within the Meadow board. All of the data, all of the TCP/IP packets, the IP packets traveling from the ESP32 to STM32, all the data is handled through there. As is all queries and set and attempt and commands, any commands for any queries for configuration, any commands to start or stop the device or reconnect. All of that is handled through HCOM. Same for data transfer between Meadow CLI and the Visual Studio extensions and the device. Everything goes through HCOM. Request to reset, request to write a file, including the file data itself, goes through HCOM. So a very valuable part of our infrastructure that was completely made by a very talented OS team. I think it's mostly Mark's work or Peter's work. It's either. Thank you so much, Mark and Peter. I think they did most of it. I don't know who did most, so sorry. And thank you. And sorry. And finally, now that we're in .NET land, we switch over to using .NET libraries to do all of our work on the device, including I/O with peripherals. That is the advantage to the end user. C# is a modern language that is fast, easy to use, supported by a wide variety of great IDEs, has extensive libraries, very well represented on the internet. So we provide this .NET world, all of this .NET world for everyone, and we provide a way to handle low-level low-level I/O and peripherals in a .NET way. So we try to make it as easy as possible for people to just plug in a component and start using it. Not have to worry about memory. We provide a lot of utility code for people to use. I think I have a tab open of how just a sample that I was admiring earlier is a few lines about setting up like a graphics device and like actually writing on it. Is how a lot of people know how to code in web development and mobile app development and desktop development. But this is very new to have such conveniences and such high-level programming on an embedded device where you can wire whatever you want to it and have it be independent. And Meadow Foundation, or I forget, Meadow Core actually also provides measurement unit safe code for any readings from sensors and any input and output from peripherals that we know is measured in a specific physical unit. So we provide this like extra layer of not having to worry about messing up very human things. So a lot of programming is messing up very human things, and a lot of software development research is finding out those very simple things and offloading them off the developers so that silly mistakes are not made because someone is tired and someone didn't catch the review. And a lot of that can be done by a proper foundation. So the name is appropriate, by having a proper foundation for your code. So we strive to provide that for you. Meadow Core and Meadow Foundation strive to provide a safe, easy, reliable, performant way of handling hardware on the Meadow platform. That's pretty much our summary of the Meadow OS and Meadow platform on the software side. Quickly going through our 1.0 goals. We definitely just want to be reliable, so it's just bug fixing and testing all the way to the end. We're completing our TLS 1.2 support, including the ability for Meadow to be a server and having client certificates. Sorry, actually, that should be server certificates. And also, I didn't realize I switched back to not presenting, but whatever. There we go. And we are going to provide app code linking, which is a way of drastically reducing the size of the .NET binaries that go on device right now. If you've pulled a deploy, you notice it takes a while. And anyone who's developing a heavier app is already probably running into issues with running out of memory and flash storage space. So app linking just puts only the code that's used by your app on the device, so it just removes anything that's not being used, and that helps a lot with the core libraries of .NET. So we're excited to bring that into use, and that should actually make the next release. We're gonna bring a full app lifecycle design into life by 1.0, where an app will sort of be designed to provide what the Meadow device, what it wants the Meadow device to do for initializing, for shutting down, for its main execution, how to handle push events that can command it to do something else, or receive an update, how to handle error reporting, how to handle updates, how to handle rollbacks if the update has failed. And similarly for the OS, we are going to provide a full way for a system OS update to be downloaded, validated, and rolled back on if the update fails. That's always very important in the availability goal of Meadow OS. We don't want to get stuck anywhere. We don't want to get a device stuck on the field because the update failed, because it didn't download correctly, or the power shut off because the sun's under there's a cloud over the sun. So, and finally, full Ethernet support. In future goals, we want to get on track with .NET. So the Mono runtime does support .NET 5 and 6, and with the .NET 6 release, it supports being embedded on in a way that allows Meadow OS to finally use it. So we hope to get on that train and follow .NET from now on. That includes library optimization, new features in C# and so on. We want to get full ahead of time compilation in the system. That means we will have a code generation platform on the host computer, on the development computer, that compiles almost all .NET code into native code that then Mono sort of executes instead of otherwise interpreting the .NET code. So at the very least, that's much faster math, because LLVM is very, very good at that. But people should expect dramatic upgrades to all-around speed of Meadow once we manage to deliver that. It is a hard project, but we are hard at work at it, and close to having ahead of time compilation support in the runtime. Not quite LLVM, but hopefully in the near future. And another thing about embedded devices, as I mentioned before, like they can't always tolerate large pause times. So we're definitely gonna optimize the current Mono GC to minimize its pause times and provide as much as possible a bound of how long it takes for a GC to go through. And experimentally speaking, explore the possibility of having .NET managed code threads that use only classes that are guaranteed to not be touched by the GC, and therefore can keep themselves from being stopped and paused whenever a garbage collection happens. So if that doesn't sound like it applies to you, it probably doesn't. If you're checking some sensors every few minutes and sending something to the internet, that's fine. It matters for very high resolution peripherals and that cannot handle no input for a few milliseconds or something like that. It does allow us to introduce more peripherals and introduce code that acts in a very responsive way. So that's definitely worth it for the Meadow platform. And thank you very much. I'm gonna be at the Q&A later, so anyone who has any questions, we can talk about it in, I think, 2 hours. Thanks.
Hey there, welcome to DevCamp 2021. My name's Chris Tackey, and I'm here to introduce, or I guess reintroduce since Brian introduced it during the keynote, Meadow for Linux. So it sounds cool, but what exactly is Meadow for Linux? Well, it's an implementation of the Meadow core that runs on popular Linux distributions. It can run on Debian, Ubuntu, things like that. It's designed to target common hardware that you would see in the IoT space, such as Raspberry Pi, Raspberry Pi Zero, the NVIDIA Jetson Nano, NVIDIA Jetson AGX, and BeagleBone Black, those types of devices. So when we say it's based on the Meadow core, what exactly does that mean? If you look at the standard Meadow core, underneath it has a Linux distribution of NutX. Above that, it's got some BCLs. Then above that, we have the Meadow core, so Meadow.dll, Meadow contracts, and Meadow units. And then on top of that, there's the Meadow F7 implementation. Meadow for Linux uses pretty much the exact same stack underneath. It uses the exact same Meadow core, Meadow contracts, and Meadow units, but for .NET, it actually uses the .NET 5 runtime. So we're running just the standard .NET 5 runtime as shipped by Microsoft on these platforms. The next question we should probably answer is why Meadow for Linux? What's the purpose? Well, I was actually working on a project for a Jetson Nano, and I needed about 4 different peripherals. I went online and looked at the .NET IoT code, and there were drivers for I think 1 or maybe 2 of the peripherals, but not all of them. I then took a look at the source code for those peripherals, as well as a few others, and the source code itself was kind of confusing. It was certainly not standard from one peripheral driver to another, so it made it difficult to understand exactly how these things were supposed to be written. Meadow Foundation already had drivers for every one of the peripherals I had, so I had a couple options. I could create .NET IoT drivers for those peripherals, or I could work on Meadow and port Linux to it. I chose to port Meadow to Linux because it made more sense to me. It also meant that the drivers that I was working on would be portable from the Jetson Nano project that I was working on, as well as some other Pi stuff that I've been working on, to the F7. Basically, it was for my own sanity. It lets me work with a single set of drivers for multiple platforms. The added benefit is this also allows for you to write your code and test your code on other platforms. You can test and write for, say, a Raspberry Pi and then move it down to a Meadow. The other nice thing is it allows you to vertically scale. Maybe you start on a Pi and you move down to a Meadow F7 because you realize you don't need that much horsepower. You also want to have something that consumes less energy. So it makes sense to go down to a micro. Maybe you start working on a Meadow F7 and it grows to be too large of a project or requires too much processing power, so you want to move up to a Raspberry Pi. Maybe you're working on some project that you say, I want to do some sort of machine learning and a GPU would be useful. Well, you can move that code directly onto a Jetson Nano or even up to an AGX without having to change anything. That is a lot of the benefit of doing Meadow for Linux here. So now let's talk about how this actually works. What does a Meadow for Linux app actually look like? Here's a quick side-by-side, or I guess rather above and below, look at the two. At the top you see a standard Meadow F7 app. The app class itself is defined with the platform, the F7 Micro. A Meadow for Linux app, the only difference is instead of using the F7 Micro, we use a Meadow for Linux type, and then inside that type it actually takes another type that is the pinout of the hardware that you have, because things like the Raspberry Pi and the Jetson Nano have slightly different pinouts. But really that is the primary difference. There are some other small differences, like you can see here when we're creating this BME 280 we send in an I2C bus, and the I2C bus on the Meadow F7 versus the Jetson or the Raspberry Pi are actually a different index. On the F7, the default when you create the I2C bus is bus 0. It's a default parameter here. When you're using the Raspberry Pi or the Jetson Nano, you actually have to use bus 1 because for some reason, bus 0 doesn't even exist on those platforms. But that's the only difference. Let's take a look at what this looks like in practice on some actual code though. You see here we have our Meadow app class, which derives from app. Very familiar, but instead we're using this Raspberry Pi pinout type for our Meadow for Linux. Otherwise, this looks very, very much like a F7. We have our device. We call create digital output port on that device. And then we pass in the pin into that method for the creation. And this pin collection is a type-safe set of objects that we can select specific to our device. And that device pinout is specific to your hardware. Here you can see the Raspberry Pi pinout, and it has all of the GPIOs defined. And then down here, we have aliases for those GPIOs that give you the pin to GPIO mapping, so you don't have to pull up the diagram that is the pinout to try to remember where all of those pins and GPIOs go. And just like we can use the Meadow core pieces, we can also use the Meadow Foundation libraries. Here you can see we're using the core to create a digital input port, and then we pass the digital input port into a Meadow Foundation push button. Works just like it would on another platform. Here we add it to an array, but then we walk through the array and we add event handlers to all of these push button events, and then we have these handler methods down here that write out to the console, and these write lines just go direct to the console in Linux on either the Pi, or if you were running on something like a Nano, it would go there. And as I had hinted to before, you can also use the I2C bus. Here you can see we use the device object, call create I2C bus, and pass in an index of 1. Has to be a 1 on a Raspberry Pi or a Nano. Then we pass that bus into the constructor for our BME 280, which is a driver out of the Meadow Foundation. Once we have the BME object created, we can party on with that. We call read, we get back a set of conditions. We can then take those conditions, write them out to the console, and loop forever. So even with all of this coolness that I've described, it's important to understand that Meadow for Linux is right now just an alpha. I wouldn't even consider it a beta. What works today? Well, digital output ports work. Digital input ports work. Currently, these are using the sysfs driver, so it's got limitations. You can't use interrupts, you can't use resistors. There are plans to move it to a character driver, which will allow us to get interrupts and resistors and things like that, but that is not yet done. I2C is working, as you've seen, but SPI bus does not yet work. Other things are coming up. You can keep track of the status of those on the repo in GitHub. I'll put up the link for that here in a little bit. But what I really want to show you is a neat thing that Meadow for Linux allows, and that is container support. Wilderness Labs is now maintaining a public base image of Meadow for Linux. It's at this address. I've put the address in Docker Hub up on the screen. And here's an example Docker file to run a BME 280 application. This is actually also up in Docker. So the Docker file is, looks like what, 7 lines of code? And this last line, Docker run with the device, and then the Wilderness Labs BME 280 sample. You can run that on a Raspberry Pi today that has either Docker or Podman installed. As long as you have it wired up to a BME 280, this will work. We've confirmed that it works on the Raspberry Pi 4 and the Raspberry Pi 02. Let's take a look at this in action. First, let's run the application just right in the OS using .NET. I've already built this, so it's in the release. You can see it's a .NET 5 application. In here, we have a bunch of results, some conditions, shows the temp, humidity, and barometric pressure. For reference, I've thrown up the fritzing diagram of the wiring for this. Now, I also said this can run in Docker. So let's call Docker. We're going to tell it we want to expose the hardware device, the I2C1, to the container. And then we're going to run the Wilderness Labs BME 280 sample image tagged with 0.2. And here you go. We are running actually inside a Docker container with access to the hardware on this Raspberry Pi. But wait, there's more. Since we have a Docker container, we can even do Docker Compose. Simply call Docker Compose up with our Docker Compose file, and here it brings it up. If the application dies for any reason, Docker will bring it back up for us, effectively acting like a watchdog. The Docker Compose configuration file is quite simple. You can see it here. We tell it that Docker should always restart the application if it dies, and always expose this I2C device to the container. Alright, so what's on the roadmap? As I said before, we're going to have SPI coming soon. I also want to convert the digital inputs from sysfs to a character driver so we get those resistors and interrupts. After that, we've got a few different ideas. Might work on a display where we would output to a GTK window so we could effectively simulate what you would do with an SPI display or an I2C display. Also want to implement the PWMs, maybe serial ports, and other stuff. Open to suggestions. Go ahead and leave comments out in the repo. You can also get a hold of us on our public Slack channel. Meadow for Linux is open source using the Apache 2 license, which is the same as Meadow Foundation, and it is available on GitHub at the address you see now on your screen. Please download it, take it for a spin. If you're interested in contributing, by all means, go ahead and clone the code and start working. I hope you enjoy it. Hope this was informational. Thanks for your time.
Fantastic. Thank you, Chris.
No problem, no problem. I'm seeing that we've got at least one question here asking about if you could use Balena to manage it. I honestly am not terribly familiar with Balena other than their Etcher product, which I do use all the time to write all of my images. You could, if it allows you to manage applications, it absolutely would work that way. Really, Meadow for Linux is just a framework that runs inside of a single process. So anything that manages an application or a process on Linux would work for managing these.
Fantastic.
Yeah, I don't see any other questions. I'll be around for the Q&A later this afternoon, so if anybody has more, they by all means bring your questions there.
Thank you again, Chris. And now we're going to go back to Brian and learn a little bit more on the hardware side of things. And you're going to learn about PCB layouts.
Hello, folks. Brian here, and welcome to this talk. This will be a session. This is part one of a three-part talk on creating custom PCBs. And this first one will be about how to create, actually, or how to capture a schematic, how to design a schematic for PCB. And then in the next session, we're going to do layout. And then once we've got that, and that's the physical board layout. And then after that, we're going to talk about how to assemble these and have practical ways to assemble them at home. As with the other sessions here at DevCamp, this is focused around Klima. In fact, we are going to spin part of the Klima custom PCB. This is the overall schematic design, and in this is just an introduction session and to get you started. And we're gonna add this BME 680 or 688 temperature, pressure, humidity sensor. Also does air quality, and then we're also going to do solar input. So we're going to do a sensor and power, which is a pretty good example of a general IoT solution. You have pick up some sensor stuff, take some readings, also maybe power off a solar panel, and so it'll be a good session to get you introduced to creating your own boards at home, and we'll get you started there. Now, the first thing I actually want to talk about is maybe why even create a PCB board in the first place? Why bother spinning a custom board? Because you can certainly prototype, you can breadboard at home and whatnot. But these two images are a good example of actually why you might want to do this. Of course, as you go to production, you're going to have to spin a custom board no matter what, right? Like that's when you're creating an end product, then it's really necessary for it to in order for mass production. But it's also oftentimes it's easier for prototyping than maybe doing something like what we see here. So typically when you are prototyping, the first step is to create a breadboard, a breadboard solution, something like this, and then as you continue it on, you might start soldering things together in a more sort of permanent way. And the challenge with this is that when you're actually doing this, you'll find that the routing and layout on this is pretty hard. Wires going everywhere. There's a lot of things to solve. And I find that these days with the PCB supply chain being what it is, it's so easy to just spin up a PCB and then order it to fabrication, and you get it a week later. And I find that just to be really a lot easier than trying to sit down and get the soldering gun out or sort of soldering iron and putting things together this way. It's also much more reliable. In when you're working with prototypes and breadboards, oftentimes you're solving problems in which you're debugging and you're like, oh, the ground wire's loose. And if you've got a custom PCB, that's not really a problem. So let's talk about the prototyping process overall, because I think that's important in building. When building a custom PCB, it's really about moving through the product design life cycle, and part of that is putting together a prototype that solves your challenges. And I always tell folks, look, the first step about prototyping is you need to take a look at your overall problem and you need to break it into pieces and solve each one of those pieces and then put them together. And as you're solving them, I highly recommend using modules, pre-built modules that you can get off of SparkFun or Adafruit, etc. And oftentimes, even the most complex designs are really just a bunch of simpler pieces put together in sort of aggregate. And I mentioned these modules. These modules are a great way to start prototyping, because what they've done is that they've taken the essential piece that you're going to work with, say a motor controller or a sensor or something, and then they've added the requisite components that are needed in addition to that particular component for that component to work. And then they put a header on there, and then that is easy for breadboarding, or you can put that in your own, even in a custom PCB by just putting a header on there. And a note about when sourcing or buying these components, most of the time what I like to do first is to purchase from SparkFun or Adafruit and get these components, because they are really optimized to be high quality, and these folks, both of those companies are really fantastic. They build quality components, and there's a lot. They take a lot of pride in their work, and I rarely have them fail on me. On the other hand, there's a cheaper way to do that, which is to go to AliExpress or eBay or Banggood, and you can buy these things much cheaper and typically in higher quantities. And the challenge with those is that they are optimized for price, not quality. So if you do purchase them, make sure that you purchase quite a few of them, and or more than one or two, and then know that some of them are just not going to work, and that's just part of the game. Now, when you're designing a PCB, I mentioned this before, but there's basically 3 or 4 parts to it. There's 3 parts that we do, and then there's something that is typically done elsewhere. And the first part is laying down the design. That's the schematic, and that's also known as schematic capture. And then when you do the actual PCB layout, that's called PCB layout or PCB design. And then you send that design off. You send off Gerbers, which are drawings, which your design tool will create. You send those off to a fabricator, and then they fabricate the PCB, and then you get that, and then you can assemble, and that means putting down solder paste and then your components, and then heating them up until the solder melts, and then everything welds to the board. And you can also outsource that as well. But for most boards that you're going to be building that are Meadow IoT, most of those can be done at home pretty easily, and we'll talk about that in a later session. And when you're actually creating these PCBs, you'll use a tool that's an EDA tool, and there's a number of them that are either free or cheap or accessible in various ways. The one that we're going to be using today is called Easy EDA. You can find that at easyeda.com. And I find that to be just a really nice, easy to use, very powerful EDA and EDA tool. And it, for the most part, does exactly everything that I need. And I have run into very few limitations with it. So it's a really great, it's a good product. Other ones notable mentions, Fritzing is one that allows you to sort of takes a different approach, and it allows you to lay them out from a breadboard perspective, which is kind of interesting. But the development on that has been kind of spotty over the years. It's always kind of a question of whether or not it's actually supported right now. And then KiCad is the one that we use internally for our Meadow modules. Now that's a high-end, it's a high-end EDA tool. High-end in the sense that it's got a lot of features. I find it a little challenging. I don't love the UX, but it does do some things that other stuff, that maybe EasyEDA doesn't quite do. But for the most part, I think EasyEDA is great. And a new one on the block is Flux.ai, and that one is still kind of in its early stages, but it looks like it might be pretty good. So that's one that I would recommend trying. And then Eagle is one that I mentioned just because it is reasonably priced. It used to be free, but it was acquired by Autodesk, and it's not totally free anymore. I will say I don't love Eagle. Neither does our engineer, our electrical engineer. The UX is really frustrating, and it hasn't really gotten any better since it was acquired by Autodesk. And then of course there are a pile of other ones that cost a lot of money, and probably the gold standard one is Altium. Altium is probably the nicest EDA tool there is, but it also costs something like $30,000 a year, so it's pretty expensive. But like I said, today we're going to use EDA, and without further ado, why don't we just jump into it? So here's Easy EDA, and I've already logged in. And the first thing I'm going to do is create a new project. So I'm going to say this is going to be DevCamp 21, and we're going to do Klima, Klima simple. This is going to be a simple version of Klima. Very cool. And then it automatically creates a new schematic file for you. So if you hit save, you'll see it shows up. And we're just going to rename this. We're going to call it schematic. Schematic. Klima simple. Okay. Now, a real quick tour of the interface here. This is our editor area. This is our project area. And then on the left, this will change depending on what you've got selected on the left navigation here. So you could be project, or it can be design information. These are standard components, and then this is the component library for more components, so that are sort of specific components, etc., will be up in the library, and we'll talk about those in a bit. And then there's some tools over here for laying out your design, and some drawing tools. And the first thing that we want to do is we're going to add a meadow board. And in this case, we're not actually going to add the meadow itself, but really just the meadow IO. And I'm going to come down here and I'm going to search for meadow. And this is a good time to talk about this library. So when you're adding parts, if it's a simple part, oftentimes like a capacitor or resistor, I just grab them from here. Otherwise, you can go in here and you can search for the specific parts. And they're organized by symbols and footprints. Symbol is the schematic symbol, and then a footprint is what goes on the PCB itself. And the classes are somewhat interesting. So in this case, this is the group in which they belong to. So user contributed is a place where you'll find a lot of components. And then LSC, SC are like official components available from LCSC, which is a big Asian component supply house. And those are the symbols in there, and the footprints are generally high quality. And the ones that are user contributed are also generally high quality, but you often have to just double check the footprint. I've found things that I've had to fix here and there. In this case, I'm going to find Meadow and Workspace because these are things that I've created. So if you open this up, you'll find Meadow and user contributed. But as you create parts, as you create a library, you'll find them in Workspace. And we'll explore this a little bit more later. So you don't have to remember everything now. But I'm going to choose a Meadow F7 V2 Micro PTH. That's a through-hole PCB through-hole wing. And this is a symbol that I've created specifically with the intention of it being used in wings because it already has the outline of the Meadow board. So we're going to grab that and then we're going to do place. So I'm just going to put that here. And then I'm going to add a BME 680. So I'm going to go in and search for BME 680. And this is a good case in which you can see there's an official part, which is great. You see the symbol, the footprint, and then even a picture from LCSC, and then also their price for it, which is very nice. And then there's a bunch of them that are user contributed. And again, you'll see as we kind of click through these, some of these, like, is that a good footprint? I don't know. It doesn't really have enough area for the solder paste, right? If you look at this one, it has kind of a wider footprint for the solder paste. So that's the kind of thing that I'm talking. I mean when you look at the user contributed stuff, you really have to kind of double check it. So, and some of them are for, like, these are obviously for this one here is for a breakout. So this is maybe like an Adafruit bar breakout or something. I'm not really sure because it doesn't say in here. But in this case, we're going to start with the official part and we're going to place that. And this is a good time now. Okay, so we've got our basic components down, and now we need to figure out, okay, what's next? So this is a good time to introduce data sheets. And data sheets are your friend. So let me switch over to the data sheet here for the BME 680. And these data sheets are easy to find. If you open up a browser and if you just Google BME 680 data sheet, you'll find them. But this is also a good time to introduce you to one of my favorite component search sites, Octopart. And Octopart is a fantastic way to find components and get their prices. It's very similar. There's another one called OEMsecrets.com. This is another one that's similar to Octopart and also very good. But I personally find, and I know some people prefer OEM Secrets over Octopart, but I prefer the UX on Octopart. So if I go in here and then type in, search for BME 680, you see that's a breakout, that's a breakout, that's a breakout. It's, when by breakout, I mean a module that has the sensor and additional components. But I just want to look up the actual component. So here it is. And you can see here, this has who has them in stock, what their prices are at what scale, and then also a link to the data sheet. So this Octopart is an awesome way to find parts, and you can also browse by category and whatnot, which is a nice way to discover parts. So switching over to the data sheet, when you're doing PCB design, when I say that the data sheet is your friend, I really mean that. When you're going to spend a lot of time in the data sheet, and the data sheet will often have, almost always will have like some sort of use diagram. In this case, in the BME 688, it's called a connection diagram. But like looking up, here's another. Here's a data sheet for the SI 7021, which is another atmospheric sensor, and I use this sensor elsewhere. I use this in a beehive, but you can see the application circuit for this diagram is actually very nice, and the BME looks very similar. You've got this is it's connected to I2C, which is a 2-wire bus. You've got clock and data lines, and then there's pull-up resistors, which we'll talk about in a moment, and then there's a decoupling cap here, and then it's connected to ground. So this is a great example of a good data sheet in an application circuit diagram. The other thing about this data sheet is that it also has for each component, it has sample part numbers and whatnot. Again, this is very nice. The BME data sheet is a little more rustic, we'll say. And BME 280, 680 is a little bit more complicated of a sensor. You can hook it up either I2C or SPI. And in this case, we're going to use it as an I2C sensor. Now, SPI is great for high-speed buses for like displays and stuff, but for sensors, I2C is great. And in here it says, for the I2C connection, which is what we need, it's recommended 100 nanofarad for cap 1 and cap 2. That's over here, and that's connected to VDD, which is power in, and VDD IO, which is also the power in. That's the level of the IO. And it says use a 0.1 microfarad, 100 nanofarad. Those are decoupling caps, and capacitors are basically like fast-acting batteries. They store voltage. So you hook them up to power and ground, and then they charge up to whatever voltage that is. And then as the voltage drops, it releases voltage. And so what happens is if there's a lot of things happening in the circuit drawing power, these store voltage so that it can smooth out the power in and make sure that this has constant smooth power, which is super important for digital circuits because digital circuits are they're sensitive. They have an operating range and they want to stay within that. And it's so-called decoupling caps because it decouples this from the rest of the power draw on the circuit. So we'll add those. So we need 2 caps. And then moreover, the value of the pull-up resistors R1 and R2 should be based on the timing, interface timing, and the bus load. A normal value is 4.7K. And those are the pull-up resistors for the I2C bus. So let's talk about that real fast. So let me go to our documentation, and let me show you what an I2C bus looks like. So an I2C bus has a clock line and a data line and then multiple peripherals, and they're controlled via addresses. So you send messages on the bus and you prefix them with an address. And then there's these pull-up resistors. Now, pull-up resistors are interesting. They provide a default value for a line. So in digital circuitry, we have 2 values. We have either high or low, on or off. And in our circuits, in CMOS level circuits, it's either going to be 5 volts or 3.3 volts for high and 0 volts for low. And we want to make sure that the signals are going to be either one of 2 of those values. We don't want them to be floating because they might be an indeterminate value. So if we don't put any pull-up resistors on here, what happens is that these lines are known as floating. And what a pull-up resistor does is they allow a trickle of electricity from something, from in this case from power, which means that it's giving just a little bit of electrons that are at 3.3 pushing value onto this bus, which means that their default value is high. Now this can be pulled down very easily because these are very high value resistors, which means they only let a trickle of current, and so it's easy to pull it down if you need to. But this provides a default value, and so you need that on an I2C bus, and so that's what this data sheet is telling us. And typically they are 4.7K, and that's kind of a magic number for I2C buses. As you add more devices, you might change that, but it's a good place to start. And then it says, finally, a direct connection between CSB and VDDIO is required, and that is the chip select, and that is that's for SPI. So the way that SPI works is you have multiple lines. You have a data in and a data out line, and then instead of having addresses, you have these chip select lines. And whenever you want to talk to a peripheral, you pull a chip select line down. You set it to ground, and whatever peripheral has its chip select line pulled down will then listen. And so instead of addressing, and that can be faster, but it takes more I/O. I2C, on the other hand, uses addressing, and if you pull this chip select line down, then it puts it in I2C mode, and it knows just to listen on I2C. So that's basically it. This is not a high quality drawing in this data sheet, so it's hard to know what's connecting to what and what's actually jumping over. This is a connection where this is actually going underneath the line. But we know that this is basically what we need. So we're going to go back over to Easy EDA. And the first thing that I'm going to do is start with power and ground. So I'm going to go here and I'm going to hook up 3-volt 3. And when I hit W for the wire tool, and I'm hooked this right to ground. And there we go. Now you got it. And the other thing that I want to do here is I'm going to rename this, because whenever I have power, I want to know exactly what kind of power it is, because oftentimes I might have multiple power buses. And I'm going to change my alt snap so that I can move this around. So right now the regular snap is on 5, and that's not as much control as I want, but if I hold down alt, I get this alt snap, and then I can move it a little bit more with more precision. So there's power and ground on that, and then I'm going to hook up ground right here, and again hit W for wire, and then wire up that. All right, so we've got power over there, and we're going to put power over here again, and then we're also going to do ground. And now let's hook up power. So VDD and VDD-IO, these are separate because sometimes on some sensors you can put power them with like 5 volts, but then the I/O level is only going to be 3.3 volts. In this case, we're dealing with 3.3 everywhere, so we're gonna hook up power to both of those. And those, I think it hooked up directly. And now we're gonna hook up ground. So I'm gonna run this out, and I'm gonna run it there, and just gonna do a little cleanup. Now, we also remember that needed those decoupling caps. So if I switch over here, it says VDD and VDD-IO both need these two 0.1 microfarad caps. So I'm going to go here and I'm going to grab a capacitor, and here it gives me different sizes. I'm going to do 0603, which is about the smallest capacitor, the smallest size that I will ever use in a hand assembled board. And if we pop over to our developer portal and we go to hardware circuits, there's SMD packages and sizes. You can see here 0603 is still pretty small, and that's in an imperial size code, and that means 6 mils or 6/100ths of an inch and 3/100 by 3/100ths of an inch. Very small. Anything below that is too small to really like work with. So I want an 0603 0.1 microfarad capacitor. So I'm going to go to Octopart, and I'm going to search for that. I want a 0.1 microfarad capacitor, 0603, And I'm going to just use Yageo because that's a brand that we've standardized on internally for capacitors. And we just have a bunch of these. So here we go. 0603, 10%. 10% tolerance, it's fine, capacitor, and it looks like there's a bunch in stock. So that's fantastic. There's other details here about like, you know, X7R versus X5R and whatnot that are not really important. You can look those up, but for the most part, you know, it doesn't matter on the designs that you're going to be doing. The one thing that might matter is that when doing capacitors, you want to have a capacitor. Rule of thumb is that the voltage on it, the voltage it's rated for, should be about twice or more of what you're using. In this case, we're using 3.3 volts, so we need 7 volts roughly. This is a 16 volt. This is a 50 volt. We probably don't need 50 volt. 16 volts fine. So this is the one that we're actually going to use. And as you can see, there's a gazillion of them in stock. So this is the one that I'm going to grab. So Yageo, and I'm going to go over here, and then I'm going to say manufacturer, Yageo, and then I'm going to paste in the part number. And this will be available now later on in the bill of materials, the BOM. You'll see all the parts that are involved in this, and that gives us our part and the manufacturer. That's important to put in here because later on when you actually go to source the bill of materials, you'll want to make sure that you know what all the parts are. So we're going to need 2 of those. So there they are. I copied and pasted, and so one of these goes to VDD, one of them goes to VDD-IO, and then they both go to ground. Remember, it's like a battery. So that's good. We got that in, and I want to just make this a little more clear here. So I'm going to do this. Cool. And then going back to our diagram, we have SDO. So this is, it's hard to see, I2C address bit 0 or 1. Is it ground? Is it 0? And VDD-IO, pulled it up, is 1. So remember in I2C that the devices, the peripheral devices, are addressed. And this allows you, by making these modifiable, it means you can have 2 of these on the same bus without having to do anything special. You just pull one up and pull one down for different address bits. In this case, I'm going to just pull this down because we're going to give it the first address. And again, we'll do just a little cleanup here, just to make some more room. Let's make this all the way over to there, and wire those up. Cool. And then just clean that up. Cool. So this side is now wired up. Now we got to do the right hand side, and it's ground, chip select, serial data in, and serial clock. So I'm going to first, let's toss a ground over here. And one thing to note is that anytime these things share, anytime a net, these wires are all nets, and anytime they share a name, that means they are going to be physically connected. But instead of making wires go from here and then around and then, you know, like this sort of thing, and making your drawing really a mess, we can just name them. Similarly, we can put these ports on there. So this is a net port. So we're going to put one on here for this, and we're going to call this I2C data, and then we're going to do another one. And by the way, space rotates these around, and this is going to be I2C clock. Copy both of those, and we're going to connect them up over here. They're in that order here, so connect them. Oops, I'm not sure. There we go. Ooh, what's going on? All right, connect these up and then pull them out just to show that there's a connection. These are now on the same net, and we didn't have to run a wire or a line all the way around. So that simplifies it. And then going back here, chip select says Finally, a direct connection between chip select and VDDIO is required. So that basically says, hey, put this into I2C mode, always listen, rather than SPI mode. So we're going to wire that up. And then let's wire up this ground. And we're going to move these over just so it's kind of a little cleaner. Ground. There we go. So that is effectively most of it. The final thing that we're going to do is the pull-up resistors for this bus. So we're going to go in here, we're going to copy these, select them here, and then we're going to grab our 3-volt 3. And now I'm going to grab resistors, and these are going to be 4.7K, 0603 again. These are resistors and capacitors are collectively known as jelly bean components, and they're not very specialized. There's a lot of great brands that make them. So we're gonna go, now I want an 0603, 4.7K Yageo resistor. There we go. So that's what I want. So I'm gonna go search for that. Here we go, 1% tolerance, 0603, 4.7. And there's a gazillion of them. So this is a good one. This is it's one that we use all the time. So grab that and switch over, and Yageo, and then the part number. And over time, you'll basically come up with kind of a library of your own components that you use all the time. And when you're building, you wind up buying these things on reels because you use them all the time. Like we always use 4.7K resistors and 10K resistors and 0.1 microfarad caps and stuff. So we've got like them hanging on the wall on pegboard. So you'll kind of get a library of your own favorite components. So here we are. We're gonna wire these up to 3-volt 3, and again these are our pull-up resistors. Let's make that a little cleaner. Boop. And oops. Let's try this again. Cool. And then finally, I just want to add a couple of labels. So this is going to be I2C pull-ups. And we'll go over here, and this is going to be our BME 680. And then this is our Meadow. Okay, now the last thing that we're going to do is that there's all these unterminated lines, and if we went up and we tried to convert the schematic to PCB, it's going to say, you want to check the nets first? And we're going to say yes. And over here in the design manager, it's going to give us flags for all these and say, hey, you have these, but they're not connected to anything. And that's not good. So we go up here and grab this X. There's no hotkey for this, even though it's a really common tool. And we're going to go in and terminate each one of these pins. Okay, so now the basic design's done. There is one other thing that I wanted to do. I want to add our solar jack, and I'm gonna go look at the Klima doc, the design, to figure out what that part number is. It's over here. And all this Klima's totally open source, so you can actually find this schematic in the Klima repo, as well as the Gerber files, the output files, so you can make. Oops, I must not have copied it. So you can you can make Klima on your own. Let's try this again. Let's do this. Let's footprint. Oh, here, let's grab it from the name. Okay, now let's go search for that part. And this is a standard 2 by 2.5 millimeter jack, connection jack. And I'm going to look through. So these are user contributed. So I'm looking here with sort of a critical eye of what I want to use. This one is probably the one I'm going to use. This one actually looks like it's super high quality, and I think that's the one I used before. Some of these are, like weird. Like I'm not going to use that. But here's this one, and here it is, and the connections are on the right side. And for whatever reason, I want these on the left. So I'm going to use this tool here, and I'm going to flip it horizontally. And this is the ground on the outside. This is positive on the inside. So we're going to do ground and hook this there, and then just hook those together. And then finally, we're going to do a net port on this, and this is going to be, we're going to call this 6 volt solar, because it's going to be 6 volts, what the solar panel gives off. And then we're going to hook that up to the 5 volt rail, which is a way to power Meadow from a solar panel, or, like a USB or whatever. USB power. You can plug it into USB, obviously. So there we go. So that is our schematic, more or less, design. Let's say solar in. And there's other things, you should go and update your drawing information and whatnot. But let's check it out. So let's go up to convert schematic to PCB, and there it is. The nets were all good, and then it's time to lay that out. So that's exactly what we're going to cover in the next talk. So I'm going to stop here, and we'll jump into the next talk in a moment and cover that. So thank you very much. Hey, all right. Welcome back. This is session 2, part 2 of our creating custom PCBs walkthrough. In this session, we're actually going to do the PCB layout. In the last one, we designed the schematic for our Klima board. And then after this, we're going to have a quick tutorial in how to assemble them, put them all together. So we're going to just get right into it. Let me switch over to EasyEDA, and here we are. This is where we left off last, and just a quick sort of intro. This is, again, where we're going to do our design. This is our tools, and then these are layers and objects, and this is kind of a super important thing. This is where we can look at our top layer, our bottom layer, silk layer, which is where labels go, etc. And then we're going to look at this stuff a little bit later. The first thing that I want to do is I actually want to, this grid style just drives me nuts. So I want to change it to dot, and so much better, so much cleaner, much easier to see. The next thing is that EasyEDA automatically puts in what it thinks is going to be your sort of minimum, or a guess as your outline, and this where all your components would fit. And I'm not sure how it calculates this, because this is obviously very large, and I'm going to delete that because we have started with a Meadow wing, and when we imported the Meadow through-hole wing symbol, it automatically came with this footprint, which already has the wing outline. So it's a nice shortcut. So we're going to use that as the outline. And then the other thing that I want to talk about a little bit is our grid. Now, when you first come in here, it probably will say units millimeter. And the grid size will be a little bit weird. It says 2.54 millimeter and 0.127 millimeter. And that's a little bit, those are weird. That's a little strange size. And that's really because of legacy reasons. Electronic design was really was really invented in the United States, and the United States uses inches. And so if we switch over to mils, you see that's 100 mil and 5 mil. And mils are thousandths of an inch. So if you look at breadboards, they're or these headers, each one of these are 100 mils or 1/10 of an inch apart. And so that is unfortunately just kind of the standard size of a lot of things. So when you're laying out components, you'll often work in mils, but then when you're working on your outline of the board itself, I often switch over to millimeters because I like to design my enclosures and my products in metric. Otherwise, it's really hard. No one likes to work in imperial. It's just silly. So anyway, I want to modify this. I'm going to do grid size is 100, but my snap size I'm going to change to 10, and my alt snap is going to be 5, so that's good. And then I'm going to align this. I almost always do this. I align my bolt to the origin. And then this just gives me a nice way to sort of measure everything off of your bolts. And again, this is a product design thing. And the first thing that we're going to do is we're going to lay out our components. And this is generally when you're doing your PCB layout, that's the first step you do. And you start by laying out the most important components or the components that have the greatest constraints. Like for instance, let's say this was a chip that had USB lines. I might lay this out somewhere right up here, and then I turn it so that the USB lines went to the USB connector. And then what you do is you lay out the components that are supporting those important components, and then you work from there. When we go to route, it's the same sort of thing. Now I know that this thing is going to go up here, so I want to put this here, and I know that it goes this way. This is the back end of this connector. So I'm going to put this up here, right on the edge. That's my solar panel connector, and maybe I want to just move it down and give a little more headroom up here. And then I'm going to place my BME 280 sensor. I'm going to have it directly in the middle of my board. And I'm going to align it kind of near my I2C stuff, just for the heck of it. Now, I also want to align it. I want to think about the routing a bit when I align this. And you can see the clock goes here and the data goes here, and they would cross over. So I've got some options. I could turn it this way, and then I could run lines underneath. Or even better yet, I can turn it this way. And now when I route, it's going to route. They'll route, you'll see, much easier to route it, this way, even though I'm making a mess of it there. So we're not going to route yet. We're just going to place some components. So the next thing is I've got my pull-up resistors for I2C. And you can see there's these blue lines. These are called rat lines, and these show unconnected things. And the first thing I want to do with these is there's a lot going on. So I can go over to Design Manager, and I can see my nets. And I'm going to hide the power and ground. And that, all of a sudden, see, that is a lot easier to understand. And we're going to route power and ground last. And they're basically, everything has power and ground. If you have those rat lines shown, then it makes a mess of things. So let's first get our resistors in place. So this is the data resistor. I hit space to rotate, and I'm going to put that one here. And then I'm going to turn this one and put this one. That's the clock line. And so now the line is going to go right through. And the next thing I'm going to do is I'm going to line and size these labels. These are really big. I don't like them that big. They take up a lot of space. So I'm going to change this to Demi Light. That makes them much smaller. Rotate this one and change to Demi Light. Great, and let's do the same to this one. Cool. Now we want to place our capacitors. Now recall from our design, these decoupling caps, C1 goes to 8 and C2 it goes to 6. We want these as close to those leads as possible because we want them to dump their electricity into that component before dumping it into the rest of the board. So C1 goes to 6. So we're going to put the 3 volt 3 and 3 volt 3 right next to each other. And we're going to line this one right next to it. And then again, let's change these to a smaller font and rotate them and place them in a reasonable place. Now, one thing to note about these prefixes is that you generally want to align them. You want to align them all in 1 or 2 directions, which means that they should all be facing this way or like this way. And what that means is that when you're looking at the board, you only have to rotate it once to read any prefixes. Ideally, they all point the same way. So you don't have to rotate it at all. You just keep it in one spot. It's not always practical on very complex or dense designs. Okay, so we got that. And then this one has a prefix. And you know what? I know what this is. I don't actually want to bother putting a prefix on the board for this. It just feels, it feels like too much. Also, something that you notice, I keep accidentally selecting this board, and it's real easy to like, oh, I moved it around. So one thing that's super helpful is to lock it. Right click and lock, or go over here, select it and say locked yes. And now I'm not going to move it around. And there it is. So I'm going to select this, and I am going to say no, don't display the prefix. And the same on this one, because even though it won't show up anywhere, I just don't want it there. Just a, I guess, OCD maybe. Okay, now I need to actually route the traces. I need to actually connect everything up. And again, you do your most important lines first. So in this case, there's not actually a lot of stuff going on here, but if we had other supporting components out here for this BME 280, I still want to do my bus lines first. So I'm going to hit W or select this line, this track here, track or wire. And then I'm just going to select it and then route it over like so. And there's 2 things to think about when routing. The first is electricity is like water. You don't want to make a river that's a 90-degree angle. And this, the reason why is that when the electrons come pushing through here, they kind of hit this wall and they crowd up over on this corner and they're not here. They like 45-degree angles or even rounded stuff. So this is much better than that. So don't do 90-degree angles. The other thing to know is that you don't want any acute angles either. So let's say that this actually had to go to another I2C device. 90 is okay here. This is not okay. And the reason why is that if you're creating this PCB using acid etching, the acid will this will create an acid trap in which a blob of acid might get in here and get trapped and etch out much more of this than you want. The best for something like this is actually you would do a line, run that, and then help it out with a little 45 on each side. And that's a real clean connection. Obviously we don't need that here. Okay, so that's routed. Now we're going to run our power. So 6-volt solar. So we're going to route this up to here and then route it to here. And one thing I want to do is that this is where all my power is coming in. I want to make this bigger. I'm going to make this 30 mils. And 10 mils is actually fine, but I like to overbuild things a little bit. And you can look that up. You can look up your, based on your copper thickness, these are going to be 1 ounce, what they call 1 ounce copper thickness, which means every square inch will have 1 ounce of copper. That's how thick it is. You can use ½ ounce copper. That's another common one. But you can look up on the internet, like how much power can be moved over what size of trace for your copper thickness, if you want to be real technical. But for me, this is totally fine. Even a 10 mil would have been fine. But it is nice to beef it up. Okay, cool. So our routes are in. We didn't use the auto router. That will only make a nightmare of your design. And we've got everything routed except for ground and our power. So I now displayed those nets, and you can see, oh yeah, I still got to route those things. But we're going to do something different for those. We're gonna do a copper pour, which means we're going to fill all this rest of the area with copper that's going to be ground or power. And we're going to put a power plane on top and a ground plane on bottom. And the reason why is you always want a ground plane opposite of your components. And this will become more apparent later on when you start doing controlled impedance and whatnot. But basically, the ground plane underneath serves as kind of a sink for errant signals and things like that, and capacitance. We'll explore that in a more advanced tutorial at some point. But just know right now you're going to do on a 2-layer board. It's going to be ground on the bottom and power on top. And that brings up another thing that we should talk about is multi-layer boards. Most of the boards that you spin are going to be simple 2-layer boards. That means they've got a fiberglass core, and you've got copper on top and copper on bottom. And the copper is what constitutes a layer. And that's where your signals and your power and stuff is routed. Now, some boards are very complex, and the routing requires multiple layers, and either because there's controlled impedance or because there's just not enough room on the layers for all the routing, because there might be a lot of signals. The Meadow board, this is Meadow Core Compute module here, for instance. This is an 8-layer board, and it has controlled impedance and high-speed signal routing and stuff. It's very complex. There's a lot of design considerations that go into this little thing. You don't have to worry about that generally when you're designing a breakout module for a Meadow or most of your IoT designs. However, if you need to do that, if you need to do more layers, it's pretty easy. You go up into edit, where is it? It's in the layer manager, tools, layer manager, and then you can add additional layers. So you can add an inner, if you go to 4 layers, it'll automatically add an inner 1 and an inner 2. And then you can go additional layers, 6, etc. And that adds additional layers. We're going to keep it at 2. And it's just going to be top and bottom. So what we're going to do is pour our copper area on the top. It's going to be power, so we're going to choose 3V 3. Make sure we're on the top layer. And then outside here, I'm going to start this, and this makes it easier to select this layer if it's not, if it's on its, if it's not, if I put it, I could put it right on the outline here, but it would be hard to select. I'd be selecting the other board. And then 3 points, and then right click to close. There's my 3V 3 power plane, and notice some of the rat lines disappeared because they're now connected. And I want to show something real fast. So first of all, because I put this out here, it's easier to select. I'm not competing with selection for that. But if we look at these connections, you'll see something interesting, that they're connected via these spokes. And that's something over here. It's a pad connection, spoke, or direct. And if you look at direct, like, oh man, that looks a lot cleaner. But in fact, you want spoke. And this is really what these are called, are thermals. I've never heard of spoke before, but they are thermals. And that's what you'll find in other EDA tools. They'll call them thermals. And what that allows is a good electrical connection, but it won't sink a lot of heat away. And so when you're assembling this, this will prevent problems during the reflow process, where there's differential heat thermal properties on a component, and like a capacitor might tombstone. That's where it stands upright instead of laying flat. So this prevents that. It also makes it easier to solder. For example, this, let's say we were actually having to hand solder this. If this were a direct pad connection, it would be very difficult with a soldering iron heat this up enough to actually get solder to melt, because all the heat would just be flowing out into this big solder or the copper pour. So we want a spoke or thermal connection. The other thing is islands, and we'll show that in a sec. One thing that I forgot to do is route the rest of our I²C. And something, this is a good thing to see. Notice that these wound up being really big, and that's because the last thing I selected, or last thing I wired up, had a 30 mil route. And you'll notice that these are now conflicting with that pour. So there's a couple things that we want to do here. One is we want to reflow the copper so that it's not in the way. The other thing is that when we're actually doing this, it's nice to, once you have a solid region poured, it's nice to turn that off, the visibility, copper area. It's nice to turn that off so that it's not, so visually you can still route and whatnot without it sort of being in the way. Visually in the way, it's still there. But we need to reflow this copper around those lines. So we can either right click and unselect everything and right click and say rebuild all under copper area, or Shift B. Shift B is your friend. That will rebuild. And this brings up one additional thing, which is on this copper area, you have an option for keep island, yes or no. An island is an unconnected area of a pour. And that looks nice, but when you're doing complex boards, sometimes you'll see like a rat line between, like two things that are 3 volt 3, and you're like, I don't understand, why is that not connected? And it's because that's actually an island and they're not connected. So it's nice to turn that off, and then sometimes I'll turn it back on when I go to make this, just because it looks kind of nicer. But there's no important difference there. Cool. All right, so we've got our power plane drawn, but we still got to do our ground plane, and ground's going to be on the bottom, so we need to switch over to the bottom layer, and we can select this, or we're going to hit B to switch over to that. T for top, B for bottom. And again, we're going to grab a copper area, or we're going to select E for that tool and hit ground, and then again, we're going to pour this out here, and I'm pour it outside of the other one so I can select it without competing for this with the selection of the other one. And I make these, I'm starting from the top out, and I just make them concentric outlines, and that makes it easier to know what's going on. So that's poured, and we're on the bottom layer. That's what we're looking at. We're going to switch back to the top, and now we need to connect our grounds to that bottom layer. And for that, we're going to use a tool called a via. And a via is like a little tunnel. So you can hit this tool, or you can hit V. And I'm going to put this right here. And what that does is that automatically names my via for ground. And again, I'm going to go back to this, and I don't want to see the copper area right now. If I do a V without pasting it on, if I just put it out here, it's not named, and then I would have to go and manually name it ground. But by pasting it directly in first, then it picks up that name. So that's just a little trick. All right, so I've got these ground vias, and now I want to wire this up. So I'll wire this to here and wire this to here. And you might be thinking to yourself, well, you got one via here. Why don't you just connect them to? And that's totally fine for most things. And then not, and not have this via, right? And that's totally fine for most things. It's not okay for decoupling capacitors, because doing that, tying them together, can make some weird electrical capacitance that we don't want. And I don't fully understand what it does, but I just know that you don't want to do them. And vias are cheap. Vias are free. They don't add any money to your board. So you can put all the vias in you want. In this case, we're going to share. Those two can share, and we'll just tie them like this. If this board was, or if this component needed to dump a lot of heat, like maybe it was a power component, maybe it was converting power from a high voltage to low voltage, we might actually pour a solid area of ground and then do a bunch of vias. But in this case, it's not doing anything with heat. One is fine. And then we need to do the same up here. We need to put vias in for the solar jack, and just as before, because this is a power line, I'm gonna beef these up a bit. I'm gonna beef this up to 30 millimeters, or 30 mils, not millimeters. All right, so there we have it. We'll show our copper area again, and we need to rebuild. Shift B is your friend. And there we go. We're basically, where components are laid out and we're routed. And now I want to check to make sure I did everything all right. So I do design and then check DRC, and that runs through all these things. It's also refresh our nets. It looks like everything has been routed appropriately. There's no design rule, DRC, design rule check. There's no errors on that. So our board is good. There's one final thing I want to do. I want to save often, actually. But I want to go to the silk layer, and I want to add some labels to this. So I'm going to grab the text tool, and I'm going to put a label there. And I'm going to change the font. One nice thing about Easy EDA is it allows true type fonts. You can go into fonts management. You can add fonts. And these are Wilderness Labs fonts, Mrs. Eves and Wave House. So I'm going to change that to Wave House. And I'm going to say DevCamp 21. And copy and paste. And I'm going to call it Klima. And then I'm going to version this. And this is super important. Putting a version on your board is really important, because when you're working with your board, you want to be able to just pick it up and know what version that is, because you might change the design, and if you don't know what the version it is, then the pinouts might be different, etc. So this is really important. So there we are, DevCamp 21 Klima V1A. So that is basically, our board is done. So switch back over to the deck. And we're going to talk through a couple more things. So in review, in terms of the rules, ground plane opposite of major parts. Remember, no 90-degree angles, no acute angles for acid traps. And 0603 is really the smallest part I recommend placing, because otherwise they're too small and it's just a nightmare for assembly at home. If you've got a machine or something that does the component placement, then you can use whatever size you want. And in terms of the process, lay out your components first, get them in the right spot, do your high value components first, and then the stuff around them. Hide those nets so that you don't see all the, the power and ground rats. And then don't bother with the auto router. You can try it just to see how badly it will screw up your design. But really, I think of, this is kind of strange maybe, but I love laying out PCBs. To me, it's very meditative. And as you're laying things out, you're actually validating the design and you're thinking through things. The auto router sidesteps all of that, and you'll wind up with more errors in your design, but also the auto router just makes an absolute mess. It doesn't have any intelligence. Maybe as we maybe one day GitHub will do an AI auto router or something, and then the router will make sense. But right now, auto routers are terrible. Don't worry. Don't bother with it. But route your high value lines first, your buses, your differential pairing, etc. And then finally lay your planes, and then do your vias to tie those things together. Now, once you've created a PCB design, once you've done the layout, it's time to order that to fabrication. And in order to do that, you actually output Gerber files, and those are drawings for each layer, and a PCB fabricator will know what to do with those, to how to make a PCB from that. The first thing that I want to show is that if you're, and this is a nice thing about Easy EDA, is that if you're in Easy EDA, you can order your PCB directly from here. If you go fabrication, PCB fabrication, yeah, check DRC, there's no errors, and you can order directly at JLC PCB from here. And we'll talk about these options in a moment. you can either download the Gerber or you can just order straight from them, and then this will automatically bundle up the girders and will create a cart and will automatically add it to your cart and have everything, all the settings in there and stuff for you. So JLC PCB is fantastic for simple boards. They even have you can even do multi-layer boards with them and stuff. But they're really quick turnaround, simple boards shop. If you're doing very complex boards, many layers, and you need to control the stack up and stuff, Rush PCB is a great outfit. They're out of San Jose and Toronto. And they do quick turn PCBs. And then if you're doing, once you start to do production run quantities, there's a number of suppliers. One that we have used with success is PCB Unlimited, and they're based out of Portland. But like I said, EasyEDA makes it very easy to actually order order them. Ordinarily, I hit an OK button, and then you'd see the cart come up, but for some reason it's not working right now. I'm not sure why. But a couple of things to note about that. I want to talk about the fabrication finish options. So when we were over in EasyEDA and we had the opportunity to order, it gave us a finish option, and it was either Hassel or Enig. And Hassel is a hot air solder. It's like an air knife. They blow hot air over it, and they put tin on top, or like kind of solder on top of the pads. And that used to be that used to be what everyone used, and that could make things easier to assemble. Enig is electrolytic nickel immersion gold, and that's a gold finish on the pads. And Hassel is definitely cheaper, and there's two Hassel versions. So if we go in PCB fabrication, you'll see surface finish is Hassel lead or rose, which is lead free. That's a reduction of hazardous substances directed, ROHS, pronounced rose. Always do lead free. Lead free Hassel or Enig rose are what you should choose almost all the time. We choose Enig almost every time, and Enig is arguably a better surface finish. For some components, like very fine pitch components, you actually need Enig. You can use Hassel, but it causes more problems. But Hassel is also a lot cheaper, and the finish looking is different. So this is a board that's finished Enig, and you can see all the pads are gold. I don't have a Hassel board, but the boards would come back with tin colored or silver colored pads. So yeah, Hassel, lead free, rose, or Enig. Whatever one generally for simple boards. For more complex boards, almost always Enig. And in fact, we don't order anything that isn't really Enig at this point. So with that is everything on the intro to PCB layout. And next up, I'm going to show you, okay, so we've ordered a board and they come back from PCB fabrication. Now what do we do with it? How do we assemble that? And that's up next. So thank you for joining me. And I'll see you in the next one. Hey folks, Brian here again, and also shout out to Willis Smith, who helped me put this together. She actually does all of our assembly here for our prototypes. This is part 3 of our Creating Custom PCBs talk, and in the first 2 talks we went over how to actually design a PCB and then get them fabricated, and then this is the last part, which is actually putting all the components on and soldering them up. And we'll be looking at the cleanup board again, and there's 4-ish steps to doing PCBA. So the first step is to actually take the solder paste and put that on the pads. And solder paste are little tiny solder balls suspended in flux, which which lowers the melting temperature of the solder and allows it to flow. And then after you've put the paste on, then you've got to put the components, the SMT, the surface mount components on your board, and then you heat the board up in there's some options of how to do that, and that melts the solder and flows it. It's called a reflow process, and that welds the components to the pads. And then finally, after you've done the SMT, then you would go back and do any through-hole component soldering. Now, for solder paste application, there's two basic options. You can either do it manually by hand, or you can do it via a stencil. We do most of our stuff by hand. Unless you're doing volume production, then it doesn't really make sense to bother with a stencil. And also by hand is super inexpensive, and it takes a little time, but it's not hard. Either way, make sure that when you are purchasing solder for your assembly, make sure to get low temp lead-free solder. Low temp because it's a lot easier to work with, and there's a less chance you're going to damage components when you're actually doing the reflow. And lead-free because you don't want lead in your system, and it gases off, when it's reflowing. And Chip Quick is a great brand that we use. It's really easy to find, and you can get it off of Amazon, and seems to be really good for us. Now, there's two ways to there's two tools that we use to do manual solder paste application. The first is that when you buy the solder paste, you'll typically get it in a syringe and it'll have a tip, and that's fine, and you just squeeze the solder on. But we highly recommend getting a micro dot dispenser. You can buy that off of Tindy.com, and it's a little spendy. It's $30, but boy, does it make a big difference. It's very, very precise in how much solder comes out, and you can hold it a little more naturally like a pencil rather than having to like jam your thumb and do that. So definitely recommend that. That's a real hack and super useful. If you're looking at doing stencils, the stencils are great. They are the fastest way to apply solder, and they're very reliable, and you wind up with very high quality solder paste application. The first thing is that unless you're doing more than like 5 or 10 boards, I wouldn't even bother with it. It doesn't really make it doesn't make a whole lot of sense for just a couple of boards. It's also very expensive up front, so you have to buy kind of a bucket of solder, a container, and it's much more expensive than buying a little syringe. And it's usually $50 to $70. And then you need to order your stencils. You can either get them, you can get them laser cut, which is about $150, or you can laser them, or you can make them at home with a laser cutter or a vinyl cutter. But both of those obviously require that you have those machine tools, and those can be pretty spendy. And also, while you can do stencils by hand, you can line it up, and if you've got bolt holes, and you can put something through the bolt holes. You can do it without a stencil machine, but a stencil machine is really highly recommended, and especially if you're doing multiple boards, which you typically would be doing. You'd be doing volume production. You really want a stencil machine, and this is the stencil machine we use on the right. And it's about the cheapest stencil machine you can get, and it's after shipping, it's almost $1,000. So again, unless you're doing, if you're going to be doing a production run, I wouldn't bother with stencils. When you order stencils for a machine like this, you want to get a frameless, or if you're doing them by hand and trying to align them, you want frameless stencils. Framed stencils all have their edges bent up, and they sit inside a container, and then the machine, this is for like high-end machines that automatically spread the paste, like in a high volume production environment. Now, for the reflow step, there are a number of options. Our number one recommendation is to get a hot plate. We'll talk about options there. There's other options as well, which is some folks have hacked toaster ovens into reflow ovens, and these are okay. They can be temperamental. If you're doing components on both sides of your PCB, you basically have to use a reflow oven. But generally, you're not doing that on at-home designs. And honestly, if you're doing designs that need components on both sides, it's because you're really trying to pack them into a tight space, and that's really more of like a final production design, and I would have those professionally assembled. Honestly, the other option is to use a hot air rework station, and this blows hot air over the components, and that's doable. It's better for like reworking. That's better for like pulling a component off and reapplying solder and putting them back. It's not great for doing your main assembly, but it's good to have a hot air rework station to be able to rework components that didn't solder well. Our recommendation is to get a professional hot plate, and the reason why we say this is that they have really good precise temperature control, and they're not actually that expensive. So they're about $80 on Amazon for a decent one, and you know, the whole setup is about $100. That's including your solder paste and some tweezers. You can also use just a regular old hot plate that you would like make tea or your eggs on in the morning. You know, get an old pan from a thrift store or whatever, and a lot of folks do this at home and are very successful. For the price difference, you know, it's about $60 difference between this and a pro one. I do recommend getting the professional one, just because the temperature control on this isn't as precise, and I think once you get to know your hot plate, then it works a little bit better, but it takes a little bit of time, a lot of trial and error. But this will work, and a lot of people actually do use these successfully. So, you know, your mileage may vary. Now, the actual when you're ready to do the reflow, so we've put the paste on there, and we've either done it via stencil or we've squeezed it on there, and you've placed your components, and there's no magic to that. You basically take your tweezers and put your components in place. Then this last step is to actually do the reflow, and to do that, you basically bring your hot plate up to a warming temp, pre-warm, and that's typically around 180 degrees. But you can look at your solder. Your solder will have a temperature profile, and typically what you do is you bring it up to that temp. You put your stuff, you put your board and all the components already installed on the hot plate, and then you bring it up to whatever the temperature of the melting point of your solder, plus about 10%. You need a little bit of overage. Sometimes you can skip the warming step, and you can just turn it up to 10% above your solder melting point, and then just put your stuff on there. And then what you want to do is you want to let all the solder melt. And you can see here in the image, this is sort of before. This is when we first put the solder on there, and it's just starting to melt. You can see it's getting shiny. And then here it is on the right when it's finished. So that you can tell that the flux has gassed out, and the solder's all melted and very shiny. And that usually takes 10 to 30 seconds, depending. And then once you've done that, then you turn off your hot plate and use tweezers or something to pick your hot board up, and then take it off and put it on something to cool, typically on like hot silicone or silicone mat, like a soldering mat, or even just a piece of wood or something that you don't mind that it might brown up or whatever. It's fine. So that's it. It's very easy, and this is really, like I said, a practical guide for doing this at home. The final step is that if you have any through-hole components, then you want to finish off with your through-hole soldering. And we're not going to cover that in here, because by the time you're doing the SMT stuff, you're probably already familiar with through-hole soldering. But if you're not, check out our video on YouTube, and you can check that out. It's very easy. So thank you for joining, and this concludes our our three-part on creating your own PCBs at home. I hope it was useful for you and give you a good introductory understanding of how to do this, and also just, it's very practical. You can, if you followed through these 3 videos, I think you should be pretty comfortable to try this at home and know that you can do this. This is something that is pretty easy to do, and there's a little bit of trial and error, and you'll get to sort of get the feeling of your designs and the process and whatnot. But it is very easy, and it's very simple to do at home with it doesn't have to be very expensive at all. So again, thank you very much for joining, and best of luck on your hardware assembly and creation journey. Thanks.
That was fantastic. Thank you very much, Brian. So we've covered a lot of ground today. I hope you really enjoyed all the PCB talks, and it's been really fascinating getting to spend time with this crew and really seeing how this can come together. And I want to show you a couple of things. There's some fun stuff that the team's been working on here. So this here is a little board that we've been using just to test out some gaming, and it's been nice to build some hardware that's practical. So things that we want to run. So we did a little configuration with an OLED screen. This is a 1309. You may have seen it in the interstitial over the break, and some buttons. This little piezo speaker I unplugged the wire just so it would make noise when I'm testing sometimes. And it's fun having these common hardware platforms so we can code against and build various games, and done some little common game clones, little Tetris type things, and one called Frogger inspired, and similar things like that. But what's really interesting is seeing the vision for something like this, then be able to take it beyond this really early prototyping stage and turn it into a physical thing. And this here is a ton of fun. So this is an early prototype taking that same concept. So you see the hardware's extended a little bit, but again, we've got a little OLED display here. Just so I can turn on to that battery has any life here or not. It might not. This OLED display, we got, we had the 4 buttons on the other one. This now has 6 buttons and added an analog joystick. And these little guys up here are the piezos. And it's just really, really fun seeing these things side by side, seeing the rough prototype come to life as a physical product. And we've actually got a few variations of that here. Here's another one. Same idea, but this is with the same display from the hack kit. You can see the evolution. And having the ability to take something off a proto board, off a simple wire and connect, and turn it into a real product. And then of course we could take this, design a 3D case around it, and make it look semi-professional at relatively low cost, relatively low effort, a ton of fun. And I'll show you a couple of other interesting examples as well. So we do a lot of work preparing test hardware. So obviously, as Meadow advances through the beta versions, features added, sometimes breaking changes come in. The code base changes quite a bit. So I have to do some consistency test checks just to make sure that, hey, things are running before releases go to the door. And this is our fun one, similar idea where it's been some custom hardware built. And this again has a couple of displays, some buttons, and then there's some other fun things down here. We do some EEPROM testing and analog temperature sensors. And this is a really great board, custom built, that we're able now to use for consistency testing before every release. So the ability to make these kind of PCBs is really powerful. So we're going to come back for our last session in just a few minutes. So we're just waiting for Brian to come back, and we'll be ready. We should be online probably in about 5 to 7 minutes. We're aiming for about 3:15 PST. So we're going to take a 5-minute pause here. If you have any questions, please put them into Twitch, into the chat. We're going to come back with Lexi and Brian. So bring all your questions. They're going to answer some questions we've seen throughout the day. And we'd love to hear from you and answer all of your Meadow and IoT questions. And we'll be right back. Thank you very much. Welcome back.
Good afternoon, everyone.
Hello, hello.
Hello.
Thanks, friends. Thanks for joining. Community, thanks for joining. It's been an awesome day. We've been having a blast just talking about Meadow and all these great new things. We're winding down here, and we're going to end it with a fireside chat. And we'll be taking questions directly from the Twitch stream. So just pop your questions in there, and we'll get started. So my first question is, the world has seen supply chain issues globally. So are we out of that yet? Has that eased up? What's your feeling there on that?
Man, that's a fantastic question. Boy, let me start by telling a little story. So a couple of years ago, we were building the first Meadow board, or some along the line of one of the first Meadow boards. I guess it was 3.5 years ago now. And we had this shortage hit of capacitors, and you couldn't for the life of you get a 0.1 microfarad capacitor. And what had happened was that all at once, a number of manufacturers discontinued large SMT components. So we typically, in modern days, we deal with components of size of like 0603 and smaller, oftentimes 0201 for production designs. And they're very, very tiny, right? But for years, engineers have been using big components in their boards. And there's kind of an interesting secret about components in that a lot of folks don't actually manufacture their own components. A lot of these companies, they don't manufacture their own ICs. They don't manufacture their own resistors. There's a few fabs in the world that actually, there's foundries doing jelly bean components, and there's fabs doing chips. And a lot of folks don't actually manufacture their own chip. They're like, Espressif is foundryless or whatever, or forgeless, and they contract out a forge to bang their chips out. And it's the same thing for resistors and capacitors. There's not like a lot of manufacturers of these. And so what happened was that some of these factories were like, we're not going to run these anymore. You need to stop selling these. And the manufacturers said, yeah, that makes sense. Let's, they're more money and they waste energy and blah, blah. So you couldn't get, like, what happened was that all of a sudden, now this is an interesting thing with hardware, because you have all these designs out there and they are hard-coded to a particular design, right? And it's not easy to tell Ford Motor Company that the millions of controllers that they're shipping, the millions of control boards and motherboards for their cars need to be new components. Not easy to do. Same thing, tell Apple that, etc. And so, although Apple was, bad example, maybe because they had small components, they're modernized. But there's a lot of these things out there that have these like legacy designs. And all of a sudden, the whole industry said, "Oh shit, we've got to." Sorry, I don't know if that's FCC word. Oh poop, we've got to redesign our designs to move to these new capacitors. And in the meantime, like capacitors, 0.1 farad microfarad capacitors at like these bigger sizes, all of a sudden people started paying a lot of money for. And we were doing a modern design, so we weren't really affected by that. And we're also not affected so much on our F7V2 module and our modules that we've been building. And I'll talk about that in a moment. But let me tell you, that taught us that first shortage of capacitors 3 years ago was kind of the first, a lot of us were new to hardware. It was the first pinch that I'd ever felt. And I was like, oh my gosh, this is bad. This is unfun. This can really it doesn't hurt the big companies so much as it does the little innovators like us and other companies. And so when COVID came around, I had a sense that this was going to happen again. Like this, this was everyone thought COVID would really shrink the economy and stuff, and would really, technology would really get hampered by it. And I've been running remote organizations for almost 20 years now. And I was like, that's not what's going to happen, man. This is like all these changes are always, and disruptions are always a boon for innovators and disruptors. Technology is by definition an innovator and disruptor, right? Because technology is always moving things forward. So I knew this was coming, and we hustled so hard to make sure that we had components for our latest runs, right? We ran out of boards, not because we didn't have components, but because we didn't want to make a bunch of new, we didn't want to do another run of F7 V1s when we knew that we had this hot new design coming. We just were waiting for it to validate. So we put ourselves in a position in which we actually did really well in this supply chain shortage, but a lot of folks didn't. And there is no indication that in the next 2, maybe 3 years, there's going to be a real let up of this. And so like it's going to be a challenge for everyone and it'll be a challenge for us as well as we like continue to expand and have customers ordering new stuff. But we've done pretty well thus far. But I think we're in this for another couple of years. There's foundries coming online and whatnot to make more components to increase capacity. But here's the reality of the situation. You can't just take so a lot of the high-end semiconductors in the world are made by TSMC, Taiwan Semiconductor Manufacturing Corporation, and they're in Taiwan. And this is actually a big a political driver right now. This is a geopolitical driver because both United States and America are and really the world and China, China and the United States, but also China and the world are sort of like vying for access to these components that are coming out of Taiwan, which is a big driver of the geopolitics of Taiwan today because of their strategic importance in the world. Now, TSMC has very high tech fabs. So fab is the dies and and whatnot to make ICs. It's not really a die. I mean, it is a die, but there's lasers and there's magic and there's stuff, right? You can't just take TMC and duplicate it. You can't, like, they have a lot of IP around building high-end chips. You can't just we're talking about trying a lot of nations, including the United States, they're talking about bringing some of that manufacturing back, and eventually maybe we will. But the idea that you can take these like very high resolution dies and get them to work reliably at scale in other places is like not really a reality. And so while people are sort of banking on a rapid expansion of manufacturing capability domestically here in the United States and other places in the world, I don't think that's going to happen as nearly as fast as people think that it might, right? We've been in the business for 5 years now and doing hardware, and we've learned a lot. I've learned a lot, and that kind of capability, that kind of capacity is not like a copy paste sort of thing. And so I think we're going to be pinched for a while. Now, with that said, there are practical ways to deal with this, to compensate for this, and to deal with it. The first thing is that you want to order your parts well ahead of time, right? And for most of us, for most of you as customers of ours, you're a little bit insulated from this as well, because for instance, the components that are really in demand are ICs. They're your microcontrollers, they're your high-end MOSFETs, etc. And for the most part, when you're building IoT, you're going to be taking modules, pre-built modules like this, like our Meadow board, and then you're going to be hooking up sensors and things like that, and displays, things that don't really have the same sort of demand and the same sort of, you're not going to be fighting in the marketplace as much for those. So we've actually de-risked a lot of your product and your production by doing the hard stuff on the module. And we de-risked ourselves by choosing chips that had more capacity in the market. So for example, right now, we are about 7 to 8 months lead time if you want 10,000 Meadow boards. So let's say you're going out to production. You've got this awesome new product, and you need 10,000, right? And that's not, you're not going to need 10,000 right away anyway, because usually you spin 100, then you spin 1,000, you get those out into tests, and then when you're ready to go out to commercial production, it's like 1,000, and then or 10,000, 100,000, so on, right? So you can order those, and we got about an 8-month lead time, give or take, on this. If you're, for example, needing particle boards right now, their lead time is 1.5 years, and it's and I wouldn't be surprised if that went to 2 years. The reason why is that if you look at like our board, we have a chip on there, a very high-end chip there, that doesn't have the same sort of, our design is newer, and it doesn't have the same sort of supply constraints as like a lot of the commodity lower end boards out there, right? Like the STM32F4, ours is an F7. You can't get the F4 right now, even if you wanted to. It's 2 years to get those chips. There's the STM 32F0. Again, it's like, it'd be almost impossible to get those chips. So yes, the supply chain is probably not going to get better. It's probably going to get worse before it gets better. But on the other hand, as an implementer, from your perspective of a hardware creator, it is also like, if you're using pre-designed modules like ours, you're insulated a bit from that. So long-winded answer. I hope that gives some context and an explanation there. If you have any other more specific questions, I'm happy to answer.
Cool. Thanks for that, Brian. Next question, I guess for the panel here. What new Meadow feature are you most excited about? You can try to be unbiased and pick something you didn't directly work on, but you can choose whatever you want. We'll say Adrian first.
Yeah, I'll jump in, and I'm super biased on this. I'm really excited about adding support for the hardware 2D engine in the Meadow F7. So we're going to see a big boost in graphics performance on our displays. So it's going to add hardware blending. I think there's some hardware sprite capabilities, hardware JPEG decoding. So really big boost on creating user interfaces, especially on these high-res displays.
Cool, Chris?
Well, I'm going to say that I'm biased as well. I think Meadow for Linux, a lot of the stuff that it's unlocking, there's a lot of cool stuff that's going to come out of this. And so I'm really looking forward to some of the neat things that it's going to enable.
Yeah, for sure. Super cool. And Alexi?
I think it will be OTA for me. It's going to be so nice to have this life cycle in the Meadow that's sustainable. We can push system updates to users. If they subscribe to it, they can set up their own system. I'm very excited about it. I'm excited about the side effect it might have of like allowing people to push a new version of their app just for development purposes and not even have to plug the Meadow in. I didn't talk about it before. It's just kind of like a side effect of being able to push new apps on it that is gonna make the developer cycle a little bit better too. So yeah, I would say all the OTA system and app updates stuff.
I'll choose debugging because it seems like, oh, it's just debugging, but we didn't have it for so long, and we just got used to doing console write line. But once you're actually stepping through, you can see everything. It's just, man, it's just like a breath of fresh air. I know you covered a lot of stuff already, Brian, but what is your one thing that you love?
One thing that I think on the software side is probably AOT. AOT, we have this sort of long-running initiative to make things lighter and faster, right? Lighter and faster. And AOT and linking are sort of combined with those two. But like, I think the more that we push on that, the farther we take that, the smaller that we get this, and the more places that it fits. And I would like to see Meadow everywhere.
Yeah, absolutely. We have a question coming in. Is OTA a self-hosted solution or provided only through the Wilderness Labs cloud?
Yeah, great question. So OTA is tied to our security stack, which is tied into Wilderness Labs Meadow Cloud. So all the key management and identity management today will go through Meadow Cloud, and that will be how you'll do OTA, and that'll be absolutely free for developers, on devices up to 100, 100 devices, and then beyond that, we'll have pricing for businesses and enterprise.
Cool. All right, next question. We announced a lot of new updates today, but what's on the horizon? Like, what's the next roadmap for the vNext?
God, that's a great question. So on the software side, we've talked about a lot of the stuff that's coming out, AOT, OTA, other anagrams of those three letters, and lighter, faster. But on the hardware side, there's some pretty big things that we're working on right now. And the first is we'd like to spin an ESP32 only low cost board. This is a board that target price point would be somewhere like $20 and below, much cheaper at scale. And that really excites me. That I think the idea that, because then we would have sort of we have Meadow sort of across the hardware gamut, right? We have, as announced today, we've Meadow on Raspberry Pi, so you can do very high-end AI loads, workloads, computer vision, HDMI, etc. And then you've got your high-end but still battery power conscious microcontrollers. So our STM32F7 with an ESP32 coprocessor, which one of the things that we're going to do is that we're going to enable TensorFlow Lite to run on the coprocessor. This is a really cool architecture. What this will enable you to do with these boards is that you'll be able to do all your hardware real-time stuff on your main MCU, offload all your AI workloads to the ESP32 coprocessor, which is actually a dual core chip. So you can have one core doing that, one core doing network as necessary. And that gives you that honestly covers kind of 75% of enterprise IoT scenarios. But then adding an ESP32 gets that kind of bottom, where you're really budget conscious. And there's a bit of overlap there too with our F7 in terms of use cases it will cover, but really from a budget conscious or a place where you need a lot of these things everywhere, and you still want the full experience of Meadow, and you want .NET 6, and you want AOT, and you don't want it to be interpreted and stuff like that. I think I'm really excited about that. So that's a big thing that's happening in hardware. The other thing that there's two other things happening in hardware that are simultaneous to this. We are working on a cellular connectivity model. And so that would be an F7. And instead of having an ESP32 for Wi-Fi and Bluetooth, we would have a cellular module on there. And that is in design right now. We've done it. We've drafted a design of that, and we need to do another draft, and then we're going to, get it and test it. And there's some software stack that we have to do in there because we want you to connect to the internet via cellular radio or other radios in a completely hardware agnostic way, right? You don't, as a developer, you don't need to be you don't want to be thinking about the low level stack and stuff. And so we've got some software to do there to make that completely seamless. And that'll be really awesome. I think adding cellular connectivity is going to unlock a lot of IoT use cases that, we don't really cover for today. And we have customers that are needing that. So that's really exciting. And then this other thing that we're doing on the hardware, something that we've been working on, is an industrial control reference design, and this is something that we'll sell as a hardware, as a turnkey hardware as well. But something like if you Google the Arduino, I think it's called machine control. We want to do something almost very similar. We've had this idea for a long time, which is have all your industrial IO that are voltage protected and automatically, has like the mod bus built in, an RS485 and all the industrial stuff, and maybe even a little screen on there that's easily programmable via Meadow, and have all of the industrial stuff out of the box. Like that's something that we've been working on, and we've been solving like kind of little pieces of that and learning about that hardware, and then we'll get that out. And that's really exciting. I know Chris Tackey's over there nodding because he's like, I need this, because if you look at his shop, his lab back there, you can tell Chris is our industrial IoT guy.
Yeah, there's a question, does it include LoRaWAN?
So that one, neither one of those do, but I would like to make LoRaWAN much more easy to integrate. You can actually do LoRaWAN today with Meadow, and there's Clifford Aegis has done a lot of work, Bryn Lewis, our New Zealand friend, Kiwi friend, has done a lot of work to make drivers for that and stuff. I would like to, and that's really easy to plug in. There's not like, we could probably spin a module, but it's also really easy to just plug a LoRaWAN and make if you need to make a breakout board. I'm not sure we want to make an all-in-one. Maybe we do, really depends on our customers. If you tell us that's what you want, we will do that. But what we would like to do is make sure from the software perspective, again, like that network stack is just transparent. We're going to publish this driver for our Ethernet, and it'll be, or we're working on like a pluggable NUTX driver model where you can be able to take LoRaWAN, plug that into the network stack, and then it will just be, it'll work like anything else. So that's the part of that we're working on, is making sure that's a really easy software thing.
Yes. So
yeah, maybe LoRaWAN would be awesome.
Yeah. Yeah, there's a lot of curiosity on Chris's lab. What's the craziest, most exciting thing you've ever built?
Can you talk about them?
I've got a wide range of things I've done. I've put Raspberry Pis in space. I have worked on manufacturing high-end explosives, like the machines that actually mix the explosives. I've legit set off explosives detectors at the airport before, because I went from one of those facilities to an airport. I've worked on, building control, a lot of industrial automation, robotic arms that, are big enough that, they could easily crush you. I think the biggest robotic arm I've worked on, if it extended straight up, was 18 feet tall.
Oh.
I've worked on machine tools like a lathe. Most people are familiar with what a lathe is. The largest one that I've worked with was big enough you could actually take a car, stick it in the chuck, and it would spin an entire car. It's that big, used in the oil and gas industry. So, yeah, I've worked on a lot of nutty things, lots and lots of them.
Yeah, so if you need to build it, just ask Chris. He'll know. Cool. And a question for Alexei. You're kind of a mono nerd. Why do you love mono so much?
The question is, why do I love mono so much?
Yeah.
I don't know that it's a show. It's funny. I have a single commit from 2004 or 6. When I was a student, I was obsessed with .NET. I made my first commercial product using the Visual Studio .NET beta, like the very first .NET that we had. And I was very excited about Miguel's like .NET on Linux thing. Worked a little bit as, just as a student. Just knew by name some of the names that I worked on with later. And it was one of the greatest software engineering teams that I worked on. So yeah, big fan. It's behind a lot of things, and it's open source, and yeah, I like that. I like it. Big fan.
Cool, thanks. Yeah, speaking of open source, we the question is, like, you guys have released a lot of open source today. Why is that important to the company, and what's the company's goals around open source?
That is a fantastic question. So, you know, a lot of us come from open source backgrounds, and we believe in open source. We believe that nothing is built in a vacuum, that scientific progress and humankind's technical progress are bettered by sharing of knowledge and IP. And Wilderness Labs itself would not be possible without the IP work of titans like Miguel de Icaza, like Jeff Norton, you know, Jonathan Pryor, and Greg Nutt, and all the other folks that I'm not, you know, I don't want it to be an Oscar speech here that goes on 10 minutes of naming fantastic folks that we rely on, but like, we're able to make a business because of this. and open source really does feed the world. It feeds technology in a way that's really fantastic, and can you know, work in also in this capitalist market that we exist in, and no one beats the market. You know, like, the market is this gazillion ton thing in the room that you are at the whim of, right? But open source is still, like, it's still possible, and there's ways to make that work within that, and we fully believe that the more that we open source and the more that we contribute back to that world, the better the world will be. Now, we also have to be competitive in that. So there's a balance, but my bias is towards leading a company that open sources more and more and more and more. And eventually I'd like to completely open source Meadow OS. And I'd like to backfill that with revenue from enterprise revenue from Meadow Cloud, and what other things that we do. Maybe, you know, the hardware, you know, we get a little bit of margin on the hardware, and still, because of our scale, we can sell to you for cheaper than you can make it. And we solve the supply chain stuff, etc. So I would like to really make Meadow. I'd like to see Meadow run everywhere, right? And today was a big step in doing that. And we open sourced a lot of stuff today. We open sourced all of the. You can basically port. You can now port Meadow any place that you have .NET, right? Real .NET. Any place that you have generics and modern, like, you know, any place that's not .NET, like circa 2000. You can now bring Meadow to those platforms. And that's a huge move, you know, and it was such a big and sort of like almost scary move at the beginning. I was like, I don't know, should we do this? You know, blah, blah, blah. But it's a brilliant move. And like I said, I bias towards, you know, let's get crazy. Let's attack this, and we'll figure out a way to make sure that we monetize and we do the things that we need so that we can continue to innovate. So that's really our approach, and that's how, you know, we've led this. And like I said, I want Meadow to be everywhere. You know, I think it is by far the greatest way to build hardware, like bar none. You compare any other platform and nothing touches Meadow. Just absolutely nothing touches the experience. And I know that we're not quite yet production ready. That'll come, you know, early next year, but like nothing touches it, and I want it to go everywhere. So we'll figure out a way to open up more and more, and, you know, creative ways to backfill that.
Awesome. And I guess anybody can pitch in on this question. So I'm a web developer and I want to get started in hardware, but there's so many new things to learn. What should I get started on?
Go to Hackster.
I have a piece of advice for there. Because learning a new platform can be daunting and overwhelming. I've been in the industry for over 25 years, and I've gone from one, you know, revolution to the other. First things that I was hacking on were Commodore 64s, and along the way I've learned a lot of different skills, and hardware is brand new to me. You know, like at some point I learned hardware. My piece of advice here is pick a project and go after it. Just pick a project. Figure out something that you want to do. I want to make a smart beehive. And I want that to measure the height, the weight of the hive and activity within the hive and climate outside. Okay, break it down. Pick a project, break it down. Just solve one piece. Solve one piece and then move on to the next. And if you get stuck on this one, move on to the next thing and then come back to it. Don't get stuck in the mud. Pick a project, break it down, and just go for it. And we are here to help. Join our Slack, you know, come and chat with us, get recommendations, talk with the rest of the community. Just pick a project and go.
I was waiting to see if Chris was going to say anything.
You know, I was trying to decide whether or not I had anything to add, because really that's what it's about. Hardware is its own beast. Don't be afraid. You are going to smoke parts. You are going to burn things up, guaranteed. But Brian's advice,
magic smoke.
Yes, I think we've all done it multiple times. But Brian's advice to pick a project and then deconstruct that project into small pieces and go, how do I read a load cell? How do I wire a load cell? What does it look like when it's not working? Because you will actually learn a whole ton about how hardware works by the mistakes you make. When it goes right, you actually don't learn a whole lot. It's when you go, I spend 4 hours trying to figure out why something isn't working, and oh, you just had 2 wires crossed or something along those lines. And, you know, we do our best to try to throw meaningful errors and stuff like that to lead you. But a lot of times there's just nothing we can do at a software level to tell you what's going on in the hardware. So making those mistakes and learning those things is important. So starting and go, how do I do X? And then how do I add Y on top of it? And eventually you'll get to the solution to whatever problem that is that you're building.
So you just got to get started and jump in and keep going. Yeah.
Don't be afraid of it.
Yeah, great advice. Great advice. I got another question here. How does your deployment story fit into Azure IoT Edge?
Yeah, great question. So our deployment will be fully scriptable, fully CI/CD-able. In fact, out of the box, it'll work from CLI and script before it'll ever have a web interface. So you can absolutely like automate that via Azure Edge, and also we have you know, you can also push up data to Azure and whatnot, or data anywhere really, because we've, you know, all the network stuff.
Yeah, and in similar vein, I think you would be able to deploy via Greengrass as well through AWS if that was the channel that you prefer.
Got it. All right, another question here from Xcode. Have you seen what Particle has done with its ability to have a console, API, and variables that are accessible from a central point? Do you think you'll be offering something like that also?
Yes, so that's part of the vision for Meadow Cloud, is to have data aggregation and brokering if you want to use that and have that built in. So same sort of thing, right? You can batch data up, you can automatically just push data to the cloud, and then you can broker that and put in you know, you can grab a connector and push that on elsewhere. So absolutely. We've been thinking about that for a long time.
Yeah. Exactly. ETA?
Yeah, no ETA on that. We've got, you know, our core stuff is priority. We need to finish out our OTA. We need to launch a security stack. Those are our priorities right now. We want to get the core features up, and then we can go on and do other things.
Nice. All right, next question. Do you guys have a favorite YouTube maker you watch?
And where's Jorge? We should get Jorge up there.
I've got a few answers though, and I'll take maybe the simple but fun choice. I mean, I'm a big Electro Boom fan. Maybe isn't a full-on maker, but nod towards.
Mateus Castillo. What's his? It's called. I forget his handle. I just know him by his name. Make Codes. Is it Make Codes? Oh, and gosh, my absolute favorite of all time. I'm terrible. I'm sorry, I'm terrible with names. She's Swedish, and she's got a tumor in her head named Brian, which is terrible. But she is fantastic. I'm sure one of you know who she is. She was the queen of bad robots.
The queen of robots.
Come on, help me out here, folks.
Simone. Was she the one that made that?
Simone Gertz.
Simone Gertz, yes. Yeah. And I don't know how that's actually pronounced because she's Swedish. She was born in Sweden, and I actually used to be conversational in Swedish, but I do not know how to say her name in proper pronunciation. I don't know if it's Simone or I don't know what, but she's awesome. She's honestly such an inspiration. Just love her.
Great Scott's another good one too. He's probably electronics. Totally fun to watch. Great explanations.
All right, we got another question here. Will you be selling the breakout board that you have pictured in your blog?
Breakout board pictured in our blog. Is that, one sec. Is that this? Is this the one, or would that breakout for our core compute module, or is there, because we've got a lot of breakout boards. Meadow presentation, in case you missed it. At blog. All right, I'm going to look it up. Oh, ISU.
Oh.
ISU. Okay, so this is a fun question. So we have this board and we call it ISU. We all have ISU. I had never considered selling ISU, but we absolutely can. So ISU is our analog I2C serial UART board. Is my internet still good? Did you guys get all that? Because it froze for a minute. So this is a board that exercises everything except our digital I/O, and this is it does exercise some of our digital I/O, but this is our board that is specifically for test suite. So when we check in code for NutX, the idea is that then test suite goes and runs a bunch of stuff on this. And that's why we all have this. And we have like DIN industrial mounting rails. You can't see it, but I've got some over here on my wall, and we've got ISUs. So ISU is meant to make sure that we have great code releases. And we're working towards completely integrating that into our CI/CD. Now we're in progress. We've actually made a lot of progress here, but it's not quite there. But yeah, we could absolutely sell these if you want them. They're pretty cool. They've got an I2C display. They've got an SPI display. They've got two EPROMs. They've got some buttons, and they've got some analog temp sensors and things like that. If you really wanted one of these, we could probably make one. Although I suspect what you want would be something a little bit different. Yeah, maybe Juego. Maybe our game board or something. So we could probably sell you them if you want.
Yeah, there's another question here about another breakout board for LAN connections. Will we be selling those?
Yes, we will have. We will be selling. So with our core compute module, you can get a dev breakout board, and this has. It doesn't actually have all the through-hole stuff on this one, but it does have two Ethernet ports on it, and one's optional, so you could use daisy chain in an industrial scenario, and it also has you don't see it, but there's just a couple of displays and a SD card, and then an integrated ST micro debugger and stuff. We will sell something like this for our core compute customers. So we're finalizing them right now, but we will absolutely be selling these for folks that want to move to the core compute and need a reference design to play on, to have Ethernet and SD card.
Cool. Well, we're just about out of questions. I'll give the stream another chance or two to wait for people who've been sitting on the fence. Yeah, only for core compute.
Yeah, so the core compute has Ethernet broken out, but the Meadow F7 developer board does not, because it doesn't have enough pins. You need like 32 pins or something for the RMII interface, and the core compute module has like piles of I/O on it. So that's where Ethernet is available. We may make a small Ethernet board that is like more of a dev form factor. If that's something that you're interested in, definitely let us know. We've considered that. In fact, what we would probably do is it would be kind of a double wide dev board, and it would look like a Meadow F7, and then it would have power over Ethernet. So it would have a transformer to get your power from Ethernet, and then it would have your 2 ports and your LAN chip. So that's something we've considered. It really depends on you, honestly. If that's something that you need, then reach out to us and we can chat.
Cool. Well,
Any thoughts on using state machines?
There you go. Any thoughts on using state machines or the active objects pattern from traditional embedded software development?
I can talk to the first part. Maybe Taki can speak to the second part. So we use state machines all the time, all the time. In fact, the patterns that we looked at today in the application architecture, a lot of those are state machines. They're just a little nicer, so a state machine in its most basic is like actually forms the basis of a controller pattern. And it's just the idea that it keeps state. So you have an object that knows what it's doing, and has some information on what's going on, and it keeps that. And that, like, for instance, the patterns that we looked at today, the singleton patterns that we used for the Bluetooth energy thing, or the climate, there was the climate monitor that runs as sort of a grand central dispatch in Klima. That's a state machine, so we use state machines all through our architectures. I don't know about the active object pattern. Taki, is that something you have seen?
I've definitely seen it. It's not something that I typically use. I mean, state machines is where I usually run them.
It's like an async strategy, is it not?
Yeah, it is something designed to control access to synchronized objects, things like that. So if you're running,
we don't even need that with .NET. We got all the fancy stuff.
Right, which is why I just don't use it a lot. Yeah, I still write C and C++ occasionally, but boy, I sure try to avoid it.
Yeah, we got task, async await, all the threading and semaphores.
Async await in the background creates a state machine for you. So async await is a way to do asynchronous processing and have a state machine sort of like miraculously be generated for you. So in the background, that's how we do async await in .NET world. State machines in .NET world.
Cool. Well, I think thanks. Well, I think that's it for questions, and we're just about right on time. So I think we'll wrap it up now. But on behalf of Wilderness Labs and the team, we just want to thank you so much for joining us for our second annual conference that we do every 2 years. It was really exciting to have you all on board. And
it's only been a year and a half. Come on.
Well, it was COVID, so it's fine. We're fine. You get a pass. But yeah, we just want to thank you again for joining us. It's been a blast, and we wouldn't be here without you guys, and we thank you so much for your support. So with that, thank you, and we'll see you next time.
Woo! Thanks, everyone. Thanks for joining, and hats off to the team who put on a fantastic,
amazing job. Yeah,
conference this year. Really. Hey, Jorge!
Hey, Jorge.
Made it just in time
Jorge,
to say.
who's your favorite maker?
Oh man, I love this guy is called his channel is Stuff Made Here. I don't know if you guys have seen him. He makes these amazing garage projects like aimbot arc weapon. What do they call it? Bow and arrow.
Bow and arrow. You can't call those garage projects. He puts way too much time.
Yeah, definitely. Yeah, that guy is amazing. Really good. I'll reach that level later. Stuff Made Here, yeah. Cool.
Thanks, everyone. What an awesome day. What a great dev conference.
Awesome.
Lou for now.
Thanks. Bye.
See ya.